Welcome to this section. Great work so far. I would like to give you my sincere congratulations for reaching this part of the course. We will start covering inheritance and how it is very helpful in object-oriented programming. Inheritance involves defining classes that inherit attributes and methods from other classes. Just like a family tree, classes in Python can inherit from other classes. So we are sort of making like a hierarchy with our classes. Inheritance helps us reduce code repetition. It also helps us to reuse the code that we have written and improve readability. We will write more concise and understandable code, so we will organize our projects better. So overall, we will have a better design for our code. Inheritance helps us to follow the principle of don't repeat yourself, DRY. It basically states that whenever we can, we should aim to reduce code repetition in our programs. For example, let's say that we need to represent a triangle and a square in our program. They both have common characteristics, such as, for example, the number of sides and the color. And they also have common functionality, such as, for example, displaying the length of their sides, displaying their color, or changing color. So, we could make these two classes, triangle and square, inherit from a more general class called polygon. Both triangles and squares are a type of polygon. So we can write the common attributes and functionality that they share in this more general class and make them inherit the attributes and methods from the general class. This is the basic principle of inheritance. This way, if we need to add another polygon to our program, such as, for example, a rectangle, we won't need to repeat any code. We will just make this new class inherit from the polygon class, and all the functionality that we will need that is shared by all these polygons will already be defined in the polygon class. Classes usually inherit from more general classes that represent more abstract concepts. For example, in this case, polygon is a sort of like more general or abstract concept. Can you imagine or visualize a polygon? It's more difficult to imagine a polygon than to imagine a triangle, a square, or a rectangle. So those more specific classes usually inherit from more general classes that describe them in a more abstract way. When we implement inheritance, we represent common functionality in the parent class. We define that functionality in our attributes and methods in the parent class. And we add new functionality or customize the existing one in the child class. So we are reusing our code from the parent class and extending it or customizing it in the child class. In our example, triangle, square, and rectangle would be the child classes, where we would extend the functionality or customize it. And polygon would be the parent class. Here we have another example. A car is a vehicle and a truck is a vehicle. So they have common attributes and functionalities, such as, for example, turning on the engine or displaying the fuel left and the current speed. So we can define a more general class called vehicle to write the shared code in this more general class and make those two classes that are more specific, a car and a truck, inherit from this more general class called vehicle. Another delicious example is the dessert class. A brownie is a dessert, and an ice cream is a dessert as well. So they can inherit from the more general class dessert. They would be the child classes of dessert, and dessert would be the parent class of brownie and ice cream. The basic relationship to identify when a class should inherit from another is that the child class, written right here on the left, is a type of the parent class. For example, in our initial example, a triangle is a polygon. So we have the triangle class as the child and the polygon class as the parent. Right here we can see this, child and parent. Triangle is a polygon. Square is also a polygon, and rectangle is a polygon too. So these would be the child classes, and they would all inherit from polygon. In our vehicle example, a car is a vehicle. Vehicle would be the parent class and car would be the child class. A truck is also a vehicle, So truck would be the child class and vehicle would be the parent class. In our dessert example, brownie is a dessert. Right here, brownie is a dessert. So brownie would be the child class and dessert would be the parent class. This would also be the case with ice cream, child class and parent class. So you can see how this relationship is A works to create the hierarchy. We can also have this type of hierarchy, which is simpler, like one child class that inherits from a parent class. In this case, we just have the brownie class that inherits from dessert. A class can also inherit from multiple classes, and multiple classes can inherit from the same class. So we can have different shapes or types of hierarchies. This is an example of a hierarchy where we have one child class called TA, teaching assistant, that inherits from two classes, student and faculty. Because the teaching assistant in a college is usually serving both as a student and part of the faculty, so it should inherit the attributes and methods of both of these classes. And finally, right here we have a more elaborate hierarchy to show you how versatile this can be. We have 3 different levels. We have a vehicle, which is the most general way that we can describe a transportation method, vehicle. This would be the parent class of land vehicle. Let's say that we want to classify vehicles like this, land vehicle. And then car and truck are types of land vehicle. A car is a land vehicle, and a truck is a land vehicle, and a land vehicle is a vehicle. So that is how we are preserving that relationship and building up the hierarchy. If we need to add, for example, another type of vehicle, we can do so very easily. Like, for example, air vehicle. For an airplane, we would add another class that inherits from vehicle. And that way we can extend our hierarchy and the functionality of our program very easily. That is why we use hierarchies, because we can reuse code, avoid code repetition, and make our code more understandable and readable. Awesome! Please take a moment to analyze the objects around you and how you could represent them in a hierarchy in your code. Now let's see how you can define parent and child classes in Python. It's actually quite simple in terms of the code that we have to write, so let's see how we can do that. This is the general format. We have a superclass, which is the parent class, and a subclass, which is the child class. This is the class that will inherit all the attributes and methods of the superclass. To make the subclass inherit from the superclass, you just need to write the name of the superclass right here within parentheses, after the name of the subclass. Previously, we were just writing a colon after the name of the class, like this. But now, to implement the hierarchy, we will have to add parentheses, and within those parentheses, the name of the superclass. This tells Python that we want our class to inherit from the superclass. For example, if we have a polygon class and we have a triangle class, we could write something like this. The name of the parent class, polygon, is within parentheses, next to the name of triangle, the subclass or the child class that will inherit from polygon. Always remember this. Within parentheses, we write the superclass. Like this. We would have this hierarchy by writing this code. Triangle inherits from polygon. Triangle inherits from polygon. Let's implement this in our code. We will write the class headers to implement this inheritance, this hierarchy. First, we define the polygon class. We are just writing their headers for now, okay? In the body of the class, we will write pass to fill the body so we can run our code and test that it was defined correctly. After that, we have to define the triangle class. And to make this class inherit from polygon, we just need to write that name right here, polygon. And we add pass right here. This is telling Python that we want the triangle class to inherit from the polygon class. We're basically creating the hierarchy that you saw in the diagram. Now try to write a square class that inherits from polygon. You can just add a pass statement to the body of the class for now, like we did with triangle. We will be adding functionality and attributes to the class in the coming videos. Pause the video, write the class header, and then come back. Welcome back. Now we will have this hierarchy. Polygon is the parent class of triangle and square. And triangle and square are the child classes of polygon. Let's write this in our code. To create the hierarchy that you just saw, you just have to write this class header. Now we will have a square class that inherits from polygon. And we will fill the body of the class with a pass statement, like this. Right here we have two classes that are inheriting from polygon. Triangle and square are the child classes of polygon. You can see it right here within parentheses. And polygon is at the top of the hierarchy. If we save the file and we run the code, we don't get or see any errors because the classes are correctly defined. Now that you know how to tell Python that you want your class to inherit from another class, let's see how you can make your class inherit the attributes of the class. Previously, we were defining the hierarchy with the header. Now we will dive into the details of how you can inherit the attributes of the superclass. Let's see this in our code. We will start by defining a polygon class. We write the header first, and then we will have to define the init method, like this. Each polygon will have a particular number of sides, and it will have a color. So we say number of sides. We assign them as instance attributes, color, and color. In this section, we will be working with public attributes right here to focus on inheritance. But you already know how to work with non-public attributes in Python. Okay, so now we have our polygon class. So let's define our triangle class and make this class inherit from polygon. In the previous video, you learned how to write these class headers to set up the inheritance. We're just going to have an empty body for this class, but we can still use it. Let's see how. We will fill the body of this class in this section, but just by writing this line, we're already making the class and making it inherit from polygon, so we can create instances of triangle. Yes, that is surprising. With inheritance, we can still create instances of triangle, like we are doing right here. We're going to call this instance myTriangle. It will be an instance of triangle. And what do we have to provide right here as arguments? We see parameter color unfilled and parameter number of sides unfilled. And those parameters are these parameters that we can see right here, color and number of sides. These are the parameters of polygon. By default, when you don't write the init method in this class, in this child class, you can create instances by using this init method from the superclass. When we create a triangle instance, we will actually be creating them by calling this method, init. We will have to provide the number of sides and the color. The color will be blue, and the number of sides, we're going to set this as a parameter, will be 3. Okay, awesome, we don't see any errors right here. What do we have to do then? We're going to check if the triangle instance actually has the attributes that we defined. Number of sides and color. We're using dot notation to access these attributes. You can immediately notice that it does have the attributes because we don't see any yellow warnings. If we save the file and we run the code, we see this as the output. The number of sides is 3, the value that we passed right here, for the number of sides parameter, and the color is blue right here, because this corresponds to the color parameter that we defined right here. Great, so now you know that if we don't define the init method in the subclass or in the child class, when we create an instance of that class, by default, the init method of the superclass will be called. If the subclass has its own init method, the attributes of the superclass are not inherited automatically. Previously, we inherited the attributes of the superclass automatically because the subclass didn't have its own init method. But if it does have that method, then we must write it explicitly. Let's check that this is true and how we can do this with our triangle class. Let's see how we can do this in our code. Here we have our polygon and our triangle class. Let's add or define an init method for the triangle class, right here. The triangle will have a base and a height. These are the two attributes that we will define for the triangle instances. We are writing the init method with the same syntax that we typically use. But right here we see a warning. We see call to init of the superclass is missed. What does it mean? Well, if we try to run the code right now, let's see what we get. Now we see this error. Attribute error, triangle object has no attribute number of sides. This line is throwing this error. Print my triangle number of sides. Why? Because now the triangle doesn't have this attribute. When we define the init method in the subclass, we are sort of like hiding the method from the superclass. So this init method is the one being called. We are not creating anywhere in the body of this method a number of sides attribute. This is why we get this error. We are not creating these attributes because this method in the superclass is not being called. So how can we fix it? Let's see this in detail. This is a line of code that you have to write to make your child class inherit the attributes. First, we write the name of the superclass, the class that you wrote within parentheses. We can also write super right here instead of the name of the class, super followed by parentheses. Then we write a dot, the word init, because we're actually calling the init method of the superclass, then self. This time we do have to specify self, and finally we have to pass any arguments that the method requires. Let's do this. Let's implement init in the triangle class, and you will see how the attributes are now inherited. To fix this error and to add these two attributes to the triangle instances, number of sides and color, we have to write the line that you just saw. How can we do this? Well, we write the name of the class, which is polygon, the same name that we wrote within parentheses, and then we're saying call the init method of the polygon class. And how can we call this method? Well, we need to pass these arguments. This time we do have to specify the value of self, because self is this one right here, the instance of triangle that is being created. We are passing it as an argument to the init method of the superclass, so we have to specify it. And then we have to specify the number of sides and the color. We can pass a fixed value when we call this method. So for example, triangles always have 3 sides. We can define this as a constant, as a class constant, and just pass that value as the argument. We say triangle dot number of sides. This value will be 3. And then we also have to specify the color. For that, we will need to add another argument right here, a third argument, so we can specify the color when we create the instance. We add it to the init method of triangle as a parameter, and then we are passing that value as an argument when we call init of the polygon class, right here. This line does all the magic that we need. It calls the init method of polygon, so it adds these two instance attributes to the instance that we create of the triangle class. Right now, since we made some changes to the init method, we have to make some changes to how we create the instance. Now we have to specify the base, the height, and the color. Let's say, for example, base 5, height 4, and color blue, like this. Now we don't see any errors because we're passing the 3 arguments that the init method of the triangle class requires. And we're still going to get the other attributes of the superclass because we are calling this right here. Now, if we try to access the attributes number of sides and color, we don't see any warnings because our triangle will have those attributes. Number of sides, color, we can also print the base and the height. So you can see that we are actually adding more attributes to the triangle that any polygon does not necessarily have. Not all polygons have a base and a height. So that is why we are defining them right here in the triangle class instead of the polygon class. If we save the file and we run the code, we see this right here. Number of sides of the triangle is 3, which is correct. The color is blue, the color that we specified right here. When we write blue right here, this argument is passed to the init method of triangle. It is assigned to the parameter color. Then we pass that value as an argument to the init method of polygon right here. It is passed as an argument. It is received right here by the parameter, and then it is assigned as an instance attribute for the instance. This is basically how the process works behind the scenes. We're going up in the hierarchy and we are calling the method of the superclass. And we also have the values of the triangle, base and a height, 5 and 4, that we assigned right here. So okay, work so far. Now you know how attribute inheritance works in Python. Welcome to this practical coding session. We will define an employee class and a programmer class. We're going to assume that a programmer is a type of employee. So we are going to start by defining the employee class, the header, and then we define the init method. In the init method, we're going to keep the class simple so we can focus on inheritance, okay? So we're going to create the attribute full name, and we are going to create the attribute salary. Those are two attributes that are common to all employees of a company. They have a name and they have a salary. We could also add, for example, the employee's ID number, the employee's department, and other attributes that will be common to all employees. And then we can define the programmer class. But this time we have to specify something within parentheses. Remember what this is? It is the superclass. A programmer is an employee. So employee is the superclass and programmer is the subclass. After we have that set up, we need to define the init method right here. And how are we going to do this? To create a programmer, we need to know its full name, its salary, and the programming language that he or she has been assigned to work with. First of all, we know that the programming language is an attribute exclusive for programmers. So we can define it directly like this. But if we need to add the full name and the salary of the programmer, we can just call the constructor of the employee class. And that will reduce the code repetition. We can reuse the code that we already wrote. How can we do this? We write the name of the superclass, employee, right here. And then we call init. First, remember that we have to pass self right here, because this will be the instance of programmer that we are creating. And then we just pass the full name and the salary. These parameters, and we pass them as arguments to the init method right here. The values will be assigned to these parameters, and they will be assigned to the corresponding instance attributes. Great, so now we have our two classes defined and we've made our hierarchy. We have an employee and we have a programmer who is an employee. For employees, we are defining full name and salary, and for programmers, we also have programming language. Let's create an instance, Nora. Nora will be an instance of programmer. The full name will be, for example, Nora Nav. The salary will be $60,000. We're going to represent this as the yearly salary, and we will assign Python as the programming language. Awesome, we've created a programmer instance. So let's check that this instance actually has the instance attributes that we defined. We will print the value of Nora's full name. We will also print Nora's salary. These are attributes defined in the employee class, in the superclass. And then we will check Nora's programming language. If we save the file and we run the code, we can see the output. Nora Nav is the full name. Salary is $60,000 like we defined right here, and programming language is Python. So we are getting all the attributes of the employee class when we create a programmer instance. Notice that right here we're creating a programmer instance, and we are still getting all the attributes of an employee. And that is the magic of using inheritance in Python. We can reuse code and avoid code repetition. We also make the program more concise and readable. Great work so far. When you're ready, go to our next example. Welcome to our second example of inheritance. In this example, we are going to create a character class, a player class, and an enemy class. Player and enemy will be types of characters in the game. So they will be child classes, and character will be the parent class. So let's start by defining the character class. We're just assigning this name as a general way to refer to a character in the video game. What does a character usually have? Well, it has an X and a Y coordinate to know where to position the image on the screen. And it also has a life counter or number of lives. Okay? So we're going to define these instance attributes right here, number of lives, and we have our init method for character. That completes our class. We're going to keep things as simple as possible to focus on inheritance. So let's start defining our player class. Player is a character, so it has to inherit from the character class. We write the name of the class, of the superclass, or the parent class within parentheses. So let's start defining the init method. What do we need to know for the player in addition to the initial X and Y coordinates and the number of lives? Well, we might want to keep track of the score of a particular player in the game. So we will add this as a parameter, score, and initially we'll have by default a value of 0. We can customize this when we create a player instance, but by default it will be 0. Let's assign the score as an instance attribute, because this is an attribute that is not defined in the character class. It is special or additional for the player class and to create those instances. We also need to have the X, Y, and number of lives attribute. So we have to call the init method of the superclass, like you learned. We write the name of the superclass followed by a dot, and then we call init. The first argument has to be self, and then we pass the necessary arguments. In this case, they are X, Y, and number of lives. But we want all players to start at a particular location on screen. And we also want all players to have the same initial number of lives. So we can define them as class constants. We can say initial X is 0 and initial Y is 0. The player will be initially located at the point 0, 0. And we can also say initial number of lives. Let's say that it will be 10. So we can pass those values as arguments. We take the initial value of X, we also take the initial value of Y, and we access the initial number of lives. Okay? Awesome! Now we can inherit all the attributes from the character class, and we are customizing them with the initial values for the players. So we have our player class. Let's start defining our enemy class. Just like player, enemy inherits from the character class. So we have to write this within parentheses. And we will define the init method for the enemy. In this case, we want to be able to customize the initial coordinates of the enemy, but we will provide some default values. X and Y will be 15 by default, but we can have the option to customize them. We will also have an initial number of lives equal to 8. And we will add another attribute if the enemy is poisonous. By default, this will be false. The enemy will not be poisonous, but if we want to customize this, we can by passing the value true. Let's define this attribute for the instance, and then let's call the init method of the character class like this. Self, X, Y, and number of lives. We are passing the arguments that init requires for the character class. X, Y, and number of lives. X, Y, and number of lives for the character class. These values will be assigned to their corresponding parameters, and then they will be assigned as instance attributes to the instance attributes of the enemy instance. This way, we are reusing code and avoiding code repetition. So we have a much more concise, readable, and better structured code and design. Let's test this and see how the hierarchy is implemented when we start creating instances. First, we will create a player instance. In the player class, we define the init method to only take score as an argument optionally. If we don't want to customize the score, it will be 0. So we can just write an empty pair of parentheses to use the default values. We can print all the attributes of player to check that it indeed has those attributes. We have the score, we have X, we have Y, and we have the number of lives attribute, like this. We save the file, we run the code, and we see this as the output. The initial score is 0, which is the default argument that we assigned right here. The initial X and initial Y are 0, and the initial number of lives is 10, which is exactly what we expected for a player. Awesome! We've inherited all the attributes from the character class. Now let's see how we can create an enemy. We will create 2 types of enemies to show you how this can be really versatile, and it can really help us make our code more concise and yet easy to use and easy to customize. We're going to create an enemy instance. We have to specify these arguments, but they also have default arguments in case we decide to omit them. We're going to create an enemy, and in this case, we're only going to customize the number of lives of the enemy. Since this is an easy enemy, let's say that it only has 1 life, so it's very easy for the enemy to run out of lives in the game. The other parameters will have their default value. And right here, we're going to create a hard enemy or a difficult enemy, a complicated enemy, because it will have 56 lives. And it will be poisonous. We will pass a value for this parameter to customize it. Instead of false, it will be true. So we have 2 different enemies that we've created and customized thanks to how we defined our init method right here in the enemy class. And we're also using the code that we wrote in the character class to define all of these attributes. So now let's print the attributes of each one of the enemies. We're going to print if they are poisonous, easy enemy, the X coordinate, the Y coordinate, and the number of lives. Awesome! Let's print this and see their output. First, we're going to comment this out, so we only see this output. We see this? Easy enemy is not poisonous, because this is false. The initial X and Y coordinates are 15, which are the default values that we defined right here, and the number of lives is 1. It only has 1 life, which is what we defined right here. We customized the value of the argument. Great, so now we replace this easy enemy by hard enemy, and then we run the code. The only changes are the values that we customized. For example, true, right here, because this enemy is poisonous. Then we see 15 for X and Y, which is the same. And then we see 56 for the number of lives, which we customized right here. Notice the power of inheritance. With just a few lines of code, we are writing all of this logic and hierarchy, and we are reusing this code. Imagine how beneficial this will be when we start writing more complex classes and we start to set up the inheritance and the hierarchy. Now you know how to work with inheritance in Python, how to make your classes inherit attributes from other classes. Welcome to this section. Now you know how to inherit attributes from a class. So let's see how you can make your child class inherit methods from the parent class, so you can reuse the existing functionality. This way, you can define common functionality in the superclass, and subclasses will have access to these methods. The instances of the subclasses of the child classes will have access to these methods. They will be able to call the methods defined in their superclass. For example, let's say that we have this hierarchy with a polygon class and a triangle class and a square class. These 2 classes have some methods in common. For example, we might want to print their sides. And we may also want to find their perimeter, the sum of the length of all their sides. These are common operations in both of these classes that can be implemented and work for any polygon that we create. So to avoid code repetition, we can just define this method in the superclass in Polygon and make the child classes inherit these methods or functionality automatically. This is part of the magic of inheritance in object-oriented programming. Instead of writing these two methods in these two classes, we are writing them only once in the superclass and they can be reused. We can also add unique functionality to the child classes. For example, both classes will need to have their very own find area method. Why? Because their implementation will be different. The formula to find the area of a triangle is different from the formula that we use to find the area of a square. For now, let's focus on the common functionality in the superclass. For example, let's say that we have method A and method B. Objects of the class Polygon will have access to this method. They will be able to call the method in the program, and the objects that we create from the child classes will also be able to call these methods, regardless of whether they are triangles, squares, or polygons themselves. All the members of the hierarchy will be able to call these methods defined in the superclass. This is basically what will happen behind the scenes. For example, if we have a triangle object, an instance that we created, and this object is calling a method from the polygon class. Let's say that this method is defined in the polygon class. First, Python will try to find that method with that name in the triangle class, the direct data type of the instance, triangle. But since it will not find a method in this class, it will go up the hierarchy, like this. And it will find the method in the parent class, which is Polygon. And that method will be executed or called. If the method is not defined in any one of these classes, in any of the classes in the hierarchy, then an error will be thrown. And we will see the error when we run the code. Here we have some examples of classes that have common functionality that we can define in their superclass. A savings account and a checking account have common methods, such as, for example, making a deposit or withdrawing money. So this functionality can be easily represented or defined in a more general class called bank account. And they can inherit all of this functionality. We avoid writing that code twice or as many times as we need to in different classes. We just have one unique bank account class with all of that functionality defined. Another example would be a teacher. We would have, for example, a science teacher class and a sports teacher class. They are both teachers, so they will have some common functionality that we can define in the teacher class. So all of those common methods will be defined in this more general class, and these two classes, the child classes, will inherit that functionality. Awesome! Try to think about possible examples of this. Classes with common functionality. Analyzing the objects and determining these hierarchies is the first step before we actually start to write the code. So it's very important that you practice this. Now you will learn how to make your class inherit a method or methods from another class through method inheritance. You will learn the syntax and how you can do this in Python. So let's begin. Just by writing this that we already wrote in a previous lecture, in the class header, you will be making your class inherit the methods of the superclass. Yes, that's right. Just by adding this, the name of the superclass within parentheses after the name of the subclass, you are doing exactly that. There are some details that we will discuss during this section of how you can work with method inheritance. But this is the basic syntax of how you can start implementing it. Let's see an example. This time, we will apply these principles to our polygon, triangle, and square classes. We will define the hierarchy that we had previously. Let's do this real quick. We have a polygon class, and in our init method, now we have our polygon class, and then we have to define our triangle class. This class will inherit from polygon. We say number of sides is 3, And then we define the init method, base, height, and color. We're going to define these instance attributes, base and height, because they are unique for the triangle class. And then right here, we are going to inherit the attributes from Polygon. Great, we have our triangle class now, and we just have to define our square class, which will inherit from Polygon. We also defined the number of sides constant and the init method. In this case, for the square, we will take the length of the side length, and we are going to define this right here, side length, and Polygon, init, square the number of sides to get the number of sides and the color. These are the arguments of the init method of Polygon that we are calling right here to get those attributes and right here to get those attributes. Okay, so now let's start setting up our method inheritance. Just by writing this within parentheses, we're already inheriting the attributes of Polygon to these child classes. So in this case, Polygon doesn't actually have an additional method besides init. So let's add one. Let's define one. We're going to add a method that is going to describe the polygon. Okay, what are we going to print? We're going to print a descriptive message that will say something like this. This polygon has, let's indicate the number of sides of the polygon, 3 sides, for example. And it's, for example, blue, green, or yellow, the color of the polygon. And that will be the message printed when we call describe polygon. This method will be inherited by triangle and by square. They will both be able to call this method. If we create an instance of triangle or an instance of square, they will be able to call describe polygon. Let's check this so you can see how it works. We're going to create an instance of triangle. Triangles require a base, a height, and a color. 5, 4, and blue right here. Okay? Now let's see if this triangle instance can call the describe polygon method. And we do see this in the list of methods for this instance. And we see that this comes from the Polygon class, like this. We will also create a square instance. So you can see that this is actually working as we intended. Blue, green, and we call the method describe polygon from the square instance and from the triangle instance. So let's save the file and run our code. And right here we see this as the output. This polygon has 3 sides and it's blue. This polygon has 4 sides and it's green. So we see exactly what we expected. These instances of triangle and square, the subclasses, triangle and square, the subclasses, inherited this method from Polygon. We didn't define this method in neither one of the classes, and yet their instances were still able to call that method in the program. Awesome, right? You can inherit methods from Polygon, and you can also add new functionality to the class. For example, we will need to define a separate find area method for each one of the polygons, for the triangle and for the square, because their formulas are not the same. For the triangle, we have base times height divided by 2. We will return that value. And then for the square, we will define this method as well, find area. This time we will have to take the length of the side and square it. Now each one of them will be able to call their own methods as well, find area. And they will get the result that we expect because they will call their own unique find area method defined in their corresponding class. We need to add print statements right here so we can see the area because we are returning the value. Let's save the file and run the code. And we see this right here. The polygon has 3 sides and it's blue. We are describing the polygon. And right here we are finding the area, which is 10. And this is correct because 5 times 4 is 20 divided by 2, that is 10. And then we have the square. This polygon has 4 sides and it's green. And the area of the polygon is 16, 4 squared. And that is correct. Awesome, so now you know how to make your classes inherit the methods of the superclass. This is done almost automatically when you write this within parentheses next to the name of the subclass. You will have to do this in all the subclasses to inherit the methods. Great work so far during the course. Now you know how to implement method inheritance. Now let's see something very interesting that can happen when you inherit methods from another class and you also define new methods in your child class. This is something called method overriding, and it will be very helpful, I promise you. According to Merriam-Webster Online Dictionary, to override something means to prevail over that thing, to neutralize the action of, or to extend or pass over another thing. This is actually quite similar to our concept of overriding in programming. In programming, method overriding is something that we use to customize or extend the functionality of a method that is already defined in the superclass. We take the original method in the superclass, and in the subclass, we are going to customize its functionality or extend it. So we can make the instances of our subclasses have additional functionality compared to the superclass. You will see what I mean in just a moment. For example, if we have a method defined in the superclass, and in the subclass, right here we have the superclass and the subclass, and we see the methods, and they both have the same name. Notice right here, they both need to have the same name. This is very important. They must have the same name for method overriding to occur. And then we try to call the method from an instance of the subclass. Let's say that this is an instance of this subclass or child class that we have right here. Then the method of the subclass will be called. This method right here, which could be implemented differently from the method in the superclass. Remember that they both have the same name. This is key. The method of the superclass will not be called. Python will go through the hierarchy, starting from the direct type of the object, which is the subclass, and if the method is found there with the same name that we wrote, it is executed, without even going to the superclass. So this method will not be called if there is another method defined with the same name in the subclass. In formal terminology, we say that this method overrides the method from the superclass, and the method from the superclass is overridden by the method in the subclass. It's sort of like hidden. This method right here hides the method from the superclass, so the instances of the subclass do not have direct access to that method. For example, let's say that we want to define a teacher class with one subclass called science teacher. The teacher class will have a particular way to greet the students for the class, and the science teacher class will have its own way to greet the students to the class. We will use print statements. Try to implement this in your code. You have to define two methods, one in the superclass and one in the subclass. This is the hierarchy that you need to implement. We have the teacher class and the science teacher class. They will both have a method with the same name, and that method will be implemented differently in both classes. Try to do this for a few minutes. Then pause the video and then come back. Let's start by defining the teacher class. We will define an init method with only two instance attributes to focus on the inheritance: full name and teacher ID. Okay, so full name as an instance attribute and teacher ID as another instance attribute. Awesome, we have the attributes, so let's define science teacher right here will inherit the attributes and methods of the teacher class. Like this. In this case, in this class, we are not going to define an init method. We will use the superclass's init method because we just want to assign a full name and a teacher ID to our science teacher. Okay, for now, we're going to fill the body of this class with a pass statement so we can define the methods right here in the teacher class. We will have a method called welcome students. This method will have a print statement that will welcome the students to class. For example, we will print, welcome to class. I'm your teacher, My name is, and right here we write the full name. We will replace this value right here. That is why we are using an F string, so we can replace the value of this variable right here within curly brackets. Awesome, we have our method implemented. So now let's say that we want our science teacher to welcome the students differently. We want to print different messages if the science teacher is the one welcoming the students. What can we do? Well, we can define a method with the same name, welcome students. And this will be an example of method overriding. If we call this method with an instance of science teacher, this method will be called, not the method from the superclass. Let's see how this works. Science is amazing. Of course, the instance is a science teacher, so we say welcome to class. I'm your teacher, and we will replace the full name. Right here, you can see that the messages are different. So the implementation of this method is different from the implementation of this method in the superclass. Let's see how this works by creating a science teacher instance. Science teacher, and we have to specify the full name, Emily Smith. And the teacher ID will be just a combination of numbers and letters, like this. We have the instance, so now we can call our welcome students method. Right here. Since this method is defined in the subclass in the direct class of the instance, which is science teacher, this method will be called. Let's save the file and run the code to see that this works as we expected. Right here we see, science is amazing, welcome to class, I'm your teacher, Emily Smith. We are calling this method right here. Now, let's say that we don't have this method implemented in our class. Like this. Let's just comment this out and fill the body of the class with a pass statement. Now let's call welcome students. We see this message right here. So we're calling welcome students from the teacher class. Welcome to class, I'm your teacher, my name is Emily Smith. We are calling this method because we don't have a method defined in this class. Remember that we commented out to test this. But when we do define a method in the subclass, we call the method from that class. If we are calling it from an instance of the subclass, we're sort of like going up the hierarchy. If the method is found directly in that class, it is called. If not, Python goes up the hierarchy until it finds it, and if it doesn't find it, then an error is thrown. And what happens with the method in the superclass? Have we left that method already? Is it no longer accessible by the instances of the subclass? Well, not necessarily. There is a way to call the method from the superclass in the subclass. And that is by using this syntax. We will see it in detail in just a second. We basically write the name of the superclass followed by a dot, then the name of the method and self as an argument, and any arguments that it requires. This is a way to use the code that we wrote in the superclass, the code that we wrote for this method, and extend it or customize its functionality, because we'll be calling the method right here, and we can add code before or after that method call, like this. This is the basic syntax. We write the name of the superclass followed by a dot, then the name of the method, and within parentheses now we do have to pass the value self, because we have to specify the instance of the subclass that we are working with. And we also pass any arguments that the method requires. Let's implement this in the teacher and science teacher classes. We will call the method from the superclass, and we will extend it in science teacher. Let's go to our code. We can call this method from the superclass, in the method defined in the subclass. So we can reuse this functionality. For example, let's say that we want to print this instead of this line of code. How can we do that? Well, we just write the name of the superclass, teacher, the name that we wrote right here within parentheses, and then we call the method welcome students. This time we do have to pass the value of self, because this is the same value that we will get as an argument, the instance that is calling the method. This is essential because we will also need to know which instance is calling the method to replace its full name. And since this method doesn't take any other arguments, we can just pass self as the only argument. Now let's run the code and see what we get as the output. Science is amazing. Right here, this is the line that we added in the subclass in this method. And then we see this line. Welcome to class, I'm your teacher, my name is Emily Smith. This is the line of code that we wrote in the implementation of this method in the superclass. So we're actually calling this method right here. We're calling the method from the superclass and we are getting the output that we expected. And notice how we're customizing the value of self.fullname with the full name of the instance that called the method. In this case, Emily Smith. There is also another alternative syntax that we can use, where instead of writing the name of the superclass, we write super right here. This will have exactly the same effect. It will call the method from the superclass. The effect will be exactly the same. This is the basic syntax. First, we write super with empty parentheses, an empty pair of parentheses. Then we write a dot, the name of the method, and finally, within parentheses, any arguments that the method requires. And this will work exactly the same. We will do this in our teacher and science teacher classes. We just need to make this small modification, replacing the name of the superclass teacher with super. Okay? Try to do this for a second, pause the video, try to make this small modification, and then come back so we can start working on this code. In this case, we just need to make this small modification. Replace the name teacher right here with super and empty parentheses. In this case, we don't have to pass self as an argument if we use super. Super, empty parentheses, a dot, the name of the method, and finally, parentheses. If the method takes any arguments, we would pass the arguments right here. If we save the file and we run the code, we see that we get the same output. The functionality is exactly the same, but now we are using super instead of the name of the class. Great work! Now you know what method overriding is, how you can identify it, how you can implement it, and how to use the alternative syntax with super. When you're ready, go to the next video, and I will see you there. Welcome to this practical example of method overriding. In this case, we're going to work with our backpack class, the class that we have been working with during the course. Let's define our backpack class. Now we're going to define a hierarchy, because we will have the general class backpack, and we will also have a subclass called school backpack. Let's see what changes we will implement in the subclass. We said that a backpack has an initially empty list of items. For now, remember that we are making the attributes public because we want to keep our classes as simple as possible to focus on inheritance. But you already know how to make these attributes non-public and how to add properties, in case you need to. After we have that initial definition, we will define the school backpack class. This class will inherit from backpack, so it will have the attribute items. We will use the init method of the superclass. We will not define an init method in our subclass, in our child class. Okay? What we will do is define a method called add_snack. Okay, this will be a really cool method that adds a particular snack that we specify to the list of items. In the general backpack class, we will print this message, adding a snack to this backpack. So we can tell the user what we're doing. We're going to append the snack to the list of items. And then what are we going to do? We are going to print a confirmation message. We're going to print the snack right here, capitalized, with the first letter in uppercase. And then we say that snack was added to the backpack successfully. Awesome! We have those messages and we have the functionality implemented. Now let's say that we want to override this method in our school backpack class. We want to change or customize the messages that we display. So how can we do that? We just write a method with the same name, and we also need to take the snack as argument. What are we going to print now? Since this is a school backpack, we're going to say it's time to go to school. Let's add a snack. Since the functionality is very similar and we just wanted to add a custom message right here before we start printing these messages, then we can call the method from the superclass, from the backpack class. We write the name of the superclass backpack, then add snack, and then we pass self and snack as arguments. This will run this code that we have right here. And then we are going to print the list of items for the user. We say, now your backpack has these items. And we print the list of items. As you can see, with method overriding, we're able to use the code that we wrote in our backpack class, these 3 lines of code, and still extend the functionality of the add snack method, because we are printing 2 additional messages that we didn't have in our backpack class. Awesome, so let's test this by creating a backpack instance. But in this case, it will be a school backpack instance. We're going to create an instance of the subclass right here. And what are we going to do? Well, we are going to add a snack. And what snack are we going to add? Well, a candy. If we save the file and we run the code, we see this right here. It's time to go to school. Let's add a snack. This is the first line that we have right here. Adding a snack to the backpack is a line that we have right here in the method definition in the superclass. Why? Because right here we are calling the method from the superclass. We will have these 3 lines. Adding a snack to the backpack, then we are going to append it to the list. Candy was added to the backpack successfully. And then we go back to this method and we see now your backpack has these items. And we see a list with the items in the school backpack. This is another example of how you can use method overriding to extend the functionality of your methods. Right here, we are reusing the code. We only wrote it once, and we can call it in our subclasses to avoid code repetition. And still, we can extend their functionality, or we can even replace their functionality entirely. We just need to write a method with the same name in the subclass, and that will automatically result in method overriding. Awesome work! Now you've worked on several examples and you know how method inheritance works, how you can implement it in Python, and how method overriding works. Great work so far during the course! Welcome to this section. Now you will learn about a very helpful tool to work in Python, import statements. An import statement is a type of statement that we use to get access to the code that we wrote or find in another module. Code that was written in another Python file and that we want to use in our current file. Let's see why we need to use this type of statement. When we start working on our project, we typically start writing classes, functions, variables, and code in general with several different elements. But as the program grows in size and complexity, it becomes harder and harder to find the elements in our code. And organization is always key to develop maintainable programs. Imagine having to find a line of code in millions of lines of code. So what can we do about this? How can we improve the organization of our project? What we can do is split our code into multiple Python files and combine them. For that, we can use import statements. With an import statement, we can get access to the code in a file when we are working in another file. We keep the code separate, but we can still combine it to make the program that we need. This way, we can select the elements that we actually need to import to our program and keep our code organized. Let's see what we can learn about this type of statement in the documentation. In the documentation, we can go to the article, The Import System. This article explains in detail how import statements work. Let's read the first paragraph. Python code in one module gains access to the code in another module by the process of importing it. The import statement is the most common way of invoking the import machinery. The import statement combines 2 operations. It searches for the named module, and then it binds the result of the search to a name in the local scope. Then right here you can see more details about how import statements work and other elements of the import system in Python. For now, we will focus on import statements and how they work. If we go to PEP8, the style guide for Python code, we can also click right here where it says imports, and we will see the guidelines for writing import statements in Python. Imports should usually be on separate lines. So if you're going to import more than one module, you should do it on separate lines, one per line. You can always go back to the style guide as you need to. It's called PEP8, and you go to the section on imports. Inputs are always put at the top of the file, just after any module comments and docstrings, and before module globals and constants. Imports should be grouped in the following order: standard library imports, related third-party imports, and local application or library-specific imports. You should put a blank line between each group of imports. When importing a class from a class-containing module, it is usually okay to spell this: from my class, import my class. This is the name of the module of the Python file, and this is the name of the class. And if the class is at a different location, then you can specify the path to that location and import that specific class. And right here we have some recommendations for wildcard imports, which you will learn in detail in a lecture in this section. We also have some guidelines for package and module names. When we create modules, modules should have short, all lowercase names. Underscores can be used in the module name if it improves readability. The main advantages of dividing our programs into modules and then importing them with import statements are improving the project and code organization, grouping related classes, functions, and constants, reusing the code that we already wrote in the modules, and choosing which elements to import to the main program. We can choose the elements if we need to. We don't need to import all the elements of a module. Think about this for a moment. Have you ever wanted or needed to divide your project or program into multiple files? Let's see how you can write an import statement in Python. There are several alternatives depending on what you need to import. So the structure and the syntax of the statement will vary, and we will cover some variations that will be very helpful as you work with your Python programs. First, you need to remember that import statements should be the first statements in a Python module. This is very important. They are usually located at the very top of the file, if the program has any import statements. This is the most basic import statement that you can find. This type of import statement is used to import all the elements of the module that we specify: classes, functions, constants, and any other elements in the module. Notice the syntax. We write import, the import keyword, followed by a space, and then the name of the module that we want to import. This would be the name of our file or the path to our file, or it would also be the name of a built-in module, because Python also has several built-in modules that are installed automatically when you install Python. If we need to access an element from this imported module, then we will need to write the name of the module, followed by a dot, and then the name of the element. This is very important because we have to specify where the element is coming from, and this is also helpful to make your code more readable. Anyone who reads your code will know exactly where that element came from. Think about how you would write the import statement that is used to import the math module and access the pi constant. Try to write this in your code based on the syntax that you just learned. Pause the video and then come back. Welcome back. Right here we have the import statement and how we can access the pi constant. Import math at the very top of the file, and then when we need to use pi, we just write math, the name of the module, followed by a dot, and then the element, which is pi. Let's see this in our code. In our program, we can import the math module like this. We write import, followed by the name of the module. Right here, it is turning gray because we haven't used it so far in the program. So PyCharm is warning us that this module is not being used. But don't worry, we will use it in just a moment. we will define a circle class. This will be very simple, just to illustrate how to work with import statements. And our circle will have a radius. We will define a method findArea for the circle. And what do we need to know to find the area of the circle? We need to know the radius of the circle, and we also need the value of the constant pi. That is why we are importing the math module right here. To access or to work with the pi constant, we need to write something like this. The name of the module, which is math, followed by a dot, and then the name of the element. In this case, it's pi. So the formula is pi times the radius squared. And that is the basic formula to find the area of a circle. And you can see how helpful the import statement was. We have access to a constant that we wouldn't have access to if we didn't use the import statement. Now think about how you can call the randint function, which is a function from the random module, with this type of import statement. Think about this, pause the video, and then come back. Welcome back. To write this import statement, we would write import random, and then to call the function randint, we would use this syntax. The name of the module, followed by a dot, the name of the function, and then any arguments that the function requires. In this case, we have to specify the valid range of integers that we can use to generate the random integer. Great, so let's start writing our die class. We will write a die class that will have a roll die method. This method will assign a random value from 1 to 6 to the die that we are rolling. Okay? For that, we will need to import the random module. This is a module that contains functions that are very helpful to generate and work with random numbers and also to shuffle sequences. So we will use that in our code. Class die. The main characteristic of a die is its value. After we roll the die, the value at the very top of the die, the top face. So that is what we will assign as the value of the die. So we will say roll die. Rolling a die means changing the value of the die and selecting a random value from 1 to 6. So that is what we will do. We will generate a random value, and then we will assign that random value to the value of the die. The random value has to be between 1 and 6. So how can we do this? We just mentioned or write the random module, and we will need to call the randint function. This generates a random integer between a and b inclusive. So we need to specify the numbers 1 and 6 right here. It is recommended, according to the style guide, to have 2 blank lines between an import statement and any other elements in your program. So this is why PyCharm was warning us right here with a green line. It says, PEP8 expected 2 blank lines and only found 1. So this is another guideline that you should remember when you work with import statements. Great, so let's create a die instance. We say my die, and initially the value of the die will be, let's say, 4. We are setting this up in a way that we can specify the initial value of the die. We can also roll the die when we create it. That is another alternative. And we say my die, roll die. We're going to print the initial value of the die, and then we are going to roll the die and print the value again to see the change. If we save the file and we run the code, we see that the value of the die changed from 4 to 3. 3 was the random value generated right here with the randint function from the random module. So you can see how helpful it is to import modules, particularly the built-in modules are very helpful. If we run the code again, you can see that this is actually random. We get a different number each time we run the program. We got 4, then we got 2 again, then we got 1, so this is actually working as we expected. Great, so now you know how to work with this particular type of import statement, where we write import and the name of the module. You need to write the name of the module followed by a dot and then the name of the element that you want to use. If it's a function, We will call the function passing the arguments that the function requires. Now let's see another type of import statement that you can use. We can use this type of import statement to import only a specific element of the module that we specify. Previously, when we used import followed by the name of the module, we were importing all the elements of the module. But sometimes we only need to import a specific element of the module. So we can use this new syntax, this one right here. We write the keyword from, followed by the name of the module, the keyword import, and then the name of the element that we want to import. We're saying, from this module, import this element. To access the element in our code, previously we had to specify the name of the module, but now we can write just the name directly. A small tip is that this type of import statement can make the code more difficult to read and understand, since the module is not specified explicitly when you access the elements of the module, when you use the constants, when you call the functions. So we might take a little bit longer to detect visually where the elements are coming from. This is an example. We say from math, import pi. This is the name of the module, and this is the name of the element that we want to import. In this case, it is a constant. Now we can use pi directly in our code. Think about how we can use pi in the circle class that we defined, in the findArea method. Pause the video, try to implement this by modifying our circle class, and then come back. Use this new syntax for the import statement and modify how pi is accessed in our code. Here we have the example that we wrote in the previous video, where you learned this type of import statement. So let's refactor or change our code to use this new type of import statement. We write from math, import pi. We're saying, from this module, import this element. And how can we refer to this element now in our code? Well, we see an error because right here, we don't have to specify the name of the module explicitly. We just need to write the name of the element directly in our code, right here. We can do exactly the same with the random module to import randint. This is a function this time, it's not a constant, but you can refer to any element of the module right here. In this case, we can call the function directly without having to specify the name of the module. We just write randint and pass the necessary arguments. As a quick challenge, try to modify our previous example of a die where we use randint and use this new type of import statement. Pause the video, make the modifications, and then come back. This is our example with the die class. Previously, we were importing random with this import statement. So let's change this. From random, import randint. Okay? So now we have to use the name of the function directly, right here with the name of the module. We just call this function like we would call any other function in our code, passing the necessary arguments. So if we save the file and we run our code, we can see that the code still works exactly the same. We get the initial value of the die and we roll the die to get a new random value. This is another alternative syntax that you can use to import specific elements from a module. Now let's see a type of import statement that is typically called a wildcard import statement. This is the basic syntax of a wildcard import statement. We have from, the from keyword, then the name of the module, and then the keyword import, and finally we have right here an asterisk. With this asterisk, we are basically telling Python, hey, import everything that you have in the module directly, so I can access it without having to specify this name. Let's see what we can learn about this type of import statement in the Python documentation. If we go to PEP 8, the style guide for Python code, and we click right here where it says imports, if we scroll down a little bit, we will see this paragraph. Wildcard imports with the form from the module import, basically everything because we have the asterisk, This type of import, wildcard imports, should be avoided, as they make it unclear which names are present in the namespace, confusing both readers and many automated tools. So in most cases, you should avoid using this type of import. It confuses both readers and automated tools. The documentation also mentions one defensible use case for this type of import, but this is very specialized and it's not something that you will commonly do in Python. Right here we have an example of a wildcard import. From math, import basically everything. When we write the asterisk right here, we are saying import everything that you have in this module. So we can refer to those elements directly. If we write pi right here, you can see that we don't get any errors, and the import statement is sort of like active now, instead of gray, because we are using an element that was imported from the math module. And notice that we don't have to specify where the element came from. We don't have to add math right here. If we run the code, we see the value for this constant, defined in the math module. We can also call functions like, for example, sine or cosine. And we can see these values right here. These functions would not be defined if we didn't have this import statement. You can see that if we remove this, we just see unresolved reference for each one of these elements. They were imported from the math module. But try to imagine doing this in a complex program, using all of these elements without specifying where they came from. This can quickly become very difficult to maintain, because when we see this in our code, we might not be completely certain of where this came from, of the module that this came from. This is why wildcard import statements are usually not recommended, because they can make your code more difficult to read and maintain. Welcome to this section. Now we will cover docstrings in Python. The name docstrings comes from two words, documentation and strings. Docstrings are basically string literals that we can use to document our code. And what do we mean by document? Well, we're basically describing a particular element of our code using docstrings. Let's see what we can learn about docstrings in the Python documentation. Right here, we're in the Python documentation, and we are particularly at an article called PEP 257, Docstring Conventions. This PEP right here, this acronym, means Python Enhancement Proposal. This is just an article that details the conventions that we have to use to write docstrings and what they are used for. It's very interesting. You can go to this article and click right here on what is a docstring. Let's see what it says. A docstring is a string literal that occurs as the first statement in a module, a function, a class, or a method definition. Such a docstring becomes the doc special attribute on that object. Okay, we will talk about this in a video during this section. Docstrings are connected to the element they describe with this special attribute. All modules should normally have docstrings, and all functions and classes exported by a module should also have docstrings. Public methods, including the init constructor, should also have docstrings. The conventions also recommend that for consistency, we should always use triple double quotes around docstrings. And it also mentions that we should use raw triple double quotes if you use any backslashes in your docstrings. For Unicode docstrings, you should add a U before the triple double quotes, okay? This is just the basic syntax of a docstring. An overview, we will go through the syntax again in a video during this section. There are two forms of docstrings, one-liners and multi-line docstrings. So based on what we just read, docstrings are human-readable comments that explain the purpose and the logic of a particular element of our code. For example, a function, a module, a class, or a method. They work sort of like a manual that anyone who wants to use that element can read and learn how to use it. They describe the purpose and the logic of the element, what the user has to know to be able to interact with that element and use it in the code. In the case of functions and methods, they also describe their arguments. A brief description of each one of them is usually included and their data types. so the user can know what data types are expected to call the function or the method. The return value can also be described, and this description can also contain relevant information. For example, valid range of values that you can pass as the arguments, and any exceptions that might be raised if you pass an invalid value to the method or the function. These are some key takeaways from what we read. Docstrings are the first statement in a class, a method, a module, or a function. And they should be included in all public methods of a class, including init, where we initialize the instance attributes. So now let's see the difference between docstrings and comments, because they actually start to sound very familiar, right? Well, one of the main differences between docstrings and comments is that docstrings are linked to the element that they describe. We will see an example of this during the section. And comments are not linked to any part of the code. Actually, they are removed behind the scenes and they are not considered part of the code when the program runs. Another key difference is that docstrings can be used to generate documentation automatically using certain tools. But comments, they cannot be used to generate documentation automatically. They are not actually considered part of the code and they cannot be detected by any automatic tool to generate documentation. And finally, docstrings can be read with the help function in the interactive shell, and basically when you write a program in Python, you can learn more about an element by using the help function, but in comments you can only read them directly in the source code. You have to open the file and go to the specific line of the comment. These are the main differences between docstrings and comments, so you can see that they are actually quite different. There are also two types of docstrings that you have to be aware of. We have one-line docstrings and multi-line docstrings, depending on the level of detail and description that you want to add to your documentation. We will see both of them in detail during this section, and you will learn how to write them and what type of information to include. Awesome! Take a moment to analyze why docstrings are important. Have you ever seen a method or a function and wondered how it works, and wish that you had something that would just explain that to you in plain language instead of having to analyze the code line by line? Well, that is what docstrings are for. So by the end of this section, you will be able to write that documentation for you and for other developers. Now let's see how you can write docstrings in Python. There are two types of docstrings: one-line docstrings and multi-line docstrings, depending on the level of detail that you want to add to your documentation. One-line docstrings are typically used to document very simple methods and functions. Let's see what we can find in the documentation about this type of docstring. If we go to PEP 257 docstring conventions, we can go right here to the table of contents and click on one-line docstrings. We will go immediately to this part of the article, where it says, one-liners are for really obvious cases, okay? They should really fit on one line. So that is why we use them for really obvious cases. For example, right here we can see a function. Notice this right here. This is the one-line docstring. Let's read the notes. We can see that triple double quotes are used even though the string fits on one line. This makes it easy to later expand it, okay? The closing quotes are on the same line as the opening quotes. You can see this right here. On the same line. This looks better for one-liners. There is no blank line either before or after the docstring. Right here we have the docstring, we have the function header, and right here below we have the body. So we don't see any blank lines before or after the docstring. The docstring is a phrase that ends in a period. Right here we have the period. It's very important to include it if you want to follow the Python style guide. The description prescribes the function or method's effect as a command. Okay, this is recommended by the Python style guide. For example, do this, return that. It should not be written as a description according to this particular guide. It says don't write returns the path name. Write instead return. Not returns, return, like a command. This also says that the one-line docstring should not be a signature that reiterates the function or method parameters, which can be obtained by introspection. So it basically says that we shouldn't write something like this. where you're basically just writing what the user can detect by simply reading the code. We know that it is a function that takes two parameters, a and b. We can see this right here directly. And we might know from the code that the result is a list. So basically, this is not adding any important information for the user of the function, for yourself or the developer who is going to work with this function. The docstring's main purpose is to add important information for the user. Right here we see below, referring to this type of docstring, it says that it is only appropriate for C functions such as built-ins, where introspection is not possible. However, the nature of the return value cannot be determined by introspection, so it should be mentioned, okay? The preferred form for such a docstring would be something like this. Do X, do something, and return a list, okay? Of course, we should replace do X by something that is useful, a useful description, like it says right here. Okay, so these are the basic guidelines for one-line docstrings in the documentation. Right here we have an example of a very simple function that adds two numbers, a and b, and it returns that sum. Let's say that we want to add a docstring. We just click enter after the first line, the function header, and we are going to write triple double quotes, okay? PyCharm automatically adds the closing quotes right here, and in the middle, we just have to add some spaces and start writing our docstring, our description. We might say, for example, return the sum of A and B. We end with a dot, and we don't have any blank spaces right here after the dot. We just write the closing quotes on the same line as the opening quotes. We write a brief description of the function in a user-friendly format, and we indicate what the function does. It returns the sum of A and B. Right here, we have an example of a function that prints Floyd's triangle, a particular pattern with the shape of a triangle where each element is a number, and the number is incremented by 1. To add a docstring, to describe this function, we just need to write triple double quotes, the opening quotes and the closing quotes, and in the middle, we just write the description. We say, print Floyd's triangle with n rows. This is very helpful for the user because we know what the function does and how it will be customized according to the argument that we pass. We are referring to this argument and specifying what this means. This is the number of rows that will be printed by the function for this pattern. We end the line with a dot, and we have the closing quotes on the same line as the opening quotes. Awesome. So these are the key guidelines that you need to follow to write one-line docstrings. Always remember to use triple double quotes. Remember that the closing quotes should always be on the same line as the opening quotes. You should end the line with a period. Write the effect as a command. It is recommended to write the effect as a command. For example, return, add, print. You should also remember to avoid adding a blank line before or after the docstring. The docstring should be immediately after the header and immediately before the body of the function or method or element that you are describing. And you should also remember to mention the return value and describe it. If you think that it will be helpful for a person trying to use that element, then include it in the documentation. Now let's dive into multi-line docstrings. They are used to document more detailed and complex methods, classes, and modules, or even functions, if they needed more detailed documentation. Their basic structure is this one right here. We start with a summary line, which is basically the same as writing a one-line docstring. It should follow most of the same rules. Then it should have a blank line, and after that blank line, a more elaborate description of the element. Let's go to the documentation to see the guidelines and some examples. Right here, if we go to PEP 257 Docstring Conventions, we can go to the part of the article where it says multi-line docstrings. Right here, we click on the table of contents, and that will take us to this part of the article where we can learn more about multi-line docstrings. Multi-line docstrings consist of a summary line, just like a one-line docstring, followed by a blank line, followed by a more elaborate description. The summary line may be used by automatic indexing tools. It is important that it fits on one line and it is separated from the rest of the docstring by a blank line. The summary line may be on the same line as the opening quotes or on the next line. So this is up to you. You can start writing the docstring on the same line as the opening quotes, like we did with one-line docstrings, or you can start writing it on the next line as well. The entire docstring is indented at the same level as the quotes at its first line. You can see the example below right here. We have the opening quotes right here, we have the closing quotes right here, and the content of the docstring, which is this right here, is indented at the same level as the quotes, the opening and closing quotes. Right here we see the guidelines for docstrings for different types of elements. We see to document a class, to document a script, a module, and right here we have what we will be focusing on during this video. Functions are methods. The docstring for a function or a method should summarize its behavior and document its arguments, return values, side effects, exceptions raised, and restrictions on when it can be called. All if applicable, of course. Optional arguments should also be indicated, and it should be documented whether keyword arguments are part of the interface of the method or function. Right here we see what the docstrings for a class should be like. We will learn more about this when we cover docstrings in classes during this section. Okay, so right here we can see this example of a docstring in the documentation. We have a function complex. We can know how the function works and what arguments it takes just by looking at the documentation, the docstrings. We know that it forms a complex number, and it has two keyword arguments, real and imaginary. The real part of the number, which by default is 0.0, and the imaginary part of the number, which by default is 0.0, okay? So this is basically giving us a human-readable description, a user-friendly description of its behavior, arguments, and return value. For methods and functions that require multi-line docstrings, you should document the arguments that they take with a brief description and their data types to indicate the user how that method or function should be called. It should also mention any optional arguments and the return value. It should mention any side effects that the function or method may cause on an argument or on a value if it mutates, for example, a list, and any exceptions that might be raised if the arguments are not valid or if the process fails at some point. That covers most of the important aspects of a method or a function. Right here, let's see how we can write a multi-line docstring for this function, this particular function. We're using functions as examples right here, but this also applies directly to methods, so all of these guidelines apply to methods as well. In this case, this function makes a frequency dictionary. A dictionary that maps each element in the sequence that we pass as argument to its corresponding frequency, how many times that element occurs in the sequence. So we want to write something that will be helpful for the user to understand what this function does without actually having to read the code. Let's do that. Since this is going to be a multi-line docstring, we can write the quotes on different lines. If we write the quotes on different lines right here, then we can start with the initial line. The first line is just like a one-line docstring, where we write a one-line description or summary line of what the function does. It says, return a dictionary that maps each element in sequence to its frequency. Okay? We have to end this line with a dot, like we're doing right here. After that, we have to add a blank line, and then we can start writing the more detailed description of the function. Let's add more details. Create a dictionary that maps each element in the list sequence to the number of times the element occurs in the list. So we're specifying that the sequence is a list right here. We're adding more details. The element will be the key of the key value pair in the dictionary, and its frequency will be the value of the key value pair. We're writing a lot of details right here to help the user understand how the function works without actually reading the code. We can also add a subsection or more than one subsections to guide the user. For example, we can describe the arguments that it takes. Arguments, or argument in this case, says this function just takes one argument. So we say argument and we write sequence. This argument is a list of values, okay? These values have to be of an immutable data type because they will be assigned as keys of the dictionary. As the keys of the dictionary. For example, they can be integers, booleans, tuples, or strings. Great, now we described in detail the type of argument that the function can take. And we also gave some examples of the data types that the function can work with. We described what the function can take as input, and we also have to explain to the user what value will be returned. We might say the return value is a dictionary that maps each element in the list to its frequency. For example, this function call, make frequency dict, passing the list 16262, returns this dictionary. 1 is mapped to the value 1, 6 is mapped to the value 2, and 2 is mapped to the value 2. The user has a better idea of how the function works and how that can be used in the program. We also have to warn the user of any exceptions that the function may raise. In this case, we have an example of raising a value error. We say that the list cannot be empty if the sequence is empty, okay? So this function might raise a value error, and we explain why. If the list is empty. Now we remove these extra blank lines right here, and we have the closing quotes, the closing triple double quotes. Notice how helpful this documentation can be. We have our multi-line docstring right here. It is very detailed and it really helps the user to understand how the function works, what type of arguments it takes, and the return value without actually having to read the code. In this case, we have a small function, but imagine how helpful this will be if the function is more complex and if the code is a little bit more difficult to read or understand. Great, so we covered methods and functions. Now for classes. For classes, we need to include in the documentation what the class represents. We also need to mention any public methods that the class has that we can call from outside of the class, any class and instance variables that are public in the class, and the effects of inheritance on the class. You will learn more about this in the coming lecture, so when you're ready, go to the next video where you will see how you can document classes in Python. Documenting your classes in Python is very important because it can help you and other developers know how to work with and interact with the objects that you create from the class. So let's have a quick tour of the documentation to see what it says about documenting classes. Right here, we are in the Python documentation, in PEP 257 Docstring Conventions. If we go to the table of contents and we right-click on multi-line docstrings, we can see this paragraph right here. The docstring for a class should summarize its behavior and list the public methods and instance variables. If the class is intended to be subclassed and has additional interface for subclasses, then this interface should be listed separately in the docstring. The class constructor should be documented in the docstring for its init method, so the init method should be documented with a docstring. Individual methods should be documented by their own docstring. If a class subclasses another class and its behavior is mostly inherited from that class, its docstring should mention this and summarize the differences. You should use the term override to indicate that a subclass method replaces a superclass method and does not call the superclass method. And use the verb extend to indicate that a subclass method calls the superclass method in addition to its own behavior. So we have two terms for the docstring, override and extend. Okay? So the key takeaways are that the class constructor should be documented in the docstring for its init method. Individual methods should all have their own docstring, particularly public methods. And finally, if a class, subclasses another class, and its behavior is mostly inherited from that class, its docstring should mention this and summarize the differences. Right here we have a backpack class. The class has 3 methods, and it also has the init method. We can see that initially a backpack instance has an empty list of items. We can add an item, remove an item, and check if the backpack contains an item, or if it has an item, okay? So let's start documenting this class to help the user of the class know more about the type of objects that he or she can create and how to interact with the objects. We start by using triple double quotes. We close the docstring with triple double quotes, and we start writing the documentation. Let's see. First, we write a summary line of what the class represents. We can say, for example, a class that represents a backpack. Okay, we end the line with a dot. This is like a summary line for the class. After that, it depends on the style that you're using for the docstring. One alternative could be separating the different parts of the documentation or of the docstring depending on the type of description. Right here we have, for example, a section for the attributes. And we start describing the attributes that will be created for each instance of the backpack class. We say items is of type list, and it represents the list of items in the backpack. This is initially empty. Okay? So now we know that when we create an instance of backpack, we will have this attribute, this public attribute in the class. Now we have to list the methods of the class and provide a short one-line description of each one of them. You can also include the parameters of each of one of these methods so the user can have a better idea of how to call these methods. So let's list the methods. We have add item, and we say add item, self and item, and you may write the description right here on the same line, or you may write it on the next line indented. So we know that this description belongs to this method. Let's say that the purpose of this method is to add the item to the backpack. Okay? Like this. It's just a short description, and the documentation recommends writing the effect as a command, add. Then we have remove item. This method takes self and item as arguments. So we say self and item. Remove the item from the backpack. And finally, we have the third method, has item with self and item, like this. And this method returns true or false based on whether the backpack contains the item. So let's write it like this. We can, for example, write it like this. Return true if the item is in the backpack. Else, return false. This really depends on what you want to write as the description of the method. And the format of the docstring really varies, okay? So you may find these elements in a different format. But this is just one alternative, and I think it really looks nice because we are dividing the content of the docstring into different sections. Notice that we are aligning the titles of the sections with the opening and closing quotes, and that is recommended by the docstring conventions. Awesome, so now we have our multi-line docstring for a class. We have a summary line of what the class represents, we have the attributes, and we have the methods. Right here, we are writing attribute in singular because there is only one attribute, but you would write attributes if you have more than one attribute. There are many different styles to write docstrings. Another important aspect of the documentation is documenting properties in a class. In this case, you should only document the getters of the property and include relevant information from the setters, if applicable, okay? So if a property has a getter and a setter, you will only write a docstring in the getter. And that one docstring should include all the relevant information for both of these methods. Okay, so now we're going to have one more practical example of how we can document a Python class. Right here we have a circle class. We are importing the math module because right here we will be using the pi constant from the module to find the area and the perimeter of the circle. So that is why we are importing this module. We have the class, we have the constructor with two arguments, radius and color. We're going to create these two attributes for the instances. Right here we have properties. The radius, but radius will only have a getter. We don't want to change the radius of the circle, but we do want to provide a setter for the color. We're going to be able to get the color and set the color with a new color right here. We also have another property, the diameter. We are not defining this as an instance attribute right here. We're actually defining it as a property because we are going to take the radius and multiply it by 2, and that will be the diameter right here. Because in case that someday we might want to make the radius variable so we can reassign or change the value of the radius, the diameter will be calculated dynamically with the current value of the radius. We also have the find area method. It finds the area of the circle and the perimeter, 2 pi times the radius. We're going to document this class with the class docstring, and we're going to add docstrings to each one of these methods. So let's get started. First of all, we go to the class header, and on the next line, we write the opening triple double quotes and the closing triple double quotes. The first line should be a summary line, so we can write a class that represents a circle. Okay? We could write this on the same line or on the next line. This is allowed, both cases are allowed by the docstring conventions in Python. Now let's add a category, attributes. And what attributes do we have for each one of the circles that we will create? We have first a radius, which is going to be a float. We're going to define this as a float, and we say it's the distance from the center of the circle to its circumference. Okay, to the circumference. Then we have the color attribute, which is going to be a string. This will be the color of the circle, described with a string, of course. And we also have the diameter, which is going to be a float. This is the distance through the center of the circle from one side to the other. These are all the attributes of the class. This is a property, but we are including this in the section for the attributes. We also have these methods. We have find area right here below. We have find area, and this method only takes self as the argument. We can write self. In some styles, you will see that self is omitted. That depends on the style that you're using and what your team agrees for the documentation. So we say, return the area of the circle. We're using the command. Right here, we're writing this as a command because of the guidelines in the docstring conventions. And we also have find perimeter, self, right here. We say return the perimeter of the circle. And we remove these extra blank lines right here and this extra blank line right here. And we have our class documentation. You could be more descriptive, you could add more details or change the structure of the docstring, but this is just a basic idea of what you can include right here. Now let's go to the init method. We have to document the constructor as well. So let's write our quotes right here, and we say, the purpose of this method is to initialize an instance of the circle class. What are the arguments? Well, we have these arguments right here. We have the radius, which is a float, and we are going to write the same description that we wrote in the class description. The distance from the center of the circle to its circumference. Like this. And we also have the color, which is another argument right here. The color is a string, the color of the circle. We could add more details or even specify a format for the string if that is required. Okay? Now we have our documentation for the init method. So let's start documenting our properties right here. We have radius and we have color. For radius, we will write a simple docstring. We say, return the radius of the circle. And we might want to add a short description of what the radius represents. This is a float that represents the distance from the center of the circle to its circumference. Like this, okay? Now for the color, we can also be more specific right here in the property and specify the format of the string. We say, return the color of the circle represented as a string. And we can say, for example, the color is described by a string that must be capitalized. Let's say that we want the string to be capitalized. So we can give an example. For example, red, blue, green, yellow. And those are our examples. We might remove this since right here we're saying that it's represented by a string, okay? Return the color of the circle, and right here we provide more details for that property. This part of the documentation also applies to the setter of the property because we're specifying what the value should be like. It should be capitalized, and these are some examples of values that we can assign as the new color. So we're basically documenting the getter and the setter in one docstring, and that is what you should do. You should document the getter and the setter in the same docstring in the getter. Okay? We don't write any docstrings for the setter, so we go to the diameter. In the diameter, let's write return the diameter of the circle. And we say this is a float that represents the distance through the center of the circle from one side to the other. We just provide more details about this value. And we're done, basically, documenting the properties. So now we have to go to the methods. We go to find area. So what are we doing with this method? We say find and return the area of a circle. The area is calculated with the circle radius using the formula or applying the formula pi times radius squared. Great, so now let's go to our final method, find perimeter. We say find and return the perimeter of a circle. The perimeter is calculated with the circle radius using the formula. What formula are we using right here? 2 times pi times the radius. 2 times pi times the radius, okay? Great, so now we have our class completely documented. As you can see right here, we have the documentation or the docstring for the class. We have the docstring for the constructor, a docstring for each one of the properties, and we also have a docstring for each one of the methods. Great, so let's see how this works with the doc attribute and with the help function. Let's see how we can find or read the documentation for the circle class. We say help, and right here we are going to find or read the documentation for circle. Okay, let's save the file and run the code and see what we get as the output. Right here you can see that we get the documentation for the circle class, the class that we just described. Help on class circle in module main. Circle with radius and color. A class that represents a circle, and this is actually what we wrote in our docstring. We have the attributes, their description, we have the methods and their description, and this is generated automatically when we use the help function. We see this. Init, initialize an instance of circle, and right here we can see the arguments of init, the documentation that we wrote. Right here we also see a documentation for the methods find area and find perimeter. We see the read-only properties that were defined, the diameter. We can see that the docstrings that we wrote are right here, and right here the radius. We can make this documentation for the properties more concise and just describe the value directly. This is another option, making this more concise. And we see some data descriptors, including color. Return the color of the circle. The color is described by a string that must be capitalized, and we see the examples that we included in the documentation. Awesome, so we can read this with the help function. And we can also print, for example, the value of the dog special attribute. So right here, we only see the documentation for the class. Awesome, now you know how to document your classes, your properties, and your methods in Python. Great work so far during the course. Now let's see how docstrings are related to the special attribute doc. You will see that doc is actually what links docstrings to the corresponding element in the code. When you write a docstring as the first element of a function, method, module, or class, that docstring is automatically linked to that element through the doc attribute. This is a special attribute because you can see that right here we have 2 leading and 2 trailing underscores. This is what we call a special attribute. You can access the docstring in the interactive shell and basically in any Python interpreter with the help function that we have right here. We will use this in PyCharm. When you call the function and you pass the name of the element, for example, the name add, right here within parentheses as the argument, you will see the docstring for that element if it exists. You can learn more about the element and how to work with it with the help function and with the doc attribute. Now let's see how you can access docstrings for built-in methods that you commonly work with in Python. And then you will see how we can customize them. But before we do that, think about how you can access the special attribute doc. Try it. It's the same syntax that we have been using so far to access an attribute. Now we're just adding the leading and trailing underscores. Pause the video for a moment and then come back so we can try this in our code. Let's read the documentation for some built-in methods that you have been working with so far in Python since you started learning how to code. But now you will learn how to access their docstrings to learn even more about them. Let's start with the length function. This is a function that you probably used like 1,000,000 times to get the length of a sequence. There are 2 alternatives. We can use the help function that we have right here. If we write help and within parentheses we pass the name of the function, we will see its docstring directly, like this. If we save the file and we run the code, we can see its documentation. We see help on built-in function length in the module built-ins. So we know that this is the name of the module that this function belongs to. And we see right here its arguments. We see that it takes an object. And it says, return the number of items in a container. Awesome, right? We can use the help function to access that. Or we can also write print the name of the function and the special attribute doc that we have right here. You can see that it has 2 leading and 2 trailing underscores. We click enter or we can write it manually. And if we run the code, we just see the documentation, return the number of items in a container. So you can see that the documentation, the docstring, is assigned to this special attribute. And that is an attribute of the object, of the function, of the class, of the module, or the method. Awesome, let's try this again with the help function, but now let's see what it says about the sorted function. Like this. We see help on built-in function sorted in the module built-ins. Right here, we see the arguments that the function can take. Iterable, because it takes an iterable to sort it, and then we see some optional arguments, key and reverse. And these are their default values. It says return a new list containing all items from the iterable in ascending order. So you can see the purpose of the function right here. And you can see that right here, the effect of the function is written as a command, return, like we read in the docstring conventions. Right here, we also have more information about the function. So right here, we are having more details about the optional arguments, key and reverse. Awesome. Let's try this now with a method, because so far our examples have been functions. Let's say that we want to get the documentation for the sort method of a list, of the list class. We write the name of the class, which is list, And then we write the name of the method, which is sort. But instead of writing these empty parentheses, like when we call a method, we're going to omit them. Okay? We're just writing the name of the class dot the name of the method. And since we are using the help function, that will return the documentation. It will show us the documentation for that method. You can see this right here, help on method descriptor, sort. We can see that it takes self, and right here it has some optional arguments, and we can see a description, the summary line. Sort the list in ascending order and return none. Okay? We can also specify that a method returns none in our documentation. We see that the sort is in place. It warns us that the list itself is modified and stable. The order of 2 equals elements is maintained. So you can see that all of these optional arguments are explained in the corresponding paragraph, and right here we have a brief summary and more details. So these are great examples of how you can start writing your documentation for the methods of your class. Now let's see how this works with a function and its doc attribute, the special attribute, and the help function. This is equivalent for methods of the class. You just have to add the name of the class before the name of the method if it's a method. Right here we have a function. We have the add function with this one-line docstring. Let's say that we want to access the documentation for this function. We would just write help and add right here. If we save the file and we run the code, we can see this right here, help on function add in the module main. We see the name of the method, its 2 arguments, and we see that it returns the sum of A and B. Awesome, this is the documentation, the docstring that we wrote right here. So using the help function, we can access this, but we can also use the print statement to access the doc attribute, this attribute right here, and that will almost be equivalent in this case. That will just return this line without any additional information like this. We see return the sum of A and B. Now, if this was part of a class, you would just add the name of the class right here, like this. For example, the name of the class dot add dot doc. Remember that to access the documentation from a class, you just need to add the name of the class before the name of the method, like this, for example, list.sort, and that will return the documentation of the sort method from the list class. You could also write, for example, let's say tuple.count. The count method applied to tuples, like this. You can see that count returns the number of occurrences of value that we have right here as an argument. So you just have to specify the name of the class before the name of the method. For example, string, and the method capitalize. This will return the documentation. Return a capitalized version of the string. More specifically, make the first character have uppercase and the rest lowercase. This would be exactly the same with your class, your custom class. You would just write the name of the class right here and the name of the method right here, and that would return the documentation. Or alternatively, you could use the print statement and just write the name of the class followed by the name of the method and the special attribute doc, like this, okay? This returns the documentation directly, like this. Awesome, now you know the connection between docstrings and the special attribute doc and how we can access the documentation with the help function. Hello and welcome to this section. Now we will start talking about special methods in Python. They are also called magic methods, and you will see why in just a moment. The first thing that you will notice about these methods is that their names start and end with double underscores. This is key, double underscores. Here we have the basic structure of the name of a special method in Python. We have double leading underscores, followed by the name of the method, and then double trailing underscores. Right here within parentheses, we will have the necessary parameters. Of course, self will be the first parameter, and then we can add the parameters that we need for that specific method. You will learn how to do this during this section. Here we have some examples. We have the method add, the method string. This is an abbreviation of representation, REPR. You will see why these two methods are similar and yet they perform different functionality. We will also cover the length method, bool, EQ, LT. These are part of what we call rich comparison methods. We will see these and other methods that we can implement in our classes to be able to compare objects. And right here we have another example of a method, size of. This is another special method. I'm sure that you immediately noticed visually that all of these names are surrounded by double leading and trailing underscores. This type of method is also called dunder methods. Why? Because they have double underscores. Double underscores. And why are they called magic? Well, because they add special functionality to the class and to the objects that we will create from the class. But they act behind the scenes. They act indirectly. They are meant to be called indirectly through other methods or actions. We're not going to call them like we usually do, writing the name of the method and passing the arguments. We're going to call them indirectly through other methods or actions. For example, in Python, I'm sure that you've done this like a million times. We add two numbers, like for example 5 and 6, using the plus operator. But actually, behind the scenes, we are calling the add method of the integer class to perform this operation. We're not actually calling this method. We're not writing add with double leading and trailing underscores and then passing the arguments. We are just writing this operation using the plus operator, and behind the scenes, this method is being called. You will see that this is true in just a moment with a practical example. With this concise syntax, we're basically doing something that is equivalent to this behind the scenes. We're taking the first number, and we are calling the add method on that first number, passing the second number as the argument. That will call the add method, and the result will be the sum of these two integers. But this is all done behind the scenes, for us automatically when we use the plus operator. And that is basically the principle of magic methods. We perform other operations, and they are being called behind the scenes. Let's see how this particular example works in our code. Right here, I'm in my PyCharm project, Python OOP as you can see right here, and we have a main file which we are going to run with our examples. Let's see that this is actually happening behind the scenes. Let's print the result of adding 5 and 6. We know that the result will be 11. Let's run the code and we see the output, 11. Let me zoom in so we can see this a little bit better. And what do you think will happen if we call this instead of using the plus operator? We write this, the number surrounded with parentheses, then we call the method add with double leading and trailing underscores, and we pass within parentheses the number 6 as argument. This, believe it or not, is equivalent to this. We're just using a more concise syntax because magic methods are not meant to be called directly. Let's save the file and run our code. And we see that the output is exactly the same, 11. We are adding 5 and 6 using a different syntax. This is what actually happens behind the scenes when we write the plus operator. Now let's see if this works if we assign the result of 5 plus 6 to a variable. Result 5 plus 6, and we print the result right here. We know that with the plus operator this will work. We have 11, so nothing has changed so far. And surprisingly, we can also assign the result of this method call, the value returned, to a variable. We can use the same variable result. This is equivalent to this. It will return the value, and we can assign that value to the variable result. If we save the file and we run the code, we see the same output, 11 and 11. Quite surprising, right? When we write this, we actually call this. We're actually doing this behind the scenes. This was just one example of a special or magic method in Python. There are many more that you can implement, and you will learn more about them, how to use them, and how to implement them in this section. So I'll see you in the next video. Let's see what the Python documentation can tell us about special methods in Python, what they are used for, and how we can define them. To learn more about these methods, we have to go to the data model article in the documentation. Once we reach that article, we just click right here, section 3.3, special method names. And we reached that part of the article that covers special methods. We also have some details about each one of the special methods that we can define in our class. For now, let's focus on this part right here, which is a basic introduction to this type of method. And let's see how we can reach this article. You go to Google and you just type Python docs data model, okay? You click enter and the first search result will very likely be this one right here with the latest version of the documentation. Wherever you see docs.python.org, that will be an article of the official documentation. We click on it and we reach this article, which is exactly what we need. Once we reach the article, we go to section 3.3, special method names. And let's read its content. A class can implement certain operations that are invoked by special syntax, such as arithmetic operations or subscripting and slicing, by defining methods with special names. This is Python's approach to operator overloading, allowing classes to define their own behavior with respect to language operators. Operator overloading is just basically customizing what happens when we use a specific operator of the language with a specific data type. For example, with the plus operator, we can concatenate strings, we can add integers, and we can also concatenate lists, but the behavior of the operator is different for each data type that we work with. That is basically how operator overloading works behind the scenes. You can provide different functionality for different data types with the same operator. Right here we have an example of a magic method that we can implement. We will see more about this special method in this section. We will see some practical examples as well. Let's see. For instance, if a class defines a method named getItem, and X is an instance of this class, then we can index that instance. Just like we index, for example, strings or lists, we will be able to use this syntax to index the instance. And that will be roughly equivalent to this right here. So they're acting behind the scenes and they're providing special functionality. Right here we can see some information about exceptions. Except where mentioned, attempts to execute an operation raise an exception when no appropriate method is defined, typically attribute error or type error. Right here we also see that setting a special method to none indicates that the corresponding operation is not available. For the last paragraph, we see a suggestion. When implementing a class that emulates a built-in type, it is important that the emulation only be implemented to the degree that it makes sense for the object that is being modeled. For example, some sequences may work well with retrieval of individual elements, but extracting a slice may not make sense. This is basically telling us that we should only implement the methods that really make sense for the object that we are modeling. Some objects may logically allow indexing, some objects may not. Some objects can be added to get a final result and some may not. So you should only implement the special methods that make sense for that object. Awesome! Now you know how to learn more about these methods in the documentation. Right here we have more details about each one of them, and we will see them in detail when we cover them during this section. Great, so when you're ready, let's start diving into our first special method. Now let's talk about the special method str, which is an abbreviation of string. Why and when should we use this method? When should we implement it in our class and why? Let's see what we can find in the documentation. If we go to the data model article in the documentation where we said that we could find all the information for the magic methods in Python, we can click right here in section 3.3, special method names, and we can go to basic customization. Right here you will find all the information for the method. Let's just search right here to find the method, and right here we can see it, str. Let's see what we can learn from this description. There are three indirect ways of calling this method. It is called when we call str on an object, so we want to convert it or cast it to a string, like we do right here. And it's also called when we call the built-in functions format and print to compute the informal or nicely printable string representation of an object. the return value must be a string object. So if we try to print something, like for example when we print a list or a string or a number, this method is called behind the scenes. So based on what you just read in the documentation, when we call the print function on an object or the format function, we are calling the str method indirectly. We're calling the special method indirectly, and the value that we see printed as the output is the value returned by this method. Okay? So if you want to customize how an object looks when you print it using the print function, you have to implement the str method in your class. Great, so let's start diving into a practical example. First, think about how you would implement this method in a class that represents a two-dimensional point. A point with an x-coordinate and a y-coordinate. How would you print it? Pause the video for a moment, think about it, and then come back so we can start writing the code. Let's start writing the point2d class. We're going to write this class in the main file of the Python OP project. First, we write class and then we write the name of the class, point2d. Okay? A point in a two-dimensional plane with x and y coordinate. First of all, we have to define the class constructor, init. You can see the PyCharm already completes the first parameter, which is self. And we want to take x and y as arguments to create an instance. We assign these two values as instance attributes, x and y. For now, we're going to make these attributes public because this will be a simple class. Okay, so after that, what do we want to do? We want to customize how our point, or two-dimensional point, will be displayed when we print an instance of the class. So we have to define the str special method. In this case, str doesn't take any arguments. It doesn't have any other parameters besides self. And in the body of the method, we have to return a string. Remember that the documentation said that we have to return a string from this method. And that string will be used to describe the object when we try to print it. We're going to use an f string. F strings were introduced in Python 3.6, so you can use them in Python 3.6 or later versions. And how are we going to do that? Well, we are going to present the point as a tuple. The usual mathematical notation for a 2D point is the x-coordinate, like this, followed by the y-coordinate, separated by a comma and a space, surrounded with parentheses. So that is the representation that we are going to print for the point instance. We're going to print its coordinates. You can see that we're going to customize it, but first we have to add self, because these values will be customized for each instance. So the output will be helpful. It will provide more information about the point instance that we are working with or that we are printing. Let's see how this works. Let's save the file, and now we're going to define an instance. Let's call it myPoint. Point2d. We use the class that we just defined, and within parentheses, we need to pass the x and the y coordinates as arguments. Let's say, for example, 56 and 60. After we have that instance defined, we just need to print it to see how the str method works behind the scenes. If we try to print the point right now, we save the file, we add a blank line right here to follow the best practices of the Python style guide, we run the file, and we see this as the output. When we print the instance myPoint, we are getting this as the output. We are getting its x-coordinate, which we defined right here, and its y-coordinate, which we defined right here when we created the instance. Notice what happens if we don't define this method. Let's say that we delete this method. And we just have this line that creates the instance, and we print it. Let's run the code. We see the data type of the object, we see that it is a two-dimensional point, point2d, an instance of this class, and is located at this particular address in memory. So this is the default implementation when you try to print an object that doesn't have the str method implemented. But if we reverse these changes, now we run the code, And we see the data that we wanted to display, the x and the y coordinates of the point. Great, so this was our first example of how the str method works behind the scenes. Let's go to another example where we will implement a student class to print the data of each student when we try to print an instance. Okay, so let's start writing our student class. This is another example of how you can customize the output when you print an instance of the class if you customize or implement the str magic method. We define the student class and now we need the constructor, init with self. We're going to take as arguments the student ID, the name, the age, and the GPA. We assign them as instance attributes. Self.studentID, studentID, self.name, name, self.age, age, and self.gpa, GPA, okay? Now we have our class constructor. We will need to pass these arguments when we create a student instance, and we assign them as instance attributes. Now let's customize or implement the str method, so we can avoid using the default implementation. Let's say that we want to be more descriptive about the student. When we print a student, we want to know its 4 main attributes, these ones right here. So let's return a string with this data. We're going to write an f string and we say student, and let's print the name first to make the output more friendly instead of the ID. But this is totally up to you. You can customize it to your liking. We can also print the ID after the name, the age, self.age, and the GPA, like this, self.gpa. Since this string is quite a long string and it has more characters that we can show on the screen at once, it would be more comfortable and recommended for readability purposes to break this string into multiple lines. So let's see how we can do that. We just end the string with, part of the string with a double quote, we add a backslash, and then we click enter. We start another f string on the next line, and we do exactly the same. We just write this, a backslash at the end of the line, and we start each part of the string with an f to make it an f string. So now we have our string and our representation of a student instance. When we call print on a student instance, this data will be presented. Let's check this. Let's create a student instance from the student class, and let's assign, for example, the student ID 42AB9. The name will be Nora Nav. She will be 34 years old and her GPA is 3.76. Now if we call print on that instance, we will see this data. Let's save the file and run our code. We add one line right here, we run our code, and we see this as the output. Awesome, right? We see the data of the student printed on the same line because we are using this right here to indicate that we want to continue the same line, and we see the values of the instance replaced. We see the name, we see the student ID, the age, and the GPA. Notice that right here we are not having a space after this last value right here. That can be solved quite easily by just adding a space at the end of each string right here. So if we run the code again, we see that the spaces were added successfully. The important thing is that we were able to customize how the instance is printed and the data that is displayed. We are not using the default implementation. Awesome, so now you know how to customize what is printed when you print your instance. When you're ready, go to the next video, where you will learn more about the next special method that you can customize and implement in Python. Now let's talk about the special method length, how we can implement it and when we should use it. Let's see what we can learn from the Python documentation. Now we're back to the article data model, and again we have to click on section 3.3, special method names. After that we have to search for the subsection 3.3.7 in this case. It's almost at the end of the article in the documentation. 3.3.7 right here. Emulating container types. That's what we are going to do. By implementing the length function, we are going to emulate a container type, like a list, like a tuple, like a dictionary. They all have length, and strings have a length as well. Right here we can see the description of this method, object.length, and we have self as the only parameter. Let's see what the documentation says about this special method. It says that this special method is called to implement the built-in function, length. Right here, the built-in function that we typically use to get the length of a sequence. That method should return the length of the object, an integer that has to be greater than or equal to 0. You cannot return a float from this method. If you try to return a float, you will get an error. Right here, we also have another case that mentions the bool special method, but we will get to that once we reach the video that covers this special method in more detail. So, based on what we just read in the documentation, whenever we call the length function to get the length of a sequence, or in this case of an object of a class that we defined in our program, we are actually calling the length method, the special method length, indirectly. And the value that we get from calling the length function is the value returned by the special method. Right here, we are back to PyCharm. We have the Python OOP project and the main file. And right here, we're going to write our examples to prove that calling the length function is equivalent to calling the length method. It just happens behind the scenes. First, let's start by defining a string. We say my string, and we are going to assign hello world as a string for this variable. After that, we are going to print the length of my string using the length function. And how are we going to check that this is equal to the method? Well, we write the name of the variable, the string, and strings have a length method, a special method that is called behind the scenes, but we can call it explicitly. If we call it explicitly and we use empty parentheses right here, because this method doesn't take any arguments, we will get the length of the string as well. Let's save the file and run the code. And right here we see that the numbers are equal. 13 is the length returned by the function and returned by the method. The number is exactly the same. This is true for a string, but now let's see what happens if we have a list. 1, 2, 3, 4, and 5. And we also print the result of calling the length method on the list. We comment this out temporarily so we don't run these lines of code. We run the code and we see the number 5 because we only have 5 elements in this list. So you can see that we're starting to confirm that calling length as a function and as a method, as a special method, is equivalent. Now let's comment this out and let's try this with a tuple. But first, let me copy and paste this right here. You have to be very careful when you copy and paste. But this will just be a small change, replacing the square brackets with parentheses and changing the name of the variable. My tuple, we have my tuple right here and we have my tuple right here. So we know that there are no possible bugs. We made all the necessary changes. We save the file, we run the code, and right here we see 5 as the output, because the tuple had 5 elements, and that is the correct length. Finally, we tested this with strings, lists, and tuples, so we can also try this with a dictionary. Right here we define the variable myDict, and we map keys to the corresponding values. We associate them. A to 1, B to 2, and C to 3 in this case. This is just a basic sample dictionary. We will use the same function calls, print, and length, and we will also call the length method on the dictionary. Right here. If we save the file and we run the code, we see that the length of the dictionary is 3, because we have 3 key value pairs, and that is correct, and both results are equal when we call the function and when we call the special method. So this is all happening behind the scenes. We just use a more concise syntax, and we can customize what happens right here when we call the function if we implement this method in our class. Awesome! We've confirmed that this is equivalent for built-in data types and data structures. Now we will start coding our second example. But first, think about how you would implement this method in a backpack class. If we want to get how many items are in the backpack. Pause the video for a moment, think about this, and then come back. Remember, a backpack and the length should be how many items are in the backpack at any given moment, when we call the length function. Let's write our backpack class. Right here, I'm working on the main file of my Python OOP project in PyCharm. First of all, we have to write the class header. We write the class keyword and we write the name of the class, backpack. Initially, when we create a backpack, it will be empty. So, what are we going to do? We are going to define init. And in init, we are not going to add any parameters to this list. We're not going to take any arguments when we create an instance. We are just going to have an empty list of items because the backpack will be initially empty. After we have that, we have to define two methods. A method to add an item to the backpack and a method to remove an item. We're going to simulate this. So the method will be called addItem. In this case, we do have to add a second parameter because we have to specify what item we want to add to the backpack. And what are we going to do once we have that item? Well, we are going to append the item to the list of items in the backpack. This is the list of items when we use self.items. This attribute that we have right here for the backpack instance. We append the item. For simplicity purposes, in this example, we are going to describe the item with a string, but this could also be a custom object that you define. Okay, so we have our addItem method. Let's start defining our removeItem method. And in this case, we will also need a second parameter, the item that we want to remove. In this method, we will have to check something before we actually remove the item. We have to check if the item is in the list of items first. If that is the case, then we can remove the item and we will not get any errors. So it's best to check this before trying to remove the item. We call the remove method on the list of items in the backpack and we remove the item only if the item is in the list of items. Else, if the item is not in the list, then we can just, for example, print a message and say this item is not in the backpack, like this. Awesome. Now we have our two methods, addItem, removeItem, and we also have our constructor. So let's start defining our special method. In the context of a backpack, we are going to define the length of a backpack as the number of items it contains. So it will be the length of this list that we have right here. It's initially empty, so initially the length of the backpack will be 0. But as we add items to the backpack, the length will be incremented. And it will always be an integer. So this meets all the criteria that we needed. We just write return, and what are we going to return? The length of the list of items. Okay? Notice that right here we are using the built-in function within the special method. But we are using that function to get the number of items in the backpack, the length of the list, self.items. Awesome, so now we have our class. Let's start defining an instance. We will call it my backpack. And let's create the instance with the backpack class. As you can see right here, let me zoom out so we can see the name. Backpack right here. And since we don't have any arguments that we need to pass to create the instance, we just write empty parentheses. After we have that instance, we just have to start adding items. And how do we do that? We use the instance and we call the method addItem on that instance. As you can see right here, we have an item that we need to specify to call the method. So let's say that, for example, we're going camping and we are going to include a water bottle in the backpack. We also want to add a first aid kit in case anything happens, and we also want to add a sleeping bag. That will be very helpful if we want to spend the night in the mountain. Great, so now we have our backpack with 3 items. Let me just add another line right here, and what are we going to do now? We have 3 items, So based on what we defined as the length of a backpack, the length should be 3. How many items we have in the backpack? Let's check that this is true. We're going to print the length of the My Backpack instance, okay? So let's save the file and run the code to see if we get the output that we expected. Right here we see 3 as the output. That is the length of the backpack. That is correct because we added 3 items to this backpack instance. And that is awesome. We can define the length according to our context. In this case, in a backpack, we have the number of items defined as the length. Let's also test how the remove items method works. We call the method on the My Backpack instance, and we are going to remove the sleeping bag. Because let's say that in the last moment, we decided that we are not going to spend the night in the mountain. We are removing that item from the backpack, and once we remove the item, the length should be updated. Previously, we had 3 items, and now we have 2 items. So let's print the length again after removing the item, and let's see what we get. The length was updated correctly. Previously, we had 3 items that we added with the add item method. And now we have 2 items, because we removed an item from the backpack. Awesome! So let's see what happens if we just remove the other items that we had added to the backpack. For example, we remove the water bottle, and we remove the first aid kit. Now let's print the length of the backpack, My Backpack. Let's save the file and run the code. And now we see exactly what we expected, so the method is working correctly. We had 3 items, then after we remove an item, we have 2 items, and after we remove the other items left, we have 0 items left in the backpack. The backpack is empty. Now, if we try to remove an item, let's say, for example, water bottle again, the backpack should be empty. So we should get a message like this. Let's run the code and we see exactly that. This item is not in the backpack. Awesome, so now you know how to customize the length of your instances using the special method length. In the context of a backpack, we defined it as the number of items, but you can define what length means for your custom objects. And it's important to only implement this if it really makes sense for an object to have a length. Awesome! When you're ready, go to the next video to continue learning more about these special methods. Now let's talk about the special method add, how we can implement it, and when and how we should use it. Let's see what we can learn from this method in the Python documentation. If we go to the data model article in the documentation, to find the add method, we will have to go to this section right here. Emulating numeric types. We click on it and we are taken directly to the part of the article where we can find the add special method. Let's see what this says about emulating numeric types. The following methods can be defined to emulate numeric objects. Methods corresponding to operations that are not supported by the particular kind of number implemented should be left undefined. Right here we can see that this method takes 2 parameters, self and other, the 2 operands that will be involved in the operation. Let's see what it says right here. These methods are called to implement the binary arithmetic operations. You can see all the operations right here with the corresponding symbols, because all of these special methods can be customized and they correspond to binary arithmetic operations. For instance, to evaluate the expression x plus y, where x is an instance of a class that has an add method defined, then this is what is actually being called behind the scenes, okay? This is what happens behind the scenes when we use the plus operator. The add method is called behind the scenes. This is the part that we're interested in right now, how we are going to customize the behavior of the plus operator by customizing and implementing the add method in our class. So, based on what we just read, when we add 2 objects using the plus operator, we're actually calling the add method, the special method, indirectly. Awesome, right? They act behind the scenes. If we implement this method in our custom class, in the class that we write in our code, we can actually define what happens when we write something like this, when we try to add two instances of the class. We will see this in just a moment, but first let's see how this operator works with objects of built-in data types, such as integers, strings, and lists. This will be a really nice example of operator overloading, how the behavior of this operator in the language can be customized for each specific type of element or object that we are working with. Let's start coding. Right here, I am in my Python project, Python OOP, in my main file. Let's see how the plus operator is an example of operator overloading, because the behavior of the operator is different depending on the data type that we are operating with. First, let's see the effect of adding two integers. We know that they will be added, but let's confirm that we are actually calling the special method add behind the scenes. We write the first number, 3 in this case, and that number has an add method, because the integer class has an add method defined. If we add 3 to the number 4, we pass 4 as the argument, we will see the output. Let's save the file and run the code. First, let's zoom in. We run the code, and right here we see the value 7. So they are both equivalent, 3 plus 4, and calling the special method add. This is being called behind the scenes when we use this operator in Python. This is an example with integers. So let's see how this works with strings. For example, let's say that we want to concatenate two strings. For that, we would use the plus operator too. Notice how the behavior of the operator is different based on the data type that we are working with. If we add two integers, then the result is another integer. If we add two strings, the result is another string with all the characters in both strings. That is an example of operator overloading, and that is exactly what you can achieve by customizing the add method in your class. In this case, let's check that the result of concatenating these two strings with the plus operator is equivalent to calling the add method on the string. We call the add method on the first string and we concatenate or we add the second string. Right here, we pass it as the argument. First, let's comment out these two lines so we only see the output related to strings. Let's save the file, we run the code, and right here we see the same output. We see a single string made with the characters of both strings, so they are concatenated. They are equivalent using this operator or calling the add method, but in Python we use this operator, and this is called behind the scenes. This works with strings as well. So now let's test how it works with sequences, like for example lists. If we have two lists, we will be concatenating the lists. We will be joining those lists. And we will be making a single list with all of the elements in both lists when we use this operator. Notice that the behavior is customized. When we add two integers, we get an integer. When we add two strings, we get a string. When we add two lists, we get a list. And that is exactly the behavior that we have to implement in our add method when we customize it in our next example. We usually return an object of the same data type as the arguments. Okay, so let's confirm that this is equivalent to calling the add method. We're going to call this on the list, call the add method on the list, and we are going to add the list 4, 5, 6 with the elements 4, 5, 6. Right here. We save the file and we run the code, and right here we see the output. We get a single list with all of the elements that were in the two individual lists that we wanted to concatenate or join. Awesome, now you know that this works for built-in data types, and you're going to learn how to customize it for the objects of your class. Now we've completed our first example. Think about how you would add 2 points with x and y coordinates. How would you implement the special method add in this class in point2d? I'll give you a hint. When we add 2 points, we add the corresponding coordinates. The x-coordinate with the x-coordinate and the y-coordinate with the y-coordinate respectively. And the result is another point with 2 coordinates. Think about this for a moment and then come back so we can start working on the code. Right here we are in PyCharm and we are going to start implementing our point2d class with a new special method, the add method. So we will be able to add 2 or more points with 2 coordinates, x and y. Let's start with the class header. We say point2d. That will be the name of the class. We can't start the name with a number, so that is why instead of 2d point, we write point2d. After that, we need the constructor, init. And what do we need to know to be able to create a point instance? Well, we need to know the x and the y coordinates of the instance. We assign them as instance attributes. And since our class will be very simple, I'm going to make these attributes public. Okay? After we define the constructor, we can create point instances. But what do we need to implement in this case? We have to implement the special method add. So we can customize or determine what happens if we add 2 instances of the class. You can see that by default, PyCharm added a second parameter right here to the list. This parameter is named other. Why? Because we need to know what element we are going to add. Remember that in our previous examples, we added 2 integers using the add method explicitly. What did we do right here? We took the first element, we called the method on that element, on that value, the integer, and then right here we were passing a second value as the argument to the method. That argument, that second value that we are going to operate on, the second operand, the operand to the right, will be the value of other, whenever we use the plus operator. Okay? So, what are we going to do with that? We can take the data from the current instance using self, and we can also combine it or work with the data of the other element. We have the 2 values. We have references to the 2 objects, the object to the left and the object to the right. So for example, if we write this, object 1 plus object 2, object 1 will be assigned to self and object 2 will be assigned to other. So we can work with their individual attributes. That is awesome because we will need to use them to get a new point instance. When we add 2 points, we add the respective coordinates. The x coordinate, like this, and the y coordinate, to get the new x and y coordinate of the point. We take the x coordinate of self, the left operand, and the x coordinate of the right operand, and we use them to get a new value for x. That will be the x coordinate of the new point. And then we take the y coordinate of the left operand and we add it to the y coordinate of the right operand. And that way we will have a new y coordinate. And what are we going to do with that? Well, remember that when we added 2 strings, the result was a string. When we added 2 lists, the result was a list. So when we add 2 points, the result will be a point. So we have to return a new point instance. We are going to create that instance right here and we are going to return it. But for us to create an instance, we have to specify the value of x and y. And what are those values? Well, new x and new y, the new coordinates that we calculated by adding the x coordinates and the y coordinates. And that will return the new point instance. That is basically how you need to implement this method in a point class. Awesome, right? Now, instead of just returning a value like a string or an integer, we are actually creating an instance of the class with its corresponding attributes, initial attributes. And we're going to return that instance so we can use it in our program when we add 2 instances. Finally, to complete the implementation of this class, let's implement the special method string, str. We're going to print its x coordinate and its y coordinate, like in mathematics. Okay, so now we have our class. Let's start testing it with some instances. Point A will be a point 2D with coordinates 5 and 6. And point B will be point 2D with coordinates 2 and 3. Okay, we have the instances right here. And what are we going to do with those instances? We are going to add them so we can get a third point. Point A plus point B will give us a new point instance, point C. We create the instances, then we add the instances, And from that addition, we will get a new point instance, point C. That new instance will have as its initial coordinates 5 plus 2, the sum of the x coordinates, and 6 plus 3 as the y coordinate. Let's print the value so we can see that it's actually working as we expected. Let's print the values of point A and point B, their coordinates. Let's print their coordinates. We're going to print each one of the instances and point C, so you can see that the result is the addition of the coordinates. Right here you can see it. Point A has coordinates 5 and 6. Point B has coordinates 2 and 3, like we have right here. 5 and 6, 2 and 3, and when we add them, we get a new point instance. And that point has as the x-coordinate the value 7, 5 plus 2, and the value 9 as the y-coordinate, 6 plus 3. So it is a point instance and it has the correct attributes that we expected from the class. Awesome! Now you know how to implement the add method. Remember, we take self, which is the left operand, and we add it to another instance, the right operand. We can use the data from both operands to get the sum of the instances, and we return a new instance of the class with its corresponding attributes. That is basically how you can implement this method. When you're ready, go to the next video so you can learn more about special methods in Python and how you can add them to your classes. Now let's talk about a really cool special method that we can implement in our classes, getItem. When we implement this method, we can actually index an object, just like we index a string, a list, or a tuple, but we will be customizing how the object is indexed. Let's see what we can learn about this method in the documentation. If we go to the data model article in the documentation, and we click right here on table of contents, we go to section 3.3.7, where it says emulating container types. We click on it, we will go directly to the part of the article where we can find that method. We just have to scroll down a little bit and we will reach the method almost immediately. Let's see what the documentation has to say about this method. We see that it has two parameters, self and key. Why? Because we need to know the key that we are going to use to index the object. So we have to include these two parameters when we define this method in our class. Let's read the description. This method is called to implement the evaluation of self and key when we use the key to index the instance. For sequence types, the accepted keys should be integers and slice objects. Note that the special interpretation of negative indices if the class wishes to emulate a sequence type is up to the getItem method. So we can actually implement indexing and slicing. So according to what we just read in the documentation, when we index an object like this, we are actually calling the getItem method indirectly behind the scenes. Let's see how this works behind the scenes for the built-in data structures that you have worked with since you started learning Python. Right here, we're back to PyCharm, and now let's confirm that when we index a sequence in Python, we are actually calling the getItem method behind the scenes. We're going to start by defining a list, and that list will contain 4 strings, A, B, C, and D, okay? What are we going to do? We're going to get the individual elements one at a time through list indexing. We're going to use their corresponding indices, okay? 0, 1, 2, and 3. And what are we going to do now? We're going to prove that this output is the same output that we get if we call the getItem method on the list. We do this right here, getItem, and what do we have to specify? Within parentheses, we have to specify the index that we want to get. We're writing the name of the list, we're calling the method, and we have to specify what item do you want to get? Well, the item at index 0. Then we want to get the item at index 1, and so on. We're going to go from 0 up to 3, like this. And we're also going to print like a small separator So we can differentiate the output from the first sequence of print statements and the second sequence of print statements. We save the file and we run the code, and now we see the output, A, B, C, D, from these 4 print statements when we use regular indexing. And you can see that this is the same output that we get right here below. A, B, C, and D from these 4 lines of code, where we call the getItem method passing their corresponding index. So this is actually happening behind the scenes. Awesome, right? Let's see that this works correctly for strings as well, for any type of sequence that you can index. For example, let's say that we have the string word. It has 4 characters, so we can use indices from 0 up to 3. And we will need to rename this variable. We can change this manually, or we can just right-click on the name and click refactor and rename. That will prompt us to choose a new name. So we are going to name this my string, and we want to refactor. Okay? And that will change the name of the variable everywhere it occurs in our code. Now if we save the file and we run the code, we see the output. We see that the output from these 4 statements, these 4 print statements that we have right here, is the same output that we get if we call the getItem method behind the scenes, like this, okay, in Word. Awesome, so now you know how this works with built-in data types and data structures. So let's start diving into an example where we will customize this method in a class. In this example, we are going to implement a bookshelf class. We are going to start by defining the class header. And after the name of the class header, we have to define the constructor. Initially, the bookshelf, when we create that instance, will be empty. So we are going to define this. The content of the bookshelf is going to be determined or represented by a 2-dimensional list, a list that contains lists. Each one of those nested lists will represent a particular shelf or level in the bookshelf. Right here, I am assigning the name content to this attribute, but you could customize this and assign any name you like. You can see that this is starting to look like a bookshelf, so we're going to use this data structure in our code. After that, we have to implement 2 important methods. We're going to add a book to the bookshelf, and we're going to take a book from the bookshelf. To add a book, we need to know which book we are going to add and the location of the book in the bookshelf. Okay, so we're going to call this location. You could also customize this name. What are we going to do with the book? We're going to take the list of books in the bookshelf, the data structure that represents the structure of the bookshelf, and we are going to first get the location of the book, the level where it is located, where it will be inserted. If it's 0, it will be at the top of the bookshelf, the first list. If it's 1, it will be in the second level, and if it's 2, it will be on the third level. So we get that list, we get the level, and we append the book to that particular shelf in the bookshelf. That is what we are doing right here. We're taking the full structure of the bookshelf, we're getting its corresponding level or location, then we append the book. For simplicity purposes, in this example, the book will be represented with a string. It can also be a custom object with its own attributes, okay? Now we can add a book. And we also need to implement another method to take a book from the bookshelf, take book. We need to know which book we are going to take and where it is located, okay? In this case, we are going to simplify things by making the user specify the location of the book in the bookshelf. So let's see this. We're going to take the content of the bookshelf, its location as well, so we're going to get the list that corresponds to that particular level where the book is located, and then we are going to remove the book. In this case, we're going to assume that the book is already part of the bookshelf in the level that was specified by the user. You could also try to implement a conditional right here to check if the book is in the location that was specified. Great, so now we can add a book and we can take a book. So we have to start implementing the special method getItem. In PyCharm, you can see that we already have 2 parameters by default, self and item. we're going to customize this name to location, because we are going to specify the location of the book as the index. If we pass the number 0, we will get the top shelf. If we pass the number 1, we will get the second level, and if we pass number 3, we will get the bottom shelf, or the third level in the bookshelf. The getItem method is going to return all the books that are at a specific level, okay? Right here, we're specifying the location that is going to serve as an index. When we index a bookshelf instance and we pass, for example, 0, we will get all the books at the top of the bookshelf at level 0. Then in the second level, we would get that level if we pass 1 as the location, and 2, we would get the third level. Okay? So what are we going to return? We are going to return the content of the particular location or level that we want to get. We could also replace location with level or with any other description or shelf as well. Great, so we have our class. And what are we going to do with this? We're going to create an instance, my bookshelf. And it's going to be a bookshelf instance. We can create the instance without passing any arguments because we don't define any parameters right here. It will be an empty bookshelf initially. And after that, we have to start adding some books. We're going to add these books to level 0, to the top level of the bookshelf. Pride and Prejudice and Frankenstein. These 3 books will be at level 0, at the top of the bookshelf, right here. Then, let's add some books to level 1, to the second level in Sensibility 1. Sense and Sensibility, we're going to add the book Jane Eyre to level 1 as well, and then The Little Prince, level 1. Finally, we're going to add the book Moby Dick to level 2, the bottom level of the bookshelf, and we're going to add The Adventures of Huckleberry Finn to level 2, and the book Dracula. Awesome, so we've populated our bookshelf with our favorite books. And how are we going to test the getItem method? Well, we have to try to index the bookshelf instance that we just created. This instance, my bookshelf. We are going to print my bookshelf at level 0. What books do we have at level 0 of the bookshelf? Well, let's see. If we run the code, we see these books right here. We're using the syntax that we use to index a list, a tuple, or a string, but now we are using it with our custom instance, and we are passing the value 0 as the index. So we're going to get the first level in the bookshelf right here. Right here at the top of the bookshelf, we have these books. If we confirm this with our code, we see that it is correct. Awesome, let's change this to 1. Right here we see Sense and Sensibility, Jane Eyre, and The Little Prince. And that is exactly what we added to the bookshelf, Sense and Sensibility, Jane Eyre, and The Little Prince. And finally, if we change this to the value 2, we see this, Moby Dick, The Adventures of Huckleberry Finn, and Dracula. And that is exactly what we added to the bookshelf. Awesome, so now you know how to implement the getItem method in your class to be able to index your instances of the class. You can customize this to your liking. The parameter that you take right here doesn't necessarily have to be a number, and it doesn't necessarily have to be 0 to start the indexing right here. It could be 1, and by subtracting 1, we would get the same behavior. So the user would enter 1 to get the first level, 2 to get the second level, and 3 to get the third level. And that would be handled behind the scenes, indexing that starts from 0. Awesome! Now you know how to implement this method. When you're ready, go to the next video so you can continue learning more about special methods in Python and how to implement them. Now let's talk about the special method bool. This method is really cool because it will help us determine and customize when an object is true or false, so we can use them in a Boolean context. Let's see what we can learn about this special method in the Python documentation. If we go to the data model article in the documentation, we can then click right here on basic customization. After we reach the part of the article, we just have to scroll down a little bit and we will find the part of the documentation that covers this method right here, bool. You can see that it only has one parameter, self. Let's see what it says. This method is called to implement truth value testing and the built-in operation bool. It should return false or true. When this method is not defined, length is called. If it is defined, and the object is considered true if the result is non-zero. If a class defines neither one of these methods, all instances are considered true. We will see an example of each one of these scenarios. So, based on what we just read in the documentation, whenever we call the bool function, we are actually calling the bool method indirectly. This method will also be called if we use the object in a Boolean context, for example, in a conditional or as part of a condition. So let's start writing the code for our first example. We will be writing a bank account class. I'm in my PyCharm project Python OOP in the main file, and we will start defining our bank account class, bank account. Now, the first thing that we have to define is the class constructor. We have self as a parameter by default, and we also want to define the account owner, the account number, and the initial balance. Those are the three attributes that we are going to assign to each bank account object. Okay, so now we have our attributes and we are going to define two methods. Make deposit. For example, we have to specify the amount that we want to deposit to the account. What are we going to do when we make the deposit? We are going to increment the balance of the account by that specific amount. You might want to implement a conditional for this method and check if the amount is actually positive. Now we're going to implement a method make withdrawal. Okay? We're going to withdraw money from the account, but we have to specify how much. That is why we define a second parameter right here, amount. In this case, we do have to use a conditional. We have to write a conditional in the body of the method because we want to check if the withdrawal will be allowed. If the user or the account owner has enough funds in the account to make that withdrawal. If the current balance minus the amount that we want to withdraw is still greater than or equal to 0, then we can make the withdrawal. We are decrementing the balance of the account by that specific amount. If that is not the case, then insufficient funds will be the message displayed to the user. If we leave the class like this, without defining the bool method and without defining the length method, then the objects that we create from the class will always be true by default. They will never be false. If we use them in a Boolean context, they will always evaluate to true. Let's see this in action to confirm that they will always be true no matter what. Okay, so after we have these two essential methods in our bank account class, we can create an instance. Right now, we are not going to define the bool method, so you can see what happens if we don't define this method in our class. We say my account equals bank account, and the owner will be NorNF. We're going to simplify this by just passing a string with the name of the account owner. This could also be a custom object. The account number is, for example, this is just a number that I made up. You can assign any number to this. And after that, we want to print the truth value of the account. We have our instance, okay? Now we have our instance, we have our class, and we want to actually print the truth value of the account. We can do that with the bool function. We can check if the account is true or false by calling this function and then printing the result. Let's save the file and run the code. We see that the account is true. Okay? We didn't define the bool method anywhere in our class, but by default, the instance will be true. So if we try to use this instance, for example, in a conditional, like a truthy or falsy value, let's see what happens. if my account, just like we use for example lists or strings to check if they are empty or not, right now we are using the instance directly. If we run the file, we see true, because the account was true by default. It will always be true, because we haven't implemented that method yet. And let's see what happens if I update the balance of the account to 0. If we print the new balance of the account, and I test again if the account is true or false, let's run the code, we see that the current balance is 0 and that the account is still true. So by default, all instances will always be true unless we customize or implement the bool method in our class. So let's start doing that. Now think about how you would implement this bool method in the bank account class. We want the bank account to be true if the balance in the account is greater than 0. And we want the bank account to be false if the account is empty, if its balance is 0. Pause the video for a moment and then come back so we can start writing the code. Right here we have the same class that we have been working with, and now we are going to add the special method bool. We're going to implement it in our class. This method only takes self as a parameter, and it has to return either true or false. But what is the criteria that we want to set to define if a bank account is true or false in our program? Well, we want to make the account evaluate to true if the account has a positive balance, if the current balance is greater than 0. If it is equal to 0, then we want the account to be false. So that is the criteria that we have to implement right here in our method. How can we do that? We are just going to return the truth value that results from making this comparison. Self.balance, we take the current balance and we check if it's greater than 0. If it's greater than 0, then this will be true. If it's not greater than 0, then it will be false. And that will be the value returned by the bool method. So now our bank account class, our instances, will be either true or false. Awesome, so now let's test this. We're going to add 2 print statements right here before we update the balance to 0. Before we update the balance, it is initially positive. So right now we're going to print the balance to check that it is positive, and then we are going to print the truth value of the instance with the bool function. After that, we are going to update the balance to 0 and we are going to test this again. Let's save the file and run the code. We see exactly what we expected as the output. Right here we have the initial balance, which is positive, and we see that the instance was true, evaluated to true right here. After we update the balance is 0 on this line, and right here we see that it is now false. This is something that we didn't have before we implemented the method. The instance was always true. But now, since we implemented this criteria, that the balance has to be greater than 0 for the instance to be true, we also have some scenarios where the instance will be false. Okay? If we use the account, for example the instance, as part of a conditional now, we will see print true, else, print false. We can use it. Let's write this right here, and let's write this after we update the balance. We'll be using it directly in the conditional. Let's close this so we can see this better. We have the 2 conditionals, and right here we update the balance. Let's run the code, and we see that previously it was true, and after we update the balance, it is false. Awesome, now you know how to implement the bool method. Let's see a final case that was mentioned in the documentation. Now we know what happens when we implement the bool method in the class, but there is another scenario that we could have that Python handles correctly. If we don't define the bool method in the class, but we do define the length method, like in a sequence, for example, that has a length, then when we call the bool function or when we use the object in a Boolean context, the value, true or false, will be determined by the value returned by the length function. So length sort of works as a backup. If we don't have bool, then the value of length will determine if the value is true or false. The program will ask, is the result or the value returned by the length method different from 0? If it is, then the object will evaluate to true. If the value is equal to 0, so the answer is no, the object will be false. This is just like when we use empty list or non-empty list. An empty list is false, like in this case, and a non-empty list is true. If the length is different from 0, it's true. If the length is equal to 0, then it is false. We're going to demonstrate this with a list. We say 1, 2, 3, 4, and 5, okay? If the list is not empty, we will get a particular message. Let's say, the list is not empty, because it will be true. We're going to print this, and then we are going to print the truth value of the list, okay? But if that is not the case, then we are going to say the list is empty, and we are going to print the truth value of the list. Great! So let's save the file and run the code. Right now we see that the list is not empty, and we see the value true right here. This part of the conditional was executed because the list evaluated to true right here. Now, if we remove these elements from the list and we run the code again, now we see that the list is empty right here, and now it evaluates to false. So this is an example where the length of an object determines if the object is true or false. For example, let's write the string hello world. Strings are also considered sort of like sequences for the characters. So let's say my string, we're going to replace it right here. And we are going to say the string is not empty, the string is empty. We close this, we save the file, and we run the code. And we see the same output, the same behavior. The string is not empty right here, so it evaluates to true. And this part of the conditional is executed. Now, if the string is empty, things will change because the string is now empty, and now it evaluates to false. So the else clause is executed because this evaluated to false. Awesome! So now you know how the length can also affect the truth value of an object. You learned in a previous video how you can customize the length special method. So now you know that that result can also determine if an instance is true or false. Great work so far during the course. Now we're going to cover rich comparison methods. Their main purpose is to help us compare objects based on specific criteria that we are going to define in our class. Because, for example, comparing two bank accounts is not the same as comparing two coordinates or comparing two dictionaries. The criteria has to be different, and that is why these methods are super helpful. These are the 6 rich comparison methods that we can implement in our class, and the corresponding comparison operator. When we use these operators in our Python program, we will be calling these methods behind the scenes, okay? Less than or equal to, not equal to, greater than, and greater than or equal to. Let's see some code examples of built-in types and how we use these operators with those built-in data types. And after that, we will customize these methods in our class. Let's see some examples of how we typically use comparison operators with built-in data types and data structures. First, let's test this with integers. For example, we can compare if 15 is less than or equal to 8. We can also check if 4 is greater than 4. We can also check if 5 is equal to 5. And finally, if 6 is different from 8. It's not equal to 8. In this case, we are performing these operations on integers, so they will be compared based on their value. If we run this, we see that the comparison returns a Boolean value, false or true. So we know that when we try to implement these special methods in our classes, we have to return a Boolean value, true or false. Now, the behavior of these comparison operators is different based on the data type of the values or the operands. For example, right here we were comparing integers, but we could also compare strings. And the criteria that is used to compare if a string is less than another one is completely different from the criteria that we use to compare integers, for example. Right here, we are going to verify if this string comes before this string in alphabetical order. It does because H comes before W in the alphabet. So that is a totally different criteria from our previous comparisons that we made right here. This is another example of operator overloading. We are using the same operator, but the behavior is different. The result is still a Boolean value, but the comparison is made based on different criteria, and that is the criteria that we will define. Right here we have other examples. Let's save the file and run the code, and right now we see that these three comparisons are true. We can also compare built-in data structures. For example, lists. We have 1, 2, 3, 4, and we want to check if that list is less than 1, 2, 3, and 5. In this example, we are using the same comparison operator, but the criteria is also different because we are going to be comparing each one of the corresponding elements in the list. For example, in this case, all of these values or elements are equal, but this value is less than this value, and they are in their corresponding positions at the end of each list in the same index. Since this comparison is true, then this comparison will be true. If we run the code, we can see that the last comparison right here is true. Let me comment this out so we can just see the result of this comparison as the output. We see true right here. That is the important takeaway from these examples, that the operators can be customized to work with different data types. Here we have another example where we compare the lists. Like this, we see true and true. So let's start working on our custom class. Think about how you would implement a circle class with rich comparison methods. We will have circles with a radius and a color. How can you determine if a circle is less than another circle, or equal to another circle, or greater than or equal to another circle? That is what we are going to define in our circle class. So take a moment to think about this, pause the video for a moment, and then come back so we can start working on the code. In this case, we'll be writing a circle class. So let's start with the class header, class circle. We will define the constructor with two additional attributes to self. We have the radius and the color. And we're going to be able to compare circles based on these two values or attributes. Okay, we have the radius and we have the color. How are we going to implement the rich comparison methods? Well, first, we can start with the less than method. You can see that these methods take two parameters, self and other. Self is the left operand. So if we have, for example, object1 and less than object2, this would be self and this would be other. Similar to when we implemented the add special method. We had a left operand and a right operand. The left operand is self and the right operand is other. Okay, so how are we going to implement this? We have to return a Boolean value, true or false. And what criteria will we use to determine if a circle is considered less than another circle? Well, in this case, we might use, for example, the radius. We might say, if this circle's radius is less than the other circle radius, then that means that the comparison is true. We're going to compare them based on the value of the radius. And in this case, we might not even consider the color. We might just consider the radius to determine if the circle is less than another circle. Similarly, we have to implement the less than or equal method. In this case, we can also use a radius as a criteria, but we will change the comparison operator right here, because we are comparing if a circle is less than or equal to another circle. And in that case, the radiuses can be equal. So that is why we use this comparison. If the radiuses are equal, then this will return true. And that is what we need. Now let's go to greater than. like this. And we are also going to compare them based on the radius using the greater than operator. Similarly, with greater than or equal to, we can see it right here. And we're going to compare the radius. We use greater than or equal to as the operator. And right here, we have to implement the equal to operation with this special method. How do we want to determine if a circle is equal to another circle or not? Well, we can use, in this case, both the radius and the color of the circle to determine if they are equal. If the radiuses are equal and they have the same color, then we can consider them equal in terms of their attributes. So in this case, we might want to write a condition like this. If the radiuses are equal, if self.radius is equal to other.radius, and the color of this circle is equal to the color of the other circle, then the circles are equal. And we return true like this. Let's reformat the file to follow the guidelines of the Python style guide like this. So we have this condition right here. We are comparing the radiuses and we are comparing the color. If both of those conditions are true, then the circles are equal. And similarly, we can implement the not equal to special method like this. We just use the same condition, we compare the radius, and now we're going to check if they are not equal. And there is a small change. Instead of using and, we are going to use or. Because if either one of the conditions is not true, then the circles are not equal. If they do not have the same color, then they are not equal. And if they do not have the same radius, they are not equal. So either one of those conditions can prove that the circles are not equal. Let's create some circle instances. We have our class with the rich comparison methods already implemented. So let's start creating some instances. We have circle A, and we are going to create a circle with a radius of 5 and the color blue. We're going to describe the color with a string. We're going to add a line right here, and we're going to create another instance. For example, with radius 5, but this circle will be green. Now, circle C will be a circle with radius 7 and color red. And finally, circle D is our fourth instance, and we will have it right here with a radius of 5 and color blue. So we can test our comparison methods. What are we going to do with these instances? Well, let's see if circle A is less than circle B. We can make this comparison because we have the less than a special method implemented like this. This is going to compare the circles based on the value of their radius, only their radius. In this case, the radius of circle A is 5 and the radius of circle B is 5. So we should get the value false. Circle A is not less than circle B. So we see exactly that. False. Awesome. Now let's test what happens if now we write less than or equal to. This also returns true if the circles have the same radius. So now we see true. Circle A is less than or equal to circle B. In this case, we're just comparing the radiuses. We could also check if their colors are equal. To verify that this is true, we could alter or change the implementation of this method less than or equal to also test if the colors are equal, like this. And self.color equal to other.color. And the same with greater than or equal to, because now we have to consider what happens if the circles are equal to each other. So if the radius of one of the circles is less than or equal to the radius of the other circle, of the right circle, and their colors are equal, then this comparison will be true. And the same with greater than or equal to. We're comparing the radiuses and the colors have to be equal. Okay? Now, if we make this comparison, instead of true, we will see the value false. Because circle A and circle B do not have the same color. Now we are comparing them based on the radius and their color. So that is how you can sort of customize what happens when you compare your instances. Circle A and Circle D have the same radius and they have the same color. So let's see. In this case, Circle A is not greater than Circle D, but it is greater than or equal to, so we see true, because they have the same radius and they have the same color. We can also compare if a circle is equal to another circle, for example, Circle A and Circle B. They have the same radius, but they do not have the same color. In this case, that is false. And if we compare it to Circle D, we will also see the value true, because they have the same radius and they have the same color. If we compare them using the not equal to operator, we also get a Boolean value false. They are equal, so this comparison is false. Great, so now you know how to implement your class with customized rich comparison methods. This way you can compare objects based on different criteria, appropriate for the context of your object. In this case, we have circles with radius and color. Hello and welcome to this project. We will start diving into data structures, and you will see why object-oriented programming is essential to implement data structures in Python and in basically any programming language. First of all, what is a data structure? Let's see. According to the Merriam-Webster Dictionary Online, a data structure is any of various methods or formats, such as an array, file, or record, for organizing data in a computer. The key part of this definition is organizing data. Those are the two key words in this definition. We use data structures to organize data, just like you can organize shoes and shirts and socks in many different ways in your closet, and how you can organize, for example, books with different levels of complexity and sophistication, so you can find the ones that you read most often first. We can store data in data structures in very specific ways. So you can see why they are important. Let's dive deeper into this. Why are they important? The main goal of using a data structure is to organize the data efficiently and optimize common operations for a given scenario. For example, reading the content of the data structure, the values, adding data, removing data, and even updating data. Those are very common operations that we need to perform on the data that we store in a data structure. For now, let's say that these colored circles represent data. This data, at the moment, is not organized at all. You can see that they are just random colorful circles at any random position. But we can organize them in a linear way, like this. Or perhaps like this. We can also use something similar to a tree shape. Or perhaps some data elements have to be connected to other elements in a specific way, like this. Notice that in all of these diagrams, the elements are connected. And these connections are represented with arrows. This is essential in data structures, and you will see why in the coming videos. But these connections are like the glue of the data structure that keeps the elements connected. All data structures have certain advantages and disadvantages, particularly in terms of efficiency and speed for performing certain operations. For example, if we structure our data in a linear way, and we want to find this piece of data right here, the process could be slow if we can only start searching from the first element in the data structure, which would be this yellow circle right here. We would have to go from the yellow circle to the blue circle to the green circle and so on until we find this data that we are looking for. But if we change the order of the elements to have this tree-like shape and the connections look more like this, then perhaps we could read or retrieve the value much faster. So how can we choose the right data structure for our program? Well, we need to consider the pros and cons, or the advantages and disadvantages of each data structure, based on the problem that we need to solve. And based on that, we can choose which data structure optimizes the most common operations for our given scenario or problem. Great! After this brief introduction to data structures, you may ask, why is object-oriented programming important to implement data structures? Well, actually, object-oriented programming is sort of like their backbone. Metaphorically speaking, of course, but in reality, they are sort of like the backbone in code. Because with object-oriented programming, we can define the actual data structures themselves, create instances, define their elements, store their data, and represent their connections and implement their operations. That is amazing, right? In this project, we will see how you can do this with a detailed example of a particular data structure. We will implement all of its operations in Python. But first, here are some examples of different data structures and their names, so you can be more familiar with this area of computer science that covers data structures. First, we have arrays and lists. These are linear data structures that you commonly use. Arrays are typically used in Java, and lists are used in Python when we use square brackets. Then we have trees, and we have graphs. Graphs are amazing data structures that we use to represent connections between elements. So connections between cities, or connections between warehouses, or between members of a social network. And right here we have another data structure, which will be the data structure that we will be working with during this section, linked lists. We will implement a linked list class during this project in Python. You will see that this is an amazing data structure. And this data structure will let us illustrate why object-oriented programming is essential to implement data structures in general. When you're ready, let's start working on the project. We will start with the node class in the next video. Welcome back. Let's start by talking a little bit about nodes and their role in data structures. Why are they so important? We will also implement a node class in Python. First, let's start with what they are. If we have certain values or data that we want to store in a data structure, in this case we have integers, and we want to make a data structure. How can we do that? Remember that data structures have connections. This is a key characteristic of data structures. Their elements are connected in a particular way. But we simply can't connect these elements directly. Why? They are just integers. They are values of a basic data type in Python. They are simply values. They do not have those special properties or capabilities of making a connection with other values or elements. What we can do is that we can take those values and we can surround them metaphorically with a capsule. A capsule made of code, and you will understand what this means in just a moment. But think of it as a capsule that provides additional functionality to the value, such as the ability of making connections to other capsules to form a data structure. These elements that I'm describing as capsules are called formally nodes. A node is a basic unit of a data structure, so you can think of them as the building blocks of data structures. A basic unit. These colorful circles that you can see right here and that you saw in the previous videos represented nodes. They didn't represent the actual data. They represented the nodes and their connections, because data structures are made of nodes that are connected to each other. A node can store two main elements: data, the value that we want to store in the data structure, and it can also make connections to other nodes. So these connections are stored in the node and kept as references. We will implement this in our code. We will have two attributes: the data of the node and the connections that it makes. This is essential for data structures because remember that their elements are connected. They are nodes and they have to be connected to other nodes so we can work with the data structure and perform the operations that we need to retrieve, read, update, and remove and insert data. We call these connections pointers, formally. This is very important, this term, pointer. In this case, we say that the yellow node has a pointer to the blue node, because notice where this arrow is pointing to. It is pointing towards the blue node. So that means that we can reach the blue node from the yellow node. If we are in the yellow node, we can move through the data structure towards the blue node. but we can't go back because the arrow is pointing this way. We will see how this can be implemented in Python in just a moment using object-oriented programming. But first, let's define what a pointer is formally. A pointer is defined as a reference. Right here we have a reference to another node in the data structure. So basically each node is going to store references to the nodes that it is connected to. And that is how we are going to make those connections with our code. Great, let's look at the code and how you can implement the node class in Python. We will do this step by step, and we will also create some node instances so you can see how they work. Right here we have a new project in PyCharm. To create a new project, you go to File, New Project, and then you select the location of your project and you create a new environment. You can choose how to customize these settings. You can also use the default values. And then you click Create. Okay? In this case, I named the project Python OOP project. And I chose to start with a main file. This is where we will test our classes and our code. The main file will, by default, have some code right here, some sample code that you can just delete if you don't need it. In this case, we will not need it, so I deleted it. Let's start by right-clicking right here in the name of the project, and we click on New, and then Python File. We're going to create a new module. And this module will have the node class, so we write node. By convention, according to the Python style guide, module names should be written in all lowercase letters and separated by underscores if there is more than one word in the name. In this case, we just have the word node, so we write it in lowercase, and right there we have our new module, node. So we can start writing our class. First of all, we have to define the class using the class keyword, and then we write the name of the class, which is node. Remember that class names should always start with an uppercase letter. After that, we have to start defining the class constructor, the init method, like this. By default, PyCharm will add the self parameter, and after that we need to define the two attributes of the node. What are those two attributes? In the video just a few moments ago, you learned that a node can store a value and a reference to another node. So those are the two values that we are going to assign in our class. You will see many variations of the node class. I'm just implementing a particular variation. As our second parameter, after we take the value, we can optionally take a reference to the next node, to the node that this node is going to point to. Remember that init is creating a node instance, so that instance can point to another node instance. We can take a reference to that instance, which is usually called next. You will usually see this reference as next, and we can assign a default value of none. So we make this parameter optional. If the user only wants to specify the value of the node, then he or she can only specify the value. The next reference is not necessary. By default, it will be none. But right here we see a warning that says that next, this name that we chose, shadows the built-in name next. And that is correct because in Python we have a function called next. And if we name this parameter next, we will not be able to use that function. You may choose to use this name, or you might like to adapt the name like this, next node. This is still readable, it's understandable, and it's concise, and it solves that problem of shadowing a built-in name. So we can just define our class like this. Now we have to assign the instance attributes. We say self.value is equal to value. And then we say self.next equal to next node, like this. Right here we can use the word next because we are not shadowing any names. This is just the name of an instance attribute. We're not shadowing any names. And it's not necessary to have the same word or the same name of this value and the attribute. We usually try to do that, but it's not strictly necessary. You could also remove the word node and shadow the name, but that can be problematic. So we just avoid this. And that is basically our node class. We have a value and a pointer to the next node. Remember that we are going to work with linked lists. In linked lists, each node points to the next node. So that is the only reference that we are going to take right here. We have the value and we have the pointer or the reference to the next node. Great! If that value, that reference is none, then the node doesn't have a next node. It is the last node in the list. Now let's see how you can expand this class to work with properties. You could also leave it like this because this is a very simple class. You could do that, but if you want to protect the data even further, you can just define these attributes like this and use properties. We are going to define the getter for the value. We use @property value, self is added by default, and we return the value of self_value. And there we go, we have our getter for the value. @property, we define the property, this is the name of the property, value, self, and then we return the value of the instance attribute, which we had right here. Now let's say that we want to provide a setter for the value. We can do so with this syntax, @value.setter, and then we go to the value, and we replace the value. We need to add a second argument right here, which we are going to call new value. And that will be the new value for the node. We're just replacing the value attribute, the value of the attribute. And now we have our getter and our setter for the value attribute. In this case, it's already a property. We defined a property. So let's do the same with the pointer to the next node. Let's say that we want to provide that functionality. Next, with self, and we return self.next. Great. We have our getter, and we can also define a setter, depending on what you need and what you're trying to achieve with your node class. In this case, we have to replace the value of next, but we need to add an argument, like for example, new next, or new node, or new next node. You can assign any name you like that you think it's descriptive. So here we have a full node class with properties. This particular node is adapted to work with a linked list, to be part of a linked list, because we only have one reference or one pointer to the next node in the list. This node class will be very helpful when we start working with the linked list class. We are defining it on a separate module, so we can import it to our main file and work with it. If we save this file and we go to the main file, we can import this class, like you learned in the section where we covered import statements. We say from node, we want to import the node class. You will see that it turns gray because right now we're not using it. It says unused import statement. But we are going to use it in just a moment. We are going to define, let's say, node 1. In this case, we can also add an underscore right here to separate the number. And we see that we can access the node class. We can use the node class because we imported it from the node module that we have right here. We imported it so we can use the class to create an instance. We need to pass right here, let me zoom in, we need to pass the value that we want to assign to this node. Let's say that we want to assign the value 1. And we said that this next node parameter was going to be optional. That is why we don't have any errors when we only pass one argument. This value 1 corresponds to the value parameter. And this one right here, if we don't pass any value for it, it will just be none by default. So this node will not have a next node. It's just a node without any connections. So let's check that this node has the attributes that we defined. Let's check its value. We are assigning the value 1, so this should be the value of the node. If we run the code, we see this right here, the value 1. That is exactly what we expected. Now, if we change this value to 5, we should see it updated in the print statement. Right here we see 5, because now we are creating the node with the value 5. And if we check the next attribute, we should see exactly what we get right here, none. The default value was used, this default value for the parameter, because we didn't specify the next node in the sequence. This node doesn't point to any other nodes. Now let's say that we are creating a second node. This node will have the value 3, and we are going to make the first node point to the second node. We will have something like this, node 1 pointing to node 2. For that, we need to pass the second argument, which is next, this one right here, next node. We pass the reference to node 2, and we're saying that this node instance will have the value 5, and it will point to node 2, like this. So let's start analyzing how this changes our code. Let's check the value of node 1. It's 5, like we defined right here, and now if we check the value of node 2, it's 3, like we defined right here. So the values are being assigned correctly for both nodes. Now let's check the reference to the next node. Node 2 is the last node in the sequence that we're making right here with pointers. So the value of next for the node number 2 should be none, which is exactly what we see right here. This node, node 2, doesn't point to any other nodes. But now if we replace this with node 1, we see that it does point to a node object. This is the memory location where that object is stored. But right here we can confirm that this is a node object. So node 1 is pointing to node 2. We can check if that reference is node 2 like this. If the next pointer of node 1 is node 2, then we print that value and we see that it is true. So this reference, this object is equal to this object, is this object in memory. This node is pointing to this node like this. This is very important. It's very important that you experiment with this a little bit before you move on to the next video where we will start using nodes to implement the linked list. Awesome, so let's go through this class one more time to review all the small details. We defined the node class using the class keyword and the name of the class, followed by a colon and then a blank line. After this, we have the constructor, which is the init method. The self parameter is the first parameter, so we write that it is added automatically. And we use it to assign two instance attributes to the node instance, value and next. Value is the value of the node, the value that will be stored in the data structure. And right here, we are optionally taking a reference to the next node to create those connections. It is optional because we are also defining a default value for this parameter. If the user is not passing any value for this parameter, then none will be used. And that just serves as a way to indicate that the node doesn't point to any other nodes. It's just the last node in a sequence, or it's just an isolated node. It's just there, but it doesn't point to any other nodes. Right here, we are using the properties that you learned in a section during the course. So we can, for example, if we in the future want to check if the value meets a certain criteria, meets certain properties, then we can do that before assigning the value attribute with the setter. Instead of providing direct access to the value, we are using this intermediary setter method. And we're also defining a getter like this, like a property. So we can use the name value directly as an attribute. We're also doing the same for the next property, the instance attribute. We are defining a property with a getter for the next attribute, and then we are defining a setter for this property called next, where the user can pass a new next node, okay? Go through the class one more time yourself. Make sure that you understand all the details in the class and how you can import it to the main module. Like this, we say from the node module, Notice that it is written in lowercase because this is the convention established by the Python style guide, writing module names all in lowercase. We import the node class, and we use it to create instances. We can pass the value, and we can also pass the value and the reference to the next node. So we can create this type of connection between the nodes. We will use these connections, and you will see how. This will definitely surprise you when we reach the part on linked lists. How we're going to use these connections to go from node 1 to node 2 and so on until we reach the particular spot that we need in the data structure. Great work so far. We've implemented the node class. When you're ready, go to the next lecture where you will learn about linked lists and we will start implementing this class. Now you know how to implement the node class. So let's start learning about linked lists and why they are helpful. What is a linked list? A linked list is a linear collection of data elements. The key word here is linear. This is a visual representation of a linked list. Notice that it makes a straight line where each element is connected to the next element. So that is why we call this a linear collection of data elements. Linked lists are made of nodes that are connected to each other through pointers. We can see this right here. Each element or node points to the next one. This is represented in this visual representation with these arrows that we have right here. And we will use this notation throughout the project. The connections make the sequence look more like a chain. And that is where the name linked list comes from. All the elements in the list are linked by pointers. Using pointers to connect the nodes is a characteristic of linked lists. Other data structures, like arrays, store the data in contiguous places in memory, so they can be referred to specifically using indices. This is a visual representation of those locations in memory. If you have these elements in an array, they will be stored in contiguous places in memory. Let's say that this is the computer's memory. But linked lists can store each node in non-contiguous locations, as you can see right here. And the pointers that we defined are used to get to the next node in the sequence, even if they are not physically next to each other in memory. So they can be very far apart in memory, and by the pointer, using that pointer or that reference, we can reach the next node in the sequence. Amazing, right? Well, these are two key elements of a linked list that you should know before we start implementing the class. The first one is called head, and the other one is called tail. What is head and what is tail? Head is the first node of a linked list. Like any list, a linked list has to start somewhere, right? So that is the first node. And it has to end somewhere as well. We are not going to have an infinite sequence of elements. The last node of a linked list is called the tail. This is the node that doesn't point to any other nodes in the list. There are two types of linked lists. Right here you can see a singly linked list, where each node points to the next node with only one connection in one way. You can only go from one node to the next. You can't go back to the previous node because there are no connections or pointers to go back. You can only go from the yellow node to the blue node, then to the green node, to the orange node, and so on. And if you want to start searching again, you have to start at the head again. The head, the first node in the list, will always be the entry point to the list. Some implementations also keep a reference to the tail of the list. And right here we can see another variation of the linked list, which is called a doubly linked list. It's doubly because it has two references. These references let the nodes point to each other, so you can go from one node to the next and back to the previous node, like in a two-way street. We will be working during this project with a singly linked list. And a nice challenge is to try implementing a doubly linked list yourself after completing this project. So if you want, you can try this as a challenge. Some of the advantages of linked lists include that the elements or nodes can be easily inserted and removed just by updating the pointers. They're also dynamic, so their length can increase or decrease as needed. They are not like arrays that have a fixed length and you have to create a new array when it's full. They are dynamic, so they can increase or decrease in size and length as needed. Now, they do take more memory than regular arrays. They take more memory because each node has to store a reference, so their backbone is taking more memory. Instead of actually just storing the values in memory, we're creating the nodes, and those nodes are storing additional references, so that makes them a little bit less efficient in terms of memory usage. Another disadvantage is that nodes must be read linearly, in the order that they are stored in the data structure, because we have to follow the sequence of pointers. We start at the head node, the first node in the list, and then we go through the sequence of pointers, we go through the chain, until we reach the node that we are looking for, or we reach the tail. We cannot jump from one node to the next to optimize the process. Based on these advantages and disadvantages, you can decide whether you should use this data structure for a particular purpose. So you need to decide based on these pros and cons. Awesome. Now think about how you would start implementing the linked list class in Python. Remember the attributes that we've mentioned. What are the two key elements in a data structure? In the next video, we will implement its attributes. When you're ready, start watching the next video and make sure to have your IDE ready, because we're going to code the linked list class. Welcome back. Let's start coding our linked list class. We right-click on the project and then we click on New and Python file. We're going to name the module linked list. The Python style guide recommends naming our modules in all lowercase letters and separating the words with an underscore to improve readability. So we're going to follow those guidelines. The first thing that we have to start writing in our file is the class definition. In this case, we're defining the linked list class. After we have that, we can start defining the constructor, which is the init method. We click enter right here and self is added automatically. In this case, for this particular implementation of the linked list class, we are not going to take any values as arguments when we create the linked list. We're just going to create a head attribute. This is one of the key attributes in a linked list, the head. Remember that we talked about the head and the tail. Well, there are certain implementations that keep a reference to the head node and to the tail node. In this project, we are going to keep a reference to the head node only, and we will use that as the starting point for all the different operations that we are going to implement. Initially, when we create a linked list, that head node will be the value none. So we assign by default the value none right here. Since this method is called when we create an instance of the class, the linked list will automatically have a head attribute, but that will initially be none, because we don't have a head node until we insert our first node. Until that point, when we insert the first node, we have an empty linked list. Okay? And we also have to add this line right here. Why? Because we have to import the node class. We are going to work with nodes when we implement the different operations of this class, the methods, and we will start doing that in the next video. But for now, we write the import statement. Right now it is gray because we are not using it in the class, but we will use it in the next video when we start implementing the insertion operation. PyCharm also warns us that it expects 2 blank lines after the import statement. So we're going to follow that rule and add another blank line. Great, so now we have our class definition, and initially the head of the list is equal to none. In the next video, we will start implementing the first method of this class, which will be inserting a node. When you're ready, let's start working on this first method, because inserting nodes is a key operation in any data structure. You have to insert data, update data, remove data, and also search for or find specific nodes. We will implement all of these operations in the coming videos. So when you're ready, let's continue. Let's write the necessary code for inserting data to the linked list. We will start by implementing how we can insert a node at the beginning of a linked list. If we have this node and we want to insert it to the data structure, we have three options based on criteria that we defined. We can either insert it at the beginning of the list, or we can insert it somewhere in the middle based on some sorting criteria, or we can insert it at the end as the new tail. In this video, we are going to insert the node as the head of the linked list. So we will be replacing the head, and this new node will be the very first node in our data structure. So the new node will be the new head. Like we can see right here, this is like a close-up to the data structure and how it will look like after we perform the insertion operation. This yellow node that we have right here was previously the head node. That is why we're calling it old head. And now we've included the red node before the yellow node in the list. We have the new head node and the old head node, which is now just a common node that is just part of the linked list. It doesn't have anything special, it's no longer the head node. The key thing right here is that we need to create the connection between the new head node and the old head node, so we can guarantee that we can continue having access to the linked list. That is what inserting the node at the beginning of the list is all about. We have to create a connection between the red node and the yellow node, so we can continue accessing the nodes sequentially. We will do this with our code through pointers. Think about how you would implement this in Python. Pause the video for a moment and then come back, and we will implement it step by step. Now we are back to our linked list class, and we have to start implementing the insert node method. The method is going to be named insert node. We take self as the first parameter, and then we have to take another parameter, which is going to be the value of the node. In this case, we are not going to ask the node itself. We are going to ask for the value as the argument, the value that we want to store in that node, and we are going to create the node in this method. You will see how in just a moment. We say new node, and we create the node from the value that was passed as the argument. We create the node instance. We can use the node class right here because remember that we are importing it from the node module. So we use it, we create the node right here, and we assign it to the variable new node. That is a node that we are going to insert. Now let's see what condition has to be true for us to insert the node as the new head at the beginning of the list. In the coming videos, we will complete this implementation for all the possible cases of insertion. Right now, we are just considering what happens if we have to insert the node as the new head. We say, if the head of the linked list is none, the Python style guide recommends using the is operator to check if a value is none or not, okay? So we use this operator. We should never use the equality operator to compare a value to none, according to the Python style guide. So we say, if the head is none, so if the linked list was empty, because that is what we have by default right here, when we just create the linked list and it's empty, the head will be equal to none. So we're checking if the linked list is empty. If that is the case, we just have to assign the new node as the head node. And that is what we are doing right here. I will scroll down right here, but remember that we have this import statement right here above, okay? We are assigning the new node as the head, because the list was empty. Now, we're going to implement our linked list in such a way that the elements are sorted in ascending order. This is a criteria that we're going to establish in this case, okay? So we can also say, elif the value of the head node, if the first node, its value, is greater than or equal to the value that we are going to insert, then we have to insert the new node as the head node. So what are we going to do? We are going to change the pointers, like this. The new node is going to point to the head node, to what used to be the head node. At this point, it's still the head node, so we are reassigning the pointers. We're taking the first node and we're saying the new node will point to the first node in the list. And after that, we just replace the head node with the new node. The new node is now the head, and the head is now just another node in the middle of the list. Take a moment to pause the video and analyze this code and really understand how we are reassigning the pointers and the logic of the code. This condition is also equivalent to this right here. If the value is less than or equal to the value of the head node, then we do this. I think this can be more helpful to visualize what is going to happen. If the value that we're trying to insert is less than the value of the head node, then we have to assign the node as the first node in the list because we're trying to preserve the order of the values in increasing order. So we take the new node and we make that new node point to the head node. And now, after we have that, the new node is the first node in the list, and we replace the head of the linked list. And those are the two possible cases that we could find to insert a node at the beginning of the list. If the list was empty, so if the head node was none, then we assign the new node as the new head. And if the value of the new node is less than the value of the head, then we just add it as the new head. Okay? Take a moment to pause the video, analyze this, and then come back because we are going to test how this method works and we're going to create an instance of a linked list. Okay, right here we have some code in the main module where we created some node instances and we tested our code, but we're not going to use this right now. We're going to replace the code and now we are going to import the linked list class from the linked list module. And what are we going to do with this class? Well, we are going to create a linked list and we're going to name it my linked list. We're going to use the class to create an instance of the linked list. Okay? We know that to create the instance of linked list, we don't need to pass any arguments. The head will be none by default. We can check this with a print statement, my linked list.head, and we run the code and we see the value none, because the head is by default none. Since the head is equal to none, any nodes that we insert will be the new head. Okay? Because this will be true. The head is equal to none, so we assign the new node as the head. So we can try this method right now. My linked list, and we call the method insertNode. And what value do we assign to the node? Well, anything we want. In this case, we're going to work with integers and numeric values because we're trying to preserve increasing order. That is why we are making this comparison right here. We're going to keep the list in increasing order. That is not necessary. It depends on how you want to sort the data. We're just implementing the data structure this way. Let's assign the value 9. After we call this method, the data structure will have the value 9. And we can check this by printing the head node. Okay? Like this. If we just print the head node, we will see that it has a node object. It is a node object. It's no longer none. But how can we actually check that it is the node that we inserted? Well, we can check if its value is equal to 9 by using dot notation again. With this, we are referring to the head node of the linked list. And then, by using another dot and value, we are getting the value of the head node. We run the file and we see the value 9, which is the value of the node that we just inserted. Awesome, right? Now we can insert nodes. Now let's try another value to see what happens when this part of the conditional is executed. If the value that we're trying to insert is less than the value of the current head, then we have to replace the head and reassign the pointers like this. Let's insert, after we insert the value 9, let's insert a value that is smaller than 9. Let's insert the value 3. According to what we've implemented, we should have this sequence after these two calls to insert node are executed. We should have a node with the value 9, which used to be the head node. And after we insert the node with the value 3, this should be the new head node. We had 9, and after that we are inserting the new head. So if we print the value of the head node, after this we should get the value 3. Let's run the code and see what we get. That is precisely what we get, the value 3. Awesome, right? So we've implemented two main parts of the insert operation. Inserting at the beginning if the list is empty, and inserting at the beginning if the value should be there, if it's the smallest value in the list. Now in the coming video, we will be implementing the case where we have to insert the node somewhere in the middle of the list, preserving the increasing order, okay? When you're ready, after you review all the details of the code that we wrote during this video, go to the next video to start implementing and completing the code for this method. Great work so far! Now let's see how you can insert a node in the middle of a linked list. If we want to insert a new node, this new node, at this particular location in the linked list between the green and the orange node, the first thing that we have to do is to remove the connection between the green node, which is called the previous node, and the orange node, which is called the runner node. We will use this notation, and this is very common when we work with data structures, previous and runner. You will see why this is called runner in just a moment, but it is related to the fact that it will change. Right here we have the new node. Instead of having this connection, we are going to create a connection or a pointer from the green node to the new node. And then we're going to create a pointer from the new node to the orange node, the runner. If we zoom in to see this part of the list after we've made those changes to the pointers, we will see that this results in the linear structure made with pointers. That is just a continuation of the linked list. So we're getting the same structure with the new node in the middle. We said previously that we always start moving through the linked list from the head node, which is the first node. So how can we find the insertion spot, or the place where we need to insert the node, based on the values? We will need to define certain criteria to sort the nodes if we want to insert a node in the middle. In this case, since we are working with integers and the nodes contain integers, we will be working with increasing order. So we will know that if the node reaches a point where all the values are greater than that number, then that is the insertion spot. Basically, we start at the head node as the previous node, and the next node is the runner node. We check right there if the new node meets the criteria for inserting the new node at that point. If it does, then we insert it there. But if it doesn't, we need to keep searching. And how do we do that? We move the previous and the runner nodes to the right. We're not actually changing anything in the data structure. Instead of being the yellow and the blue nodes, now they are the blue and the green nodes. You will see how we do this in our code. If this is the right place for inserting the node, then we insert it right there. But if it doesn't, we keep checking, and we keep updating the previous and the runner nodes. Once we find the right location where that node meets the criteria, for example in our case, that would be if this node has a value that is greater than this node, and this node has a value that is less than this node. Okay? So if this is less than this node, and this is greater than this node, we know that this is the insertion spot to preserve increasing order. We insert it just like you just learned. We make a pointer from the green node to the red node, and then from the red node to the orange node, from the previous to the new node, and from the new node to the runner. Think about how you would implement this in Python. Pause the video for a moment and then come back. I promise you that this will be very interesting, because we're working with new concepts, previous and runner, and you will see how they are updated. Make sure that you understand the basic principles of how this works, and if you need to, go through the videos as many times as you need to. These concepts have many details, and it is important to go through them many times to understand how they are implemented in the code. When you're ready, let's start working on the code. Now let's see how we can implement this in our code. We're going to continue working with the insert node method. Remember that in the previous video, we only covered the cases where the nodes had to be inserted as the new head. Okay? Now we're going to implement what happens if we have to search for the insertion spot and insert the node somewhere in the middle, like you saw in the diagrams. For that, we are going to use an else clause right here. We say if none of these conditions are true, so we don't have to insert the node as the head node, we have to start searching. And how are we going to do that? Well, we are going to define two variables that you saw in the diagrams. You saw these names, previous, which is going to be the head initially, and runner, which is going to be the node that is next to the head, the node that the head points to. That will be our runner. Why do we have to use this peculiar syntax? Well, because we only have the reference to the head. That is the only thing that we keep or store for the linked list, the head. So we have to work with that. We start from the head and then we get the next node from the head. Those are the values of previous and runner. We're just assigning new names to these nodes, to this pair of nodes that we can use in our code. After that, we have to write a while loop. We have to use a while loop because we don't know how many iterations we will need to find the insertion spot. What are we checking? First, we're going to check if the value of runner is not none, okay? If we haven't reached the end of the list, because the runner will be none at some point when we reach the end of the list. Well, this is not the case and we haven't reached the end of the list, then we need to continue searching. If that is the case and the value that we want to insert is greater than the value of the runner, okay? So if the value of the node that we want to insert is greater than the value of the node that we're currently evaluating, the runner, then we have to move forward and continue to the right. We haven't found the insertion spot yet because the value is greater than this value. We have to continue moving to the right to preserve increasing order. How do we do this? How do we move forward or move to the right? We moved previous and runner to the right as a pair, okay? We updated them both at once. So that is what we are going to do. What used to be the runner is now going to be the previous node because we are moving them to the right. And now the runner will be the node that came after the previous runner. The runner is now going to be the previous node. We moved one node to the right. And now, what used to be the next node of the runner will be the runner. We're moving one node to the right. Until this condition is false, we will continue moving to the right. When this is false, then we've either found the insertion spot or we've reached the end of the list. So, what we do is we reassign the pointers. The new node will point to the runner because, as you saw in the diagram right here, the new node is always in the middle between the previous and the runner node. So the new node has to point to the runner node and the previous node has to point to the new node. That is how we make the pointers to create the linear structure that keeps all the properties of the linked list. Awesome, right? With this code, we can insert a node, preserving increasing order in the data structure. Let's review what we have right here. In these first two conditions, we check if the node has to be the new head node. If that is not the case, then we go to the else clause. And what are we going to do? We are going to define two variables, previous and runner. Previous is going to refer to the head node initially, and runner is going to refer to the second node in the linked list, the node that comes after the head node. That is why we use the next pointer. We are getting the node that is after the head node. While we haven't reached the end of the list, so the runner node, which is the node to the right, is not none, and the value that we want to insert is greater than the value of the current node, Then we just continue moving to the right by reassigning the values of previous and runner. What used to be the runner now will be the previous node, because we moved one place or one spot to the right. And what used to be the node that came after the runner will now be the runner. We're just moving to the right in the list. Once we reach the insertion spot or the end of the list, because this condition is false, then we just reassign these pointers. The new node will point to the runner, and the previous node will point to the new node. Okay? That is exactly what you saw in the diagram. Great, so now we've implemented insert node and we can test it. If we go to our main module, previously we saw that if we used insert node like this, we would have this linked list. The node 3 would be the head, and then the node 9 would be another node after we insert the head, the new head, which is 3. Let's see what happens if we insert a value that is in the middle of these two values. Let's say 6. Insert node 6. Okay. We're going to insert 9. After that, we're going to insert 3, and then we are going to insert 6. What's going to happen first? We're going to have a linked list with a node, with just one node, which will be the head with 9, the value 9. Then we're going to insert the value 3, and that will make a linked list with two nodes, 3 and 9. The node with the value 3 will point to the node with the value 9. And then, after we have those values, we are going to insert the value 6. And how are we going to do that? We are going to insert the node in the middle between these two values. We will have a node with the value 3 that points to a node with the value 6, and that node will point to the node with the value 9. 3 will be the head and 9 will be the tail. This will be the final state of our linked list when we print its values right here. How can we check if this node is successfully inserted? Well, we can see its value. We can check its value. If we have a reference to the head of the linked list, that will be 3, the node that contains the value 3. But we can use next to get to this node, which is the node with the value 6. And if we print that value, we can use parentheses right here so you can see this a little bit better. First, we access the head node, and then we access the next node, and then we access the value of that node. But these are just redundant parentheses. We can use dot notation like this, without parentheses. We get a reference to the head of the linked list, then we use that to get to the next node, which is the node with the value 6, and we print the value. Okay? That is basically what we're doing right here. Let's save the file and run our code. And we see exactly that. We see the value 6, which is exactly what we expected. Now let's see what value we have for our head node. Right here, if we remove .next, we will just get the value of the head node, like this, which is 3. That is correct, and that is what we expected. Now, we can go even further and reach the third node, like this. From the head node, we reach the next node, which is the node with the value 6, and then we reach the next node from that node, which is the node with the value 9. And we print its value so we can check that it is correct, and that is what we expected, which is the value 9. So the structure of our linked list is currently what we expected, 3, 6, and 9. Awesome, right? Now we can insert elements at the beginning of the list and at any particular point in the list or spot to preserve increasing order. Preserving increasing order is just something that I decided to do in this implementation of the linked list. You don't necessarily have to do that, but you have to decide a specific criteria for sorting the elements if you want to be able to insert the nodes in the middle of the linked list. Great work so far. Go through this code one more time, at least one more time, and make sure that you understand how this part of the code works. I would recommend reviewing the code with the diagrams from this video, so you can relate what is happening with the visual representation. Great work so far! When you're ready, go to the next lecture, where we will see what happens if we try to insert a node at the end of the linked list as the new tail. I will see you there. Now let's see what happens if we try to insert a node as the new tail. That means, in our case, in our implementation, that the value is the largest or greatest value that we have inserted to the linked list so far. And how can we do that? How can we reach the tail to add the new node as the new tail? Well, we start from the head, like we always do. The head is always our starting point for these operations. Then we use the pointers to reach the next node and the next node and the next node until we reach the tail. Once we reach the tail, if we have like a close-up right here, we can see that we have to add the new node to the tail. This is a graphical representation of what we are going to do with our code. We sort of place the new node right after the tail, and we have to create a new connection between these nodes, so we can reach the new node from the old tail. We create that connection through a pointer, and we have what we call the old tail and the new tail. This is no longer a tail. It's just a regular node, another node in the middle of the list, and this new node becomes the tail. So this is the only one that we can refer to the tail after we make the insertion. The only thing that we have to do is to create a pointer or a connection between the old tail and the new tail. Okay? Think about how you could implement this in your code. Pause the video for a moment and then come back. Great work so far. We will see this in our code. Right here, if we go back to our linked list class and we go back to our insert node method, we will see that our code already covers that case, this part of the code, the else clause. Why? Because we are working with the concepts of previous and runner. And we can take our previous and runner nodes as far as the tail. We can reach the tail and we can insert that new node as the tail. Okay? We will continue as long as the runner is not none, and while the value that we are trying to insert is greater than the value of the runner. Let me show you how this works to insert a node as a new tail. Let's go to our main module. We have right here the state of our linked list after these 3 lines, and now we are going to write a 4th line where we are going to insert a new node. That will be the new tail. So far we haven't replaced the value 9 as the tail. Well, in this case there was just one node. But so far in these 2 steps the value 9 has always been the tail. Now let's try to insert the node 15 to see how it works. 4th. After we run the 4th method call, we are going to have a linked list that looks like this. 3, 6, 9, and 15. These are all nodes that contain these values, okay? So if we save the file and run our code, but first we have to update this right here. We are going from the head, which is the node with the value 3. We're going to the next node, the node with the value 6, then to the next node, the node with the value 9, and we still have to go to another node because we have 4 nodes now. We have to use next 3 times to reach the node with the value 15, and then we're going to print that value. We're going to use this line to confirm that the 4th node in the linked list is now 15. Let's save the file and run the code, and effectively we see the value 15 printed as the output right here. That is exactly what we expected. So now we have 4 nodes. With this we can confirm that. We're using head, then we are going to the 2nd node, to the 3rd node, and then to the 4th node. And we're getting the value of the 4th node. And that is returning the value 15. So that is awesome. Our code already handles that case where we need to insert the node as the new tail. Great. So we have our insert node method already implemented to cover all possible cases. Inserting as the head, inserting in the middle, and inserting as the new tail. Make sure that you understand how this code works before you move on, because we will be using the concepts of previous and runner in the coming operations that we will implement as new methods. Great work so far. When you're ready, start watching the next lecture, where we will start traversing a linked list so we can print all its elements. Welcome back. Now we're going to implement a method that will traverse a linked list so we can print all its values. First, let's see what traversing means. According to Merriam-Webster Online, to traverse means to go or travel across or over. And that is essential because in the world of computer science, which we often abbreviate as CS, traversing means visiting every element in the data structure and doing something with the data of each one of those elements. In this case, we will print their values, so we will write a print list method. How do we traverse a linked list? Remember that we defined a head node for the linked list. We will use that head node as the starting node for the entire set of operations that we will implement. We used it to insert a node, and now we will use it to traverse the list. We start at the head, and then we print its value. Then we use the node's pointer to move to the next node. Then we print its value. Again, we use the blue node's pointer to move to the green node. Then we print its value, and we repeat the process until we reach the tail, which is the last node in the list. We also print its value, and then we stop. The traversal has been completed. We accessed or visited all the elements in the data structure, all the nodes, and we did something with their data, which is printing the values in this case. We could do anything we wanted with that data, but that is the basic principle of a traversal: accessing the values, all the values, and doing something with the data. In this case, this method will be very helpful because we will be able to see with just one method call the content of the entire data structure. Think about how you would implement this in Python. Pause the video for a moment and then come back. We will implement it together. So when you're ready, come back and we start to code. Great, we're back to our linked list class in PyCharm. We have our insert node method, and now we are going to start implementing a new method to traverse the list. This method will be called print list items. You can assign the name that you find most descriptive. For example, print elements, print nodes, print values, anything you like. In this case, I named it print list items. How are we going to implement this method? First of all, we need to check if the list is empty. How are we going to print a list that is empty? Well, we have to choose what we want to print. How do we check if it's empty first? Well, we check if the head node is none. If the head node is none, then there isn't a head node and the list is empty. In that case, I decided to print empty right here. You can print another message or you can handle this scenario as you like. But if that is not the case, then we have to start using the concept of a runner. In this case, we're not going to use the concept of previous. We're only going to use the concept of a runner, because this will be the node that we will be updating as we move through the list to access each one of the nodes. We don't need to update a pair of nodes. We just need to keep track of one node, and that node will be runner. I'm calling this runner. In some implementations, you may see this as the current node. Okay? Initially, we're starting from the head, so we are using the reference to the head node, self.head, and we are assigning that reference to the runner. After that, since we don't know when we are going to reach the tail, we have to use a while loop, and we say, while the runner is not none, so while we haven't reached the end of the list, this will include the tail node, because the tail node is not none. This will only stop when we pass the tail node. While this happens, then what are we going to do with each one of those nodes? We are going to print their values. So we are going to print the runner's value on the same line, separated by a space. Let me explain this. When we use a print statement, we usually see the output printed on different lines, but we can change this with the end parameter. Since we want to present the list as a sequence of values, the values of the nodes, on the same line, we need to pass this parameter, the end parameter, and we specify a space. So we want to separate the values with a space and print them all on the same line. That is what we are going to do right here. After that, we just have to update the runner. And what are we going to assign as the next runner? The node that came after the current runner. We're taking the current runner, the current node where we are at, and then we are finding the next node in the sequence, and we are assigning that next node as the new runner. That is how we get that effect of moving through the list towards the right, going node by node and checking its value. I recommend using this print statement right here because we want to separate the output of this method from the output that we generate from other methods or other method calls, okay? If we don't add this print statement, then the next output will also be printed on the same line as these values, and that is not what we want. We usually want to get the output separated with one line per method call, so this is very helpful. Great, so now we've implemented this method. Let's go through its details one more time and then we will check how it works. We have the print list items method. This method will print all the elements or the values of the nodes in the linked list on the same line in a sequence. We define this method with the self parameter and then we check. If the head is none, so if the list is empty, then we just print the message empty. But if it's not empty, then we have to start moving through the list. We start from the head and we assign the head to the variable runner so we can update it. And we say while the runner node, which is also called the current node, is not none, so while we are iterating over the nodes in the list, we print the value of the current node and then we update the value, the current node, to the next node in the sequence, in the list. And that is basically how the code works. We add this print statement for presentation purposes, so the next output will be on a separate line. Awesome. Let's save the file and go to our main file so we can test this right here. Now we can use our method instead of using this sequence of next attributes. We can just use this. We replace this and we say my linked list dot print list items. We use empty parentheses because this method doesn't take any arguments, only self, and self is not included when we call a method. What we should see is this sequence of values printed as the output, 3, 6, 9, and 15, because we've inserted these values like this previously. Let's save the file and run the code. And that is exactly what we see right here. We see the sequence of values 3, 6, 9, and 15, and we also see the value none. Why do we see none? Because we are printing the value returned by this method call. Since we are not returning any values from the method call, we are just printing the values, we get the value none. So this can be solved by removing this call to print. We run the code and we just see the sequence of values as the output. That is exactly what we expected. This is the structure of our linked list after we inserted these nodes. So we see these values in the same order as the output, separated by a space. Awesome, right? Great work so far. Now let's see what happens. For a moment, let's comment out these method calls, and let's see what happens if we print the list items of an empty list. Let's say that these insertions never happened. So the linked list is still empty at this point. If we print the items, we see the message empty. So the method also handles that case if the list is empty, if the linked list is empty. Awesome, great work so far. Make sure that you understand the details of this implementation. We're checking if the head is none to check if the list is empty, and if it's not empty, then we are just running through the sequence of nodes, printing their values, and then getting the next node in the sequence. That is basically the logic of this method. When you're ready, start watching the next lecture where we will implement a method that will count the number of nodes in the linked list. I will see you there. Another important operation that we should implement as a method in the linked list class is to count nodes, to note how many nodes are in the linked list at any given moment. To implement this, as always, we start at the head node. And in this case, we start with a count of 0. Before we've added the head node to the count, we increment the count by 1, because we're in the head node, so there is at least one node. Then we reach the blue node, and we increment the count by 1. Then we reach the green node, and we increment the count by 1. Then the orange node, the blue node, and finally, we reach the tail. You can see how we are updating the count. At this point, we update the count to 6 because we were in the tail and we stop. So we return the final count from the method. There are two ways to implement this: iteratively, using loops, and recursively, calling the method recursively. I will show you both ways to implement this, and this will be a great opportunity to work with recursive methods. These are just like recursive functions, methods that call themselves. Think about how you would implement this in your code. You have to traverse the list and keep a counter to know how many nodes you have visited so far. Pause the video for a moment, try to come up with a solution, and then come back so we can start writing the code. Welcome back. Right here, we're with the linked list class in PyCharm. Let's start implementing count nodes. Okay, you can also name this getCount. I like the name count nodes. I think it's very descriptive. Okay, so this particular method, for the iterative implementation, we are not going to take any arguments. We want to count the nodes from the head to the tail, inclusive. What do we need? We need a variable to keep track of the counter, how many nodes we've visited so far. So we are going to define the variable count. After that, we have to get a reference to the first node that we are going to visit, and that will be the head node. We'll be updating this to move through the list. And we say, while, we use a while loop because we don't know how many nodes will be in the linked list. And we say, while runner is not none, then what do we have to do? When we go from one node to the next, we have to increment the count because we visited one additional node, and we also need to get a reference to the next node, so we can analyze or visit the next node in the linked list. And that is what we are doing right here. We are getting the next node that comes after the runner node, and we are assigning that as the new runner. So we're visiting all the nodes and incrementing the count for each one of the nodes that we visit. After we complete that loop, when we reach the tail, we just return the count. In this case, we are going to return a value from this method, the value of the count. Why does this condition work? Well, while the runner is not none, then that means that the node is a valid node. It is not the value none. The tail is also a valid node. It is not the value none. So this will work correctly, and it will return the value of count. This is the iterative implementation using a loop. Let's see how it works if we go to our main script. Right here, we had 4 calls to the insert node method for the linked list. And we said that the state of the linked list was this. We had 4 nodes with the values 3, 6, 9, and 15. Now, instead of printing the items, we want to count the nodes, okay? And for that, we just need to call the new method that we defined right here, count nodes. We take the list, the instance of the linked list, and we count how many nodes it has. But first, we have to print this value, okay? Why? Because instead of printing the value right here, we are returning the value. So it's not going to be printed automatically as the output. We have to print it ourselves. If we save the file and we run the code, we see the value 4, which is exactly what we needed. This value is correct. We have 4 nodes in this linked list, 3, 6, 9, and 15. These values are all part of their own individual nodes. Okay, now let's see what happens if we insert another value. like my linked list, insert node, let's say the value 0. And then again, we print the count. Let's see if it is updated correctly. It is, because first we see 4 right here on this line, and then when we insert another node, we see the count being updated to the value 5. Now let's see what happens if we print the count of nodes of an empty linked list. Let's say that we didn't insert these values. We will just comment them out momentarily until we test what happens. We just have the linked list, and this linked list is empty right here because these are comments at the moment. We are not inserting any values. We see the value 0, which is the correct value. The method is providing the expected output. If the linked list is empty, then the value will be 0. There are no nodes in the list. Great. This was the iterative implementation using a loop. Make sure that you understand the details of this implementation before moving on, because now we will start to dive into the recursive implementation of this method. You can implement them both ways, okay? They're exactly the same, but usually iterative implementations are a little bit more efficient in terms of performance because they do not generate all the different calls in memory, and the while loop is usually more efficient. But you can do it both ways. Let me show you. We will delete this implementation of the method, and we will say count nodes. And right now, since this is a recursive function, we will have to take another argument, which we will name node. Okay? And we say if the node is none, so if the node is no longer a valid node and we've reached the end of the list, then we return 0. Okay? That is our base case for the implementation of the recursive function. Now, else, what is our recursive case? A recursive case would be to add 1 if the node is valid. If this is false, then the node is valid. We go here and we add 1. And to that value 1, we add the result of counting. We have to use self.count nodes, starting from the next node in the sequence, okay? How are we reducing the list? We are passing the next node as the argument, and that is how we are getting the count. If the node is none, then we reach the end of the list and we are going to add 0 and stop the recursive process. Else, if we haven't reached the end of the list, we are going to increment the count by 1 and we are going to add the result returned by calling the method recursively with the next node as the argument. Okay? This is how the recursive implementation works. The iterative implementation that you just saw is equivalent and it works exactly the same. This is just to show you that the same operation can be implemented in different ways. And this is also illustrating how we can have recursive methods. Methods that call themselves. Notice that we have to use self right here because we are calling a method from the instance, okay? Let's save the file and go to our main program. Right here, our main module. Now we see sort of a warning right here where we see count nodes. Previously, we didn't take any arguments, but now we do have to take one argument, which is the initial node, the node from which we are going to start counting. In that case, since we want to start counting from the head, we will have to specify that we want to start counting from the head of the linked list. Okay? We pass that as the argument, myLinkedList.head, to the method countNodes. If we save the file and we run the code, we see 4 as the output. And that is correct. We had 4 nodes and we see the value 4 as the total count. So our recursive method works correctly. But this aspect, this characteristic of having to pass an argument to the method is not very practical because usually we want to start counting directly from the head. It really makes no sense to specify the head as the argument. Let's delete this and change our implementation of the method to make life easier for the users of our method. Instead of having to pass an argument that should be assumed by default, we are going to create something called a wrapper. We are going to define a method like this, count nodes, that is going to call this method. So right here, we are going to change the name to count nodes recursive. You can also abbreviate this as rec or recursive. I think this is more descriptive. We have the same method right here. But what we are going to do now, and we have to update this right here, because we are calling the method recursively, so these should have the same name, okay? In the new method, count nodes, which is the method that the user is going to call, we are going to execute or call count nodes recursive, passing self.head as the argument. Okay? And that is basically how we can implement this to make life easier for the user of our method. Instead of calling this directly, the user will call count nodes. And count nodes will call this method, already specifying that we want to start from the head of the linked list. This is an example of how you can change the internal implementation of a class without changing how the user interacts with your code. If we go to our main file, now we see that we don't have any warnings. The user can still use the method as it did when we had the iterative implementation. We didn't change anything of how the user interacts with the method. The user doesn't have to pass any additional arguments. He or she can just call the method using empty parentheses, and the program will work correctly. We changed the internal implementation and not the interface. But we still have a small detail right here that we need to implement before we can actually call the method. And that is adding a return statement right here. Why? Because this method will return the count, but this is the method that we are calling. So we have to return that value instead of just calling this method. We have to return the value returned by the method. Okay? We are calling this method indirectly, but this method returns a value. It returns it right here. But before, we were not returning the value from this method, so the user will not receive the value. Let's test this. Right now, like we are implementing this right here, we don't have a return statement in this method. So if we call the method, we will see the value none, because the method count nodes is not returning any values. We don't have a return statement right here, and there should be one. So we just write return right here, and that way we will be returning the value that results from this method call. Now, if we save the file and run our code, we see the value 4, which is exactly what we needed, because we have 4 nodes in the linked list. Awesome, right? You learned 2 different implementations of the count nodes method, an iterative implementation and a recursive implementation. And you also learned how you can change the implementation of a method without changing how the user interacts with the method. And that is essential, because imagine if you try to make some changes to your code and that would break everywhere in the program where you use that method. Great work so far. When you're ready, let's start working on the next lecture, where we will implement a method to find a node in a linked list, so we can verify if a particular value is in a linked list or not. When you're ready, let's start working on it. Welcome back. Determining if a particular value is in a linked list or not is another very important operation. We call this finding a node. In our implementation, we will return true if the value is in the linked list and false otherwise. Let's say that we want to find this orange node in our linked list. We can see the list right here visually, and we know that it's in the list. But in practice, you will not know if the node is in the list, and you will need to call a particular method to check this. Like always, we start searching at the head node, and we ask, is this the target node? No, it isn't, so we use the pointer to reach the next node in the linked list. And we ask the same question. Is this the target node? No, it isn't, so we use the pointer again to reach the next node, the green node. We ask, is this the target? Since it isn't, we go through the pointer again, and now we ask, is this the target node? Well, this certainly looks promising. We check that, and it is. We found it, so we return true to the method call, to the place where we call that particular method. In this case, we found the item in the linked list. But if we had been searching for an item that was not in the list, then we would have reached the tail. We would have continued our search, and once we have confirmed that there wasn't a match, we would have returned false to the method call. You can start thinking about how you would implement this in Python, in the linked list class. Pause the video and then come back so we can implement it together. We only have 2 main operations left. So when you're ready, let's get started. Right here we are again with our linked list class. We only have 2 main operations left to implement during the project, so great work so far. Right now we are going to implement the find node method to determine if a node is in the linked list or not. We go to the end of the file after the last method defined in the class, and we start defining this new method, find node. As always, the method takes self as the first parameter, and we also need to take right here an argument, because we want to get the target value. We need to know what node we are searching for, what value we are trying to get, okay? We can name this target value, target, value, anything you like. I'm just assigning this name to make the code more descriptive. How are we going to start finding or searching for the node? We need a runner node. We need to go and move through the linked list using a reference to the nodes, but we are going to start from the head as usual. After that, we have to use a while loop, because we cannot know in advance how many times we have to move to another node. And we say, while runner is not none, then we check. What are we going to check? Well, we are working with valid nodes in the list and we haven't reached the end of the list. We are going to check if the value of the current node is equal to the target value. If that is the case, then we found the node and we return true. Else, if that is not the case and the current node is not the target value, then we need to update the runner to point to the next node so we can continue moving forward. That is the basic logic of these 3 lines of code. If the value of the current node, which we are calling runner, is equal to the target value, then we return true. But if it's not, then we just need to move forward and we assign the next node as the runner node. Else, if the while loop is completed and there wasn't a match in any of the nodes in the list, then we return the value false. You can use some spaces right here to make the code more readable, like this. So we find the node by using the target value. We start from the head, which we are calling runner. In some implementations, you will see this mentioned as the current node as well. In this case, I'm keeping the concept of previous and runner, so we can be more consistent. And we say, well, runner is not none, so while we are searching through a valid part of the list and we haven't reached the end, if the value of the current node is equal to the target value, then we found the node, we found a match, and we return true. But if that is not the case, and this condition is false, then we just need to update the runner to runner.next. We could also write an else clause right here to be more explicit in our code. We say else runner equals runner.next. The else clause in this case can be omitted because we have a return statement right here. If this is true, then the value true will be returned and the execution of the method will be stopped. If this is true, then the method will stop automatically after the value is returned. So this line will never run. It's basically like having the else clause right here. It's the same effect, okay? But if you think that this is more readable visually, we could also use this. I am going to keep this like this. Else, if we haven't returned the value true during our search, that means that we haven't found a match, and we return the value false at the end of the method. Great, so now we have our implementation of find node. Make sure that you understand all the small details that are happening right here to make the process work correctly, from the argument to the loop and to the return statements. Make sure that you understand their role and why they make the process work correctly. Now let's test this method find node in our main script, in our main file. We have a linked list and we inserted these values. So this is the final state, the current state of the linked list at this point. Previously we were counting the nodes, but now we are going to find a node in the list, in the linked list. We know that we've inserted the values 3, 6, 9, and 15. So let's check if the value 3, the head, is in the linked list. We run the code and we see the value true. And that is correct because 3 is in the linked list. Now let's test a node that is in the middle of the list, like the node with the value 9. Right here we see true because it is part of the linked list. We can also check the tail, 15, and we also see true. But now if we try to search for a node that doesn't exist in the list, like for example 27, we will see the value false. The node is not in the list. If we try with a value that is smaller or less than the head, like 1, we also see false. And if we try with an intermediate value that is not in the list, like 5, we also see false. So this works correctly. Now what happens if we have an empty linked list? How does the method work in that case? Let's comment these lines of code so we can see what happens. In this case, we are not inserting any elements. We just have this empty list and we call the find node method with a value that is not in the list. We see the value false, which is correct. The list is empty, so 5 cannot possibly be there as the value of a node. Okay, awesome work. We only have one major operation left, but before you get to that video, make sure that you understand how this method works. Making diagrams and adding comments to your nodes can be very helpful to understand the concepts of previous and runner and the value and the head. There are many concepts involved in these operations, so reviewing them and explaining them in your own words can be very helpful. When you're ready, let's start working on the final operation that we will implement, delete node. Welcome back! Great work so far! We almost reached the end of this project, and we only have to implement the delete operation. We've implemented a fully functional linked list class, and you can say that you know how to implement a data structure using object-oriented programming. That's awesome, right? Well, let's start talking about the final operation that we will implement in our class, which is deleting a node. Let's see how we can delete a node from the beginning of the list. We will break this operation into 3 steps or phases, just like we implemented the insertion operation in 3 different stages. This is the node that we want to delete. Let's say that we want to delete this node. It's yellow. In this case, in this example of a linked list, it is the head node. If we zoom in to this part of the linked list, we can see this part of the data structure in more detail. We want to remove this node, the head node. And for that, we need to use the pointer to reach the blue node. We will start at the head, and then we will use the pointer to reach the blue node. Why are we doing that? Let's see. This blue node will have to be the new head, because we are removing what used to be the head. The linked list has to have a head, the first node that we are going to use to reach or get to all the other nodes in the sequence. So we need to assign this node, the blue node, as the new head node. And that will automatically detach the old head node from the data structure. Remember that we use the head node, which is an attribute of the linked list, to reach the other nodes in the sequence in the linked list. If the head node is updated, then the old head node is no longer accessible by the data structure. The data structure has no access to this node, which is exactly what we needed. And that is how we remove a node from the beginning of a linked list. Now we can start the operations from the blue node instead of the yellow node. This is what the data structure will look like after we remove the yellow node. Now the head is the blue node. Think about how you can implement this in your class. Remember that you have to assign the next node as the new head node, the second node in the linked list. Pause the video, analyze this for a moment, see if you can implement this in your code, and then come back. Here we have our linked list class. Now we have more methods implemented, and we have to implement one more, delete node. Let's go to the end of the class, and let's add this new method. Let's define it. Delete node. As always, the first parameter is self, and then we have to know what we want to delete. So that would be the target value. We're going to take the value. The first thing that we have to check in our method is if the list is empty. We can't delete something from an empty data structure. So we check if the head is none. If it is, then the list is empty. And we return false. Usually, we return a Boolean value from this method to indicate if the deletion operation was successful or not. In this case, it wasn't successful, so we return false. This is in the case where the list is empty. But if it's not empty, we still might need to delete the head node. So let's implement that case. If the value of the head node is equal to the target value, what do we have to do? We have to get the next node, the second node in the list, and assign that as the new head node. And that will automatically sort of detach the head node from the data structure, the old head node. Now the second node, the node that comes after the head node, will be the new head. And then we return true, because the deletion operation was successful. This is really nice, right? We can delete the node from the head if it matches the target value by just assigning the second node as the head node. Okay, so now we have these two cases implemented. We will have a third case in case we need to delete the node from the middle or from the end of the list, of the linked list. But we will implement that in the coming video. For now, let's test how this method works with our main module. Let's uncomment these insertions, so we are going to insert the data, and we have our linked list. This is the final state of our linked list with these 4 nodes. And what are we going to do? Instead of finding the node, which we had right here, we are going to delete a node. What node are we going to delete? Well, right now we only implemented the case where the list is empty, which is not, and where we delete the head node. So we want to delete the value 3, the node with the value 3. To confirm if the node was deleted successfully or not, we are going to call the method printListItems. Okay? We're going to print the state of the linked list before we make the deletion and after we make the deletion. We can also remove the spaces. Let's save the file and run our code. We see as our first output the state of the linked list that we have right here. 3, 6, 9, and 15. We have all those 4 values printed in the same sequence that we expected. And right here we see the value true, because the node 3 was deleted successfully, the node with the value 3. And after that deletion occurs, we see the new state of the linked list, 6, 9, and 15. The head of the linked list was removed. So this works correctly. Now let's see what happens if the linked list is empty. Okay? Let's comment this out so we are not inserting anything. These are just comments for the moment. And we have our linked list, which will be empty. We print the list items, we try to delete a node, and then we print them again. Let's see what we get. We get the correct output. We see empty because the linked list was empty at this point. Then we see false because the deletion was not successful, because we have an empty linked list, we have nothing to delete. And then we print it again and we see empty. So the program works as we expected. Great work! We have these 2 cases implemented. When you're ready and you understand how this works in detail, make sure that you understand how this is reassigning the head node. We will go to the other cases where we need to delete the node from the middle and from the end of the list. Great work so far. Now let's start the second step or stage or phase of this implementation, where we will implement deleting a node from the middle of the linked list. If we want to delete this green node, for example, we can see that this is somewhere in the middle of the linked list. So let's see how we are going to do that. Our target is this green node. We start at the head node. As always, we always start the operations at the head node. And right here, we are going to use the concepts of previous and runner, like we did before. And we have the two concepts in the same operation. We update these nodes continuously until we reach the node that we want to remove. Until the runner node is the node that we want to remove, our target node. In this case, our target node is the green node that we want to delete. Remember that the runner node, this one right here, has to be our target node, not the previous node. Once we get there, we need to remove the connections between the other nodes that surround that node, the previous node and the next node of this green node that we want to delete. And we remove these connections by changing the pointers in such a way that we sort of make a bridge between these two nodes, the previous node and the next node, the blue node and the orange node, as you can see right here. Now this sort of bridge will make the blue node point to the orange node directly. So we are kind of isolating poor green node. So this list will no longer have access to the node, and it's like it doesn't even exist. So we deleted it successfully. Since linked lists work with pointers, if there isn't any pointer to that node, it's like it doesn't exist. And that is what we are obtaining or getting by making this sort of bridge with the pointers. The final data structure would look like this, where the green node is no longer accessible and it's no longer part of the list. Think about how you would implement this particular part of the operation. Pause the video, think about the details of how you would reassign the pointers to make that bridge, and then come back. We will work on the code step by step. We are back to the linked list class, and if we go all the way to the bottom, we will find our delete node method. So far, we've implemented how to delete a node when the linked list is empty or when we have to delete the head node. But now let's implement how to delete a node from the middle of the list. We saw in the diagrams that now we have to use the two concepts, the concepts that we learned previously of previous and runner. So let's do that. We start by defining previous, which is the head node, initially. Remember that we use these variables to move through the linked list. So initially, previous is head and runner is the second node. Head.next. Once we have those initial references, we can start checking if we reach the end of the list and if the nodes are still valid. Let's see. While the runner is not none, so we haven't reached the end of the list, and the target value that we want to delete, the value of the node that we want to delete, is greater than the value of the current node, the value of the runner, then we need to continue moving. And how do we do this? We do this like in the other operations. The runner is now the previous node, and the new runner is the node that came after the runner. We're moving all the references to the right, so we can move forward in the linked list. And after we do that, after we found the actual node that we want to delete, that is the runner, when the runner is the node that we want to delete, then this condition will be false. Okay? And we say, if the runner is not none, like this, we can use parentheses to make this more readable. So if the runner is not none, then we haven't reached the end of the list, and the value of the runner is equal to the target value, then we found the node that we want to delete. In this case, in this implementation, we are not assuming that the list has the target value. So we check if the value of the runner node is equal to the target value, then what are we going to do? We are going to reassign the pointers in such a way that the previous node points to the node that comes after the runner. This is a little bit tricky to understand, but think of this as the bridge. We are making a connection that skips the current node. the node that we want to delete. We had previous and we had runner. Runner is the node that we want to delete. So what are we doing? We're making that arrow that forms the bridge between previous and the node that comes after the runner. Previous will now point to the node that comes after the runner. That is basically what this line means. Previous will now point to the node that comes after the runner node. The runner node is the node that we want to delete. So this is basically making the bridge that we need to isolate that node. In that case, we made the deletion appropriately, so we return true. But if that is not the case, then we didn't find the node in the list, so we return false. The deletion was not successful because the node was not found in the linked list. Great! So if we remove these comments right here, we have our final implementation of the method. We are checking all the cases. We are checking if the list is empty, we're checking if we have to remove the head node, and we're also checking if we have to remove an elementary node somewhere in the middle of the list. Great, awesome, so let's save the file and go to our main script, our main module. If we uncomment this to insert these values, we can start calling the method. Let's do this. This is the structure, the current structure of our linked list. We have the values 3, 6, 9, and 15. If we want to remove a node or delete a node, let's say that we want to delete the node 9, okay? So the final linked list would be 3, 6, and 15 with their corresponding nodes. We can check that this works correctly by printing the list items first and then printing the list items after we make the deletion. We can also print the value returned by delete node, so we can know if the deletion was successful or not, true or false. Let's save the file and run our code to see how it works. Awesome! This worked exactly like we expected. We had a sequence with the numbers 3, 6, 9, and 15, which were the nodes in the linked list. And the deletion was successful because we got the value true. And after we made the deletion, we deleted the node with the value 9. So we only see these three values, 3, 6, and 15. The deletion was successful. That is awesome. Let's test this with different nodes, like for example deleting the head node, which is 3. This worked correctly as well. And now let's try deleting the node with the value 6. It was removed successfully, so our code is working like we expected. Now let's see what happens if we try to delete a value that is not in the linked list, like 27. Right here we see that the value false is returned because the deletion was not successful. The linked list is not affected. We see the same 4 values in the sequence. Great, now our linked list can delete nodes from the middle of the list. I really suggest analyzing the details of this implementation. Make diagrams and write your own comments on each one of these lines of code to make sure that you understand how the process is working. Great work so far. Now we've implemented all the main functions. In the next video, we will see what happens if we try to delete a node from the end of the linked list. And that will be our final video for this project. Welcome back. Finally, we have to consider how we can delete a node from the end of the linked list. If this is the node that we want to delete, we see that it is at the very end of the data structure. It is the tail. So we will need to use the concepts of previous and runner again. We will update them as we move through the linked list until we reach the tail. We need to break the connection between the previous node and the runner node, which is now the tail node. We do this by removing the pointer from this blue node to the green node that we have right here as a tail node. That way, the green node is no longer accessible by the linked list, and the blue node becomes the new tail node because we have sort of detached the green node right here. From the data structure, we no longer have a pointer to this node. Think about this for a moment. How would you implement this operation using the concepts of previous and runner? What determines if a node is a tail node or not? Pause the video for a moment, think about this, and then come back. Right here we have our linked list class. And if you think about this carefully, we actually don't have to make any changes to our code. In our delete node method, right here in our else clause, we are already taking into account what happens if the runner node, the target that we want to delete, is the tail node, because we are checking if the runner is not none. This will get to the tail node if needed, because the last node in the list is still not none. We will continue moving through the list until we potentially reach the tail node. And if we find a match, like this one, we will just make the bridge. In this case, the code will still work, because we will be assigning a null pointer to the last node in the list, and that will completely detach the last node, what used to be the tail, the old tail. Let's see this in our main file. Let's see how this works. We are inserting these values, and let's say that we want to delete the node with the value 15, which is the tail right here. We are printing the items before we make the deletion, and then we are printing the items again. We see this as the output. The program works correctly. We had our sequence of 4 values, and then we see the value true because the node was successfully deleted. And after that, we see the linked list without the final value, 15. That is awesome. The code that we wrote in our last coding session works for this case as well. If the node that we want to delete, the target value, the node with the target value, is the tail node in the linked list. So we had 2 per 1. We were deleting in the middle of the list, and we were also considering the case where the node could be the tail node. This is great! So congratulations, we've implemented a fully functional linked list class. With the attribute head, using the node class to insert a node, and checking where we have to insert the node, then we can print all the list items, we can count the nodes iteratively and recursively if you want to implement it like this. We can also find a node and know if it's in the list or not by returning true or false. We can delete a node from the start, from the middle, and from the end of the list. So we have all the major operations of a linked list class implemented using object-oriented programming. You should be very proud of yourself. Think about how much you've learned since you started the course. Now you know how to implement a data structure using object-oriented programming. This is a very common question during interviews, and these principles will help you understand how other data structures work, so you can implement them yourself in your code using Python. Great work! Welcome to this project. We will build a war card game in Python using object-oriented programming. So you will be able to apply everything you've learned so far to build a real game. This will be a simulation of the card game, implementing all the main rules. As an interesting tip, this game is also called Battle in United Kingdom. Let's review the rules of the game. The objective of the game, our goal, is to win all the cards. The player that wins all the cards wins the game. The deck that we will use is a standard deck with 52 cards. The possible values of the cards are ace, king, queen, jack, and numeric values for the other cards, ranging from 2 to 10. In the program, we will assign the values 11, 12, 13, and 14 to these cards that are sort of like special in the deck. We will refer to them as special cards in our game, okay? This is a term that we will use in our implementation. We will need to assign them numeric values because we have to compare them to implement the rules of the game. Each card will have a suit. The possible suits in a standard 52-card deck are clubs, diamonds, hearts, and spades. We will have all of these cards for each one of the suits. Okay, we will also have 2 players, the human player and the computer player, which will draw a card automatically and play automatically. When the game starts, each player will receive 26 cards, half of the deck. Of course, the initial deck that we will use in the game, will be shuffled before the game starts, so the cards are located at random positions. Each player takes the top card from their deck on each turn. The cards that the player and the computer take will be facing up, so we will be able to see their value, description, and suit. The player who drew the card with the highest value is the winner for that round. In this game, suits are ignored, so we will only compare the cards based on their numeric value. The player who wins the round takes the 2 cards and adds them to the bottom of the deck. Now, if the cards have the same value, then the war starts. Both players take 3 cards, the human player and the computer player, from the top of their deck, and they place them facing down, so they will be hidden. They will also take 1 card, 1 additional card, and they will place it facing up. And we will make the comparisons based on the cards that are facing up. The card facing up with the highest value wins the round, and that winner takes all the cards that were drawn by both players. And the winner of the round after a war puts the cards at the bottom of his or her deck. They will be added to the bottom of the deck. If there is another tie, the process continues until one of the players wins the round. If one of the players wins all the cards in the deck, the computer player or the human player, and the other one has an empty deck, then the game stops and the player wins. And those are basically the rules of the game. Awesome! Please take a moment to analyze these rules, perhaps if you need to watch this video again, and try to identify the relevant classes that we will need to define, their attributes and methods. And you will find a written description of the requirements of the project in the next article. So, if you're ready, let's get started. Let's start writing our card game. First of all, we have to define the suit class, and this will represent a card suit. This class is going to have a class constant, which is going to be a dictionary, mapping the different suits to their corresponding symbols. Right now, we will go online to copy and paste the symbols right here. You will see how we will do that. But for now, let's just leave this as empty strings, so we can complete the dictionary. We see clubs, diamonds, hearts, and spades. These are the key of the dictionary. Now the values. If we go online to this article on Wikipedia, where it says standard 52 card deck, right here we can find the different symbols that we can copy and paste to our code. For example, right here, if I click Ctrl+C, or if I right-click right here and say copy, I can go right here to my code and click Ctrl+B or right-click and paste, and you will see that symbol appearing right here. We can add that realistic touch to our game. Let's do that with the other suits: diamonds, hearts, and spades. Like this. So we have all the suits and their corresponding symbols, and we can use those symbols in our program. To create a suit, we will need to know 2 things. We will need to know its description, and we will also need to know its symbol. But based on the description, which will be one of these 4 options, we can get the symbol from this dictionary. So we don't have to specify it as an argument. We say description and symbol. What will be the symbol? We have to take the symbol from this dictionary. This dictionary is a class attribute of the suit class. We write the name of the class, then we write the constant, and since this is a dictionary, we need to specify the key to get the corresponding symbol. And what is the key? Well, the description of the suit. We write by here description, and just to be really sure that the description is written entirely in lowercase, we can call this method lower to get a lowercase version of whatever the user entered as the argument. And we will use that in our code. Right here, we are assuming that the user entered a description, a valid description of one of these 4 suits, okay? So we have our 2 instance attributes. Each suit has a description and a symbol, and we will make them non-public because we only want to allow access to those values. We don't want them to be modified outside of the class because changing the description of a suit is not really logical, right? So right here, we are creating a getter for the description. And right here, we are going to create a getter for the symbol. Like this. Okay, so that completes our class. We have the class suit with a class constant that maps the suits, the descriptions of the suits, to the corresponding symbols. Right here, we have an init method to create an instance of suit with a description and a symbol. And right here we have the getters for the description and the symbol because we don't want them to be public, we don't want them to be modified outside of the class. Awesome, we have the first class of our project. In the next video, we will write the card class, which will be fundamental since this is a card game. Okay, so when you're ready, go to the next video, and I'll see you there. Now that we have our suit class, let's start writing our card class. Right here, you can see in my project structure that I've renamed the main.py file to suit.py because right here we have the suit class, and I created a new file called card.py. You can create a new file by right-clicking here, then selecting new and clicking right here, Python file. And then you assign a name to the file. Right here we have suit and card, so let's start writing our card class. First, we write the class header, and then we are going to define the init method. What is the init method going to do? Well, it's going to create a card instance, and we have to specify the suit and the value for that card. Those are the 2 main attributes of a card, the suit and the value. In this case, the suit will be ignored functionally in the game, but we will present it to the user to make the game more realistic. We set or define the suit as a non-public attribute, and we also define the value as a non-public attribute, because the card's suit and the value should not be changed outside of the class after the card has been created. What we do want to provide is a way to access their values, so we can create a getter with a property like this, and we can also create a getter for the value attribute like this, okay? We have the 2 main attributes of the cards defined right here. We also need to add right here above init a class constant. This constant will map or associate the values of the special cards to their descriptions like this, special cards, and that will be a dictionary, mapping the corresponding values to their descriptions. 11 corresponds to the jack, to the card jack. 12 corresponds to the queen, 13 corresponds to the king, and 14 corresponds to the ace. The ace is the card with the highest value on the deck for this game. Okay, so now let's start implementing our methods. We're going to implement a method called isSpecial. This will be a very helpful method to determine if a card is special or not. Remember that right here we are calling special cards the jack, the queen, the king, and the ace. I don't think that this is an actual formal term, but I'm choosing to name them like this in our program so we can differentiate them from the regular and common numeric cards that we can find on the deck. So we say isSpecial, and then we are going to return true if the value of the card is greater than or equal to 11. 11 is the first special card, which is the jack. And if it's greater than or equal to 11, then the card is a special card. After that, we are going to define a method that will be very helpful to present the data of the card to the user. The method will be named show, like this. We define the method, we're going to define it before isSpecial. And what are we going to do with that method? We're going to present the card to the user. It's like we're printing the card. How can we do that? First, we're going to take the value of the card. You will see why I'm doing this, of assigning this value to a variable right here in just a moment. But trust me that this will make our code more readable in this case. After this, we want to get the suit of the card, but we want to get the description of the suit, the string that describes it, like hearts or spades or diamonds, that kind of description. So what do? Well, we get the card suit right here, and since we defined the suit to be a particular object that we defined in our program, we can access its attributes, like this. The suit has a description and it has a symbol. So we're going to access the description in this case, and we are going to capitalize that description. Right here, let's analyze what this line is doing right here. We are accessing the suit of the card. Remember that we are defining the card class. So when we use self, we are referring to the card instance, the card that we want to show. We take the card suit, and since the suit is a value itself, we can access its description because we defined in the suit class a description attribute. This property that we have right here can be accessed outside of the class right here. And after we have that description, this right here will be the description, we can capitalize it so we can present it in a nice user-friendly format. Great! So we have the value and the suit. We also need the symbol of the suit. We can define a variable suit symbol. And in that case, we just need to take the card suit and access its symbol. Remember that in our suit class, we also defined a symbol attribute, and we defined it as a property, a read-only property that we can access outside of the class. So that is precisely what we are doing right here. We are accessing the two properties that we defined in our suit class. Awesome! Now we have the three elements that we want to present to the user. And we need a conditional. Why? Because the presentation will be different if the card is special. If the card is special, like a jack, a queen, a king, or an ace, we don't want to show the numbers that we assigned behind the scenes. We want to show the description. For example, jack of diamonds or queen of spades. But if the card is numeric, we do want to present the number. So we say, if the card is special, right here we are taking the card instance and we are calling the method isSpecial. This will return true if the card is special. If that is the case, then we want to present the card description to the user, not the actual numeric value. We say card description, we're going to assign it to a variable. And how do we get that description? Well, remember that right here we have a class constant, where we mapped the numbers of the cards to the corresponding descriptions for the special cards. So we're going to take the value from that dictionary, card.specialcards, and the card value will be the key. We will take the value of the card and we will use it to get its corresponding text description. If we have, for example, a card with value 12, its description is queen. So we use the value 12 right here as the key, and we will get its corresponding description. We assign it to the variable right here for readability purposes, and you will see why in just a moment when we start writing the print statement. We start writing the print statement and we will use an F string. What do we want to present to the user? Well, first we need the card's description. If the card is special, we want to say, for example, queen of spades. Queen of, and then we present the suit, the description of the suit, as text. And after that description, we also want to present the symbol of the suit. Like this, okay? As you can see, assigning these values to individual variables right here really helped us to make this print statement more readable and understandable. Can you imagine trying to understand this print statement if we had not assigned this to variables before? We would have written all of this code right here directly on the print statement, and that would greatly reduce its readability. Okay, so now we can print special cards. So what happens if the card is not special and it's like any other numeric card on the deck? Well, we need another F string right here. And what do we want to print? Well, the card value directly because it is a numeric card, and then the suit, for example, 5 of spades, and then the symbol. And now we have our card class. That's really awesome, right? We've already defined suits and cards in our game, and we will work with them as objects. Let's go over this class one more time real quick to go over the small details and how these methods are implemented. We have the card class, we have a constant right here, a class constant, a class attribute, which is a dictionary that maps the numeric values of special cards, Jack, Queen, King, and Ace to their corresponding description. Then we have the init method with the suit and the value of the card. These attributes are non-public, so we create getters for them so we can access them outside of the class. We only define getters because we don't want to modify the suit or the value of the card after it has been created. Then right here we define a method to show the card to the user. We get the card's value, the suit, and the symbol that corresponds to the suit. We use right here the suit object that we will create from the class that we defined, the suit class. That object will have a description and a symbol. So we are taking those values and assigning them to these variables, which are used right here to print the data of the card and represent it in the game. Right here we have a conditional that checks if the card is special or not, because the output will be different for each type of card. If the card is special, so if it is either Jack, Queen, King, or Ace, we will print the card's description as text of the suit and then the symbol. Right here we are getting the card's description from the dictionary, the class attribute that we have right here. We will get the value of the card, and if it is a special card, we will get its corresponding description instead of the number. Right here we get the description and we use it in the output. Else, if the card is not special and it's just a numeric card from the deck, we print its value, its numeric value, and the suit and the symbol. And finally, right here, we have a method called isSpecial, which returns true if the value of the card is greater than or equal to 11, if it is either Jack, Queen, King, or Ace. Awesome, now we have our card class completed. So we will start implementing our deck class. In the deck class, we will use both the suit class and the card class so we can start building the deck that we will use in our game. Take a moment to go over the code that we've written so far. Make sure that you understand it because we will be working with these two classes to write our deck class, okay? So when you're ready, go to the next video to implement our deck class. Welcome back! Now we will start writing our deck class. We have our suit class and our card class that we defined in the previous videos. Now, as you can see right here, I created a new file called deck. Right here, we are going to define our deck class and we will use both the card class and the suit class. So let's get started. First of all, we write the class header. We say class deck and we will start by defining our init method. What do we want to do right here? Well, the deck can be initially empty or not. When the game starts, the human player and the computer player will have their own decks, but they will be initially empty. This is how we will represent it in our program. And for that, we will be able to tell the program if we want the deck to be empty or not. So we will assign a default value right here. By default, the deck will not be empty. But if we do pass the value true for this parameter, then the deck will be empty. You will see how we will implement this in just a moment. The deck will have an initially empty list of cards. This is very similar to our backpack class, remember. We have an initially empty list of something. In this case, it's cards. And we will fill that deck with the cards that we collect. Or we will have to build the deck to make a full initial deck for our game. You will see how in just a moment when we implement the build method. Okay? To create the cards, we will also need to create this class constant. It will be a tuple with the descriptions of the suits. Clubs, diamonds, hearts, and spades. We will use this to create the cards that will fill the deck when we build the deck. And we will also need to define a size property, like this. This is interesting. This is a special case where we are defining a property for an attribute that doesn't really exist right now, that we haven't defined right here. Why? Because we want that attribute or that property to be the result of another value. Let me explain what I mean. The size of the deck will be represented by how many cards it contains. So we will find that value with the length function, like this. So whenever we use the size property in our code, we try to access that property, we will actually be finding the length of the list of cards in the deck. That's really awesome, right? So we can calculate a property sort of like dynamically. When we use that, we will get the updated value of the length of the list of cards. Great, so now we have to define a method to actually build the deck. We have an initially empty deck, and if this value is false, we will have to actually build the deck and fill it with the 52 cards that a standard deck usually has for this type of game. So how can we do that? We define the build method right here with the def keyword and self. We are not going to take any arguments. And then, what are we going to do? We say for each suit in the list of suits of the deck, right here, deck.suits, and then for each value from 2 to 14, remember that right here, we have to write 15 because range doesn't include this final value. This will return a sequence from 2 to 14. For each suit in the tuple of valid suits, and then for each value in a range from 2 to 14, we will create a card and append it to the list of cards of the deck. How can we do that? We take the list of cards for this deck, right here, and we are going to append something to that list. What are we going to append? A card object. This is where things start to get really interesting, because we are going to create a card object and then we are going to append it to the list of cards, like this. We write the name of the class right here, and then we have to pass the necessary parameters. What does a card object need to be created? If we go to the card class, right here we see that it needs a suit and it needs a value. So the first parameter is a suit, but the suit is an object as well. We defined it right here. To create a suit, we just need the description of the suit. And right here we have it. We are creating a card for each suit. So this is the value that we have to pass. And the value is provided right here from the sequence that we create with range. You will see a red warning right here that says unresolved reference, card, and suit. This is because we have to give our file a way to recognize or to import those classes from other files, suit and card. We're going to write this right here. We say, from the card file, we're going to import the card class. And then from the suit file, we're going to import the suit class. Okay? You will learn more about import statements in a coming section of the course. You will see them in detail and all the different variations that you can use. But for now, we can use this right here. From the card file, import the card class, and from the suit file, import the suit class. And you can see that the red warning disappeared, because now we do have a card class and a suit class to work with. Awesome. Let's go over this method again so you can see how it works in detail. For each suit in the list of valid suits for the deck, we're going to create a card with each one of the values from 2 to 14. Remember that we have these cards from 2 to 14 for each one of the suits that we can create. So what do we do for each suit and for each value? Well, we create a card object right here with a particular suit and a particular value that we get from these loop variables. And then after we create that object, we append it to the list of cards of the deck. Self right here refers to the deck that we are creating, that we are building right here. Okay? So now that we have this method, we can build the deck. And when we create an instance of deck, If we didn't specify that the deck should be empty, we said that it shouldn't be empty initially. If this is true, if the deck shouldn't be empty, then what should we do? Well, we should build it automatically. We want to have an initially full deck with 52 cards. So this is what we are implementing right here. If we want to build a deck, then we just call the build method right here. This code will run automatically when we create an instance of deck because we are writing it in the init method. Awesome, we have this method already defined, so we have a few small methods that we also need to implement for our deck. For example, we might need to show the deck at some point, like this. So let's implement that method. We say, for every card in the list of cards, how can we show each card? Well, we call the show method of the card instance. For each card in the list of cards of the deck, we're going to show each card. And that is our implementation of the show method for the deck. We're just relying on the show method of the cards. This method that we defined right here for the card class. We can show the deck and we can also shuffle the deck. So let's implement this functionality, shuffle. We'll need to import something called random. This is a module or Python file that gives us access to some functionality that we can use for random operations, like shuffling a sequence of items or generating random integers and things like that. So how can we shuffle our deck? We write the name of the module, and what are we going to shuffle? Well, the list of cards in our deck. Right here. We pass it as the argument, random.shuffle, and within parentheses, the list of cards. Awesome. We can also draw a card from the deck, or take a card from the deck. How can we do that? In our simulation of the deck, right here, the list of cards is working sort of like a pile, like a stack of cards. This would be the bottom of the deck, and this would be the top of the deck. The first card in this list is at the bottom of the deck, and the last card on the list is at the top of the deck. So we have to take the cards. If we want to take them from the top of the deck, we have to take the last card on this list. And that is precisely what we will do to draw a card from the deck, like this. We say, if the list of cards is not empty, that is why we are writing this right here. If the list is not empty, this will be true. Then what do we have to do? Well, we have to take the last card in the list and return it. And that is exactly what the pop method does for a list. It takes the last element in the list, in this case the list of cards, and it returns it. And of course, it removes it from the list. That is exactly what we need. Else, if the list is empty, we return none. It is recommended to be consistent in our return statements. If we return a value right here, we should specify the value none right here to be consistent. And finally, we have our last method, which is adding a card to the deck. We will need to use this when the winner has to add the cards that he or she won to the bottom of the deck. Remember that we said that the bottom of the deck is the first element in the list and the top is the last element. So we have to add the cards, the new cards, to the beginning of the list. And how can we do that? Well, we take the list of cards and where are we going to insert the card? At index 0. Like this, okay? But in this case, we will need to take a card instance right here, a card object. We need to know which card we are going to add to the deck. And what are we going to do with that card? We are going to insert it at index 0 of the list of cards in the deck. Awesome, now we have our deck class implemented completely. Let's go over the class quickly one more time to make sure that you understand how these methods were implemented. We have our deck class, and right here we have a class attribute, which is a tuple with the 4 suits: clubs, diamonds, hearts, and spades. We define our init method with a parameter isEmpty to determine if the deck is empty or not. By default, the deck will not be empty, so we will build the deck when we create it. Immediately after creating it, the deck will be built with the 52 cards that we have to add. We also create an initially empty list of cards from the deck. This list will be populated if we decide to build the deck. But if we decide that the deck should be empty, it will remain empty. Okay? We also create a property for the deck class, which is the size of the deck. We are determining the size of the deck based on the length of the list of cards, how many cards the deck currently has. We will use this property, it will be very helpful to determine if the deck is empty or not. Okay? And we can also determine how many cards are in the deck, so we can present this data to the user in the game. After that, we define the build method, where we build the deck with the 52 cards. For each suit in the list of valid suits and for each value in a range from 2 to 14, we create a card with its corresponding suit and value, and we append that card, we add the card to the list of cards, to the top of the deck. Then we have a method to show the deck. For each card in the list of cards, we are going to show that card. Right here, we are calling the show method of the card object. This is the name of the method for the deck, okay? And this is the method for the card. We are using the method for the card in the method for the deck. They are not the same method, okay? This is not like a recursive call. They are different methods. And right here, we have a shuffle method which shuffles the list of cards. We are actually mutating the list of cards to make the cards be at a random position. We are using the random module to shuffle this list. We can also draw a card from the deck. Since we said that the top of the deck was the very end of the list, then we just pop the last card from the list, and that represents taking a card from the top of the deck. The pop method removes the card from the list and it returns it, so we can return it from the method. Of course, if the list of cards is not empty. If the list is empty, we return none. And finally, right here we have an add method where we specify the card that we want to add, and we insert it to the beginning of the cards list as the very first element, which represents adding the card to the bottom of the deck. This will be helpful for when the user wins the cards in a particular round of the game. Awesome, we have our deck class already implemented. Now we have to implement the functionality of a player. So go over this code and then go to the next video so we can start implementing our player class. Now let's implement the player class for our game. We already have 3 classes defined in their own unique files: card, deck, and suit. Right here, I created a new file called player.py. So let's start defining our class. We say class player, and then we define the init method. What do we want to specify about the player? We want to know the player's name so we can customize the output in the game. We also want to know which deck object is associated to the player. And we want to know if the player is the computer player, which by default will be false. By default, the player will be human. And if we pass the value true for this parameter, then the player will be the computer player. Okay, so let's assign these instance attributes: name, deck, and is computer. Okay, great, we have these 3 instance attributes. For now, let's define the name attribute as a public attribute. And the deck attribute will be non-public. We shouldn't change the deck that is associated to the object unexpectedly. So we make it non-public, and this attribute is computer should also be non-public because it shouldn't be changed outside of the class. This shouldn't ever change after we create the player. The human player cannot become the computer player or vice versa. Great, we have the init method. So now let's define a property. We will define a property for isComputer for this attribute. This is the getter, we write isComputer right here. Now we will define a short method that will return true or false if the deck is empty or not. This method will be called hasEmptyDeck. Okay? And what are we going to return? Well, we're going to return true if the size of the deck is equal to 0. the size of the deck associated to this player, this deck that we defined right here. We are associating a specific deck object to the player. So if the player's deck, like this, is empty, so if its size is equal to 0, then we return true. And this is exactly what we get from this comparison. If that is not the case, then we return false. And we can write the method like this with just one line. Remember that we created a size property in our deck class. If we go to our deck class right here, we see the size property that we defined. This is how many cards the deck currently has. So we can use that property right here in our player class to check if the player's deck is empty or not. Awesome, we just have 2 methods left to implement to complete our player class. We have the method draw card, because we want the player to be able to draw a card from the top of the deck. We say if the player's deck is not empty, so if it's not the case that the player instance right here self refers to the player has an empty deck, this is the method that we implemented before. This will be true if the deck is empty and false otherwise. So we are negating that value and we're checking if it's not empty. If that is the case, then we just draw a card from the deck. Like this, okay? We take the player's deck that we have right here, and that deck has a method called draw. We defined it right here in our class deck. If we go right here below, we see the method draw. This method draws a card from the deck. So we are drawing a card from the deck associated to the player. Else, if the deck is empty, then we return none. Great! We can draw a card, but we also need to add a card to the deck that is associated to the player. Because if the player wins the round, he or she will have to add the cards to the bottom of the deck. So how can we do that? Well, we say add card, and we have to know which card we are going to add. This will be a parameter. How can we implement this method? Well, we take the player's deck and we add the card. Like this. The deck class has an add method. If we go to our deck class, we can go to the very bottom of the class and we will find the add method for the deck. This adds a card to the bottom of the deck, so this is the method that we are calling right here. We're taking the card that we want to add and we add the card to the deck that is associated to the player. Okay? We can also check if the deck actually exists, if it's not the value none, if the deck is a real object. Okay? Okay, right here we are assuming that the deck will always exist, okay? It will not be the value none and it will be a valid deck object. Awesome, so now we have our player class defined. We have our class constructor with a name, the associated deck, and an attribute to determine if the player is the computer player or not. By default, it is not the computer player. Then we create a property for isComputer, and we have 3 methods. Has empty deck, which returns true if the deck is empty, if the player's deck is empty. Remember that we are defining the player class, so we are checking if the player's deck is empty. We can also draw a card from the player's deck, and we can also add a card to the bottom of the deck. Awesome work! Now we have our player class. So we're almost done with our game. We just have to implement the war card game class with all of the main logic of the game and the main logic of the game in the program. When you're ready, go to the next video, but first, make sure that you understand how this code works behind the scenes and why we are writing each line of code in the methods. Review the code for suit, card, deck, and player, okay? And then go to the next video. I will see you there. Okay, so let's start implementing our war card game. This will be a class where we will define the main functionality of the game, and we will use the class in our main program to make the game actually start and work. First, we have to start with the class header. We call this war card game. Okay, and what do we want to specify for the game? What do we need to know to make a game instance? Well, each game has a player, a human player has a computer player, and it has an initial deck. So these are the 3 values that we will have to specify to create a word card game. Each one of them will be a non-public instance attribute because they will not change during the execution of the program. Each game will have an associated player, computer, and deck. Great, we have our init method so we can create game instances. But when the game starts, we want to make the initial decks. Remember that when we covered the rules of the game, we said that initially we had a deck with 52 cards. But we had to shuffle the deck and then we had to make new decks of 26 cards for each one of the players. So let's do that. We're going to define a method called makeInitialDecks, like this. This method will be in charge of making the initial decks when the game starts. What do we have to do before making the decks? We have to shuffle the deck. So, how can we do this? We can take the deck associated to the game and call its shuffle method. Remember that right here in the deck class, we have a method called shuffle that shuffles the list of cards in the deck. So that is exactly what we are calling right here. After we shuffle the deck, we have to make the player's deck and make the computer's deck. So we are going to call a method that we haven't defined yet in our class. It's called makeDeck. And we will make the deck for the player, and then we will make the deck for the computer. Don't worry, this is yellow right here because we haven't defined the method yet, but we will do it in just a moment. Right here, we are going to start defining this method, makeDeck. What are we going to do? Well, we are going to take a particular character. I'm referring to this as character because I'm using a generic or general way to refer to a particular character of the game, the computer player or the human player. So to mention them in a general way, because this can apply to either one of them, I'm just naming this character. For that specific character, we are going to take or draw 26 cards from the deck. So we are going to create or write right here a for loop that iterates 26 times. Each time we are going to take a card from the deck. And how can we do that? Well, we write the name of the deck right here, and then we draw a card by calling the draw method of the deck. If we go again to our deck class, we can see this method right here, draw. To draw a card from the top of the deck, we take the card and then what do we do with the card? Well, we are going to add the card to the character that we specified. If this is, for example, the human player, this will add a card to the human player, this card that we drew from the deck, right here. Remember that in our player class, we had an add card method. Right here we have our player class and we have an add card method that we can call to add the card to the player's deck or to the character's deck. Great, so now we have the first building blocks of our class. We have the init method to associate a player, a computer player, and the deck to a particular instance of the game. And we can also make the initial decks by shuffling the deck and by making the deck for the player and for the computer. We can make the deck by drawing 26 cards from the deck associated to the game, the initial deck that we will use in the game, and then we can add each one of those cards to our character. But we have just one small line right here missing. When we create a game instance, we want to make the initial decks immediately. We want to shuffle the deck and make the individual decks for the player and for the computer. That is the first step of the game. So we can do that automatically by calling makeInitialDecks right here on the init method. I'm just separating this with a blank line so we see that right here we are defining the attributes and right here we are calling a method. Awesome! Now we have this part of the class implemented. In the next part, we will continue implementing the logic of the game for the battle and the war. So go over this code, make sure that you understand it, and when you're ready, go to the next video to implement this part of the code. Okay, so we're back to our word card game class. Now we will implement some new methods to make the functionality of our game come to life. Particularly, we will start with the start battle method. This method will be key. In this method, we will implement the actual logic of the game. In this type of card game, we have two different stages, a battle and a war. The initial stage is a battle when the player and the computer draw two cards, and if one of the cards has a value greater than the other one, then that player wins. But if there is a tie, then we have to go to a war. So we will implement those two stages as separate methods, battle and war. They will actually be like a cycle, because the process repeats itself if there is another tie, and the battle continues, and then there is another war, and possibly we could enter a cycle. So from that cycle, we could have some cards that come from the previous stage, which could be a war. By default, this will be none. If there are no previous cards from a previous state of the game, then this value will be none. But if there is a sequence of cards that we had won from previous steps of the war, then we have to pass them as arguments right here to continue the cycle until one of the players wins all the cards in that round. Awesome, so let's start the battle. First, we are going to print a message. 1, 2, and we're going to say, let's start the battle. You can customize this to your liking and print the message that you would like to show the user when the battle starts. Now, what happens in the real game when we start a battle? Well, first we get two cards, one card from the player and one card from the computer. Each one of them draws a card from their corresponding deck. So let's do that. We're going to get a player card, which will be taken from the player's deck. Remember that the game has a player object associated to the game. This is the human player. So we can use that object to call the draw card method. This method was defined in the player class right here. It draws a card from the player's deck. So we will get that card object. And we can do the same with the computer player. Computer, and then we call draw card. Remember that the computer player is also a player, so they both have this method defined. Awesome, we have our two cards which will be facing up. What is the next step? We have to display both cards. So let's print it like this. We say your card, and what are we going to do? We are going to show the card drawn by the player. This is a card object, and we know that in our card class we defined a show method to display or to show the user the value, the suit, and the symbol of the card. So we can call that method right now. And then we are going to show the computer card. We take the computer card and we call the show method right here. So we are going to display the data of these two cards so the user can see which card actually won the round, the card with the highest value. Right here, if you are curious about these symbols that I'm adding to the strings, these represent new lines. This is because we want to separate the output and create new lines between the different messages, so the output doesn't look cluttered and full of text, okay? You will see how this looks in the final output. After we have those two cards, we just have to know who won the round. And for that, we have to compare the player's card and the computer's card. Which card has the highest value? Well, for that, we are going to implement a new method, which will return the winner of the round. That method will be called getRoundWinner. We will implement it in just a second. But the method will take the player's card and the computer's card. It will compare them, and it will return a code or a value that will represent the winner of the round. And we will also need to get the cards won by the winner of the round. Like this. We will define another method called getCardsWon by the player or the computer player. We pass the player's card and the computer card because these two cards will be won by the winner of the round. But the winner can also win previous cards from previous phases of the game. If we have a cycle where we had a battle and then a war, and we had another tie, and we had another battle and another war, the process continues, and we accumulate all of those cards until one of the players wins the round. So those accumulated cards will be these ones right here. These cards would also be won by the winner of the round. So these two methods will have to be defined right here below. But before we define them, let's see what we do with the winner. How are we going to know who won the round? Well, we're going to use particular numeric values to identify them. These values will be returned by this method. The values will be these ones right here. We will identify the player with the value 0, the computer player with the value 1, and if the output or the result of the round was a tie, we would get the value 2 right here. We will define these as class constants because we want to make our code more readable. Instead of using the values directly and compare them in our conditional, we want to add some meaning to those values. So we add them right here and we define them in the class. You will see how this works in just a second. We say if the winner of this round is equal to the code of the player, the code that we assign to the player, we will have to write it like this because this is a class attribute, a class constant. We write the name of the class followed by the name of the constant using dot notation. If that is the case, if the player, the human player, won the round, we would print this message. You won this round. And what are we going to do if the player won the round? Well, we will add the cards to the character's deck. Which character? Well, the player. And we will add all the cards won by the player. This is another method that we will define right here below. We're just writing sort of like the general structure of this method, and then we will implement these methods that will make all the functionality come to life. This is what will happen if the player wins. Now, if the computer player wins, then we will have to compare this against. We say if the code that we got for the winner is the code that we assigned to the computer, then the computer won this round. And we should print this message. The computer won this round. This time we're not so happy, so we don't add an exclamation mark. Again, we say add cards to character. Which character? Well, we are going to write this the computer character, and we're going to add all the cards won by that character. Else, if neither the player nor the computer won the game, then it's a tie. And we have to print a message like, for example, it's a tie, this is war, because now war will start. Remember that in that round, the player and the computer take 3 cards which are hidden, and they take another card, and that is basically what the war is all about. Right here, we're just implementing the basic round, which is the battle. If that is the case, if there is a tie, then we have to start the war. And we are going to pass all the cards that would have been won by the player if the round was not a tie. We still have to accumulate those cards for when one of the player wins the round. Okay? So this is the basic implementation of the battle, the start battle method. We have a print statement to start the battle. We draw 2 cards, the player card and the computer card. Then we show the cards. We get who won the round from this method that we have to implement. Based on the player's card and the computer card, we will compare their values. We will also get all the cards won by the player. The player's card, the computer's card for this round, and also all other possible cards that we might have accumulated from previous battles and wars before a player won. And we say, if the winner, right here, this will be either 0, 1, or 2. One of these codes right here. One of these sort of like codes that we assign to each one of these characters, player, computer, or if it's a tie. So we say if that value is equal to the value that we assign to the player, we print a message and we add the cards to that character. To the player, we add all the cards won for that round and for any previous rounds that were still pending to be resolved. Else, if the winner was the computer, we print this message and we do the same. We add the cards and the previous cards. If neither one of them won, then it's a tie, so the war starts and we start the war, passing the cards that would have been won in that round. Finally, we also have to return right here the winner. we will return the winner, the code that corresponds to the winner, from calling this method right here. Awesome, so let's start implementing these methods. Let's start by implementing getRoundWinner. How do we know who won that particular round? Well, let's see. GetRoundWinner. We will need to take as argument the player's card and the computer's card. We will compare them based on their value and determine who won. So we say, if the player's card, if the value of the card is greater than the value of the computer's card, then what code should we return from this method? Well, we will return the player's code. Remember that we are working right here with these class constants because we want to add meaning to our code. If instead of returning this, for example, we would just write its equivalent code, return 0. That really doesn't tell us anything about what we are returning, right? So by creating a constant for this value, we are assigning meaning to our code, and we are making the code more readable. We know that the player won the round. Else if the value of the player's card is less than the value of the computer's card, then that means that the computer won. And we return the code that corresponds to the computer. Else, we would have to return the code that corresponds to a tie, because this round resulted in a tie and we have to start the war. Awesome! We have our first method. Now let's implement the second method, getCards1. This method should return a list of all the card objects that were won by the winner of the round, or that the player should have won if the result was a tie. We would have to combine the player's card, the computer's card for that round, and all the previous cards that were accumulated from previous rounds. The result should be a list. So let's implement this method, getCards1. We would have the player's card, the computer's card, and all the previous cards. We can name this parameter like this, previous cards. So we say, if there were previous cards, so if this list is not empty, then we will have to return a combination of the player's card, the computer's card, and previous cards. Why are we writing this like this? Let me explain. The player's card and the computer's card are objects. They are card objects. So we are making them right now elements of a list. But previous cards, this parameter is a list of previous cards, of card objects. So by concatenating or joining these two lists, we're creating just one list with the previous card objects and the new card objects. And the result will be a list with all the card objects that could be won. Great! Else, if there weren't any previous cards, then we just have to return a list with the new cards, the player card and the computer's card. And that is how we can implement this method. We just return a list with all these objects. This name should be cards, okay? To match the name that we wrote right here. We have to add an S right here. So we've implemented these two methods. Finally, let's implement this method in this video, and then in the next video, we will implement the start war method. Add cards to character. Okay? Add cards to character. What is this method going to do? Well, this method is going to take the character that won the round, and it's going to take a list with all the cards that the character won, either the player or the computer. And it has to add those cards to the player or the computer's deck. So let's implement this functionality. It will have to take the character as argument and the list of cards. And then we say, for each card in the list of cards, then we just have to add that card to the character's deck. Remember that character is of type player, so we have a method called addCard that adds the card to the deck. And that is basically the implementation of these three methods. Awesome work so far! We've already completed the implementation of our war card game. We have our init method, we make the initial decks, we start the battle, and we implement the main logic. We can get the round winner, we can get all the cards that were won by the player, and we can add cards to the character's deck. So, the method that we are left to implement right now, and some other smaller methods, are start war. We have to implement what happens when there is a tie in the round, when the two cards have the same value. We will do that in the next video. Go over this code and make sure that you understand how it works and why we write each line of code in the implementation. After this, go to the next video so we can complete the implementation of our class. Welcome back. We're back to our war card game. And now we have to implement what happens when we have to start a war. Right here we see a warning because we haven't implemented what happens when there is a tie. So let's implement that. We have to define the method start war. This method is going to take one argument. So we have to define one parameter. That parameter will be the list of card objects that we got from the battle. The battle is the first round when we draw two cards. If there is a tie, then we start a war. But those two cards still have to be accumulated for when the player or the computer win the round. So we will take them as an argument right here. During the war phase of the game, the two players draw 3 cards from their deck, and these cards remain hidden, but they are accumulated for when the player wins the round. We're going to define a player cards list, which will be initially empty to keep those 3 cards that we draw from the deck. And we will also define a computer cards list for the same purpose. After that, we have to draw 3 cards. So we're going to write a loop. In that loop, we're going to draw a card for the player from the player's deck, right here, using the draw card method. And then we are going to draw a card from the computer's deck with the draw card method. We have the 2 cards that we draw. And then we have to add that card to this list. This list will contain the 3 cards that we drew from the deck for each one of the players. Right here, we are just drawing 3 cards, one for the player and one for the computer, and then we are appending them. We could also write these lines like this. We take the player's card and then we append the card to the list. We take the computer's card and then we append the card to the list. After we have that, we have 2 lists with 3 card objects for each one of the characters. We will print this message for the user. 6 hidden cards. So we will represent them with an X. This is just to add some interactivity for the user to show that we drew 6 cards and they are hidden. So after we have the war, after we started the war and we draw those 3 cards, the functionality is basically the same that we implemented for a battle method. We have to draw 2 cards and then compare them and determine which player won. So that is basically what we wrote in start battle. Therefore, we can just call the start battle method again, like in a cycle. And what are we going to pass right now to this method call? If we go to start battle, we see that we have an optional parameter, an optional argument right here. The cards that we got when we played the war. By default, this is none, in case there wasn't a war before we started the battle. But if there is, like in this case, we can pass that list with all the cards. So we will do that. We will pass the list with the 3 cards that we got from the player, and the cards that we got from the computer, and all the cards that we accumulated from the previous battle. Remember that when we start the war, we had previously another battle. So those cards should also be accumulated so the winner can take all the cards. We concatenate these 3 lists. These 3 arguments are lists, and by using the plus operator, we can concatenate them to make a single list. This will be the argument to start battle, and the cycle will continue, accumulating cards until the process stops because one of them has a higher value than the other. Great, we've implemented start battle and start war. Awesome, so we have our start war method implemented. And it works in a cycle with the start battle method. One calls the other and the other one calls the other until the process ends. When does the process end? Well, when we have one of these cases. When the winner is either the player or the computer. You can see that in these cases, we don't call the start war method again. We just call it right here when it is a tie. Please take a moment to go over this code again to understand how we start the war and how we continue the process, and how the parameters are working behind the scenes. When you're ready, go to the next video to implement 3 small methods that will be very helpful. So we'll see you in the next video to start implementing this code. Welcome back. Let's start implementing those 3 very helpful methods that will make our game come to life. First, we have to check if the game is over. And how can we do that? Well, we said in the rules that the game ended when one of the decks was empty. So the other player won all the cards in the deck. We have to check if one of the decks is empty. For example, if the player's deck is empty, like this, then the game is over. That's right, we have to end the game. So we will return true right here. We want this method to return either true or false, if the game has to end or not. If the player's deck is empty, then that means that the computer won. And we should print a descriptive message, a nice message to tell the user the result of the round. We say, we see game over, and then we see try again, the computer won, or the computer won the game. You can customize this message. After we print that, we can return the value true. You can add a blank line or just leave it like this without a blank line. But what happens if the computer's deck is empty? If this is true, then we should also print game over, like we do right here. We can copy and paste this. But now the message will be different because the player won. In this case, we're going to use an F string because we're going to customize this with the name of the player. We're going to say, excellent, you won, and then the name of the player, like this. Congratulations. And right here, we also have to return true because the game is over. One of them won. Else, if this is not the case, if neither the player nor the computer has won the game, then we just return false to tell the program that the game is not over yet. We will use this method to determine if a while loop has to continue running. So that is why we return either true or false. Let's also define a method that will be very helpful to create the user experience during the game. Print stats. Print statistics. What are we going to do right here? We're going to tell the user how many cards are on his or her deck and how many cards are on the computer's deck. So how can we do this? We just use an F string and we write, you have, and right here we are accessing the player associated to the game. We are taking his or her deck, and then we are finding the size of the deck. How many cards are still on the player's deck? Cards on your deck. And we will do the same with the computer player. We write the computer has cell.computer.deck. We access the computer's deck and we take its size. Cards on its deck. But right here you can see that we are getting a warning from PyCharm because we have to fix something in our player class. See if you can determine what we need to fix right here. The message says, access to a protected member deck of a class. This is a nice example to review what you have learned so far about public and non-public attributes. Think about this for a moment and then come back. Right here, we are accessing the deck attribute of the player class right here, but this is a protected attribute, so we shouldn't access it, at least not directly. So we have 2 alternatives. We can either provide a getter for the deck, or we can provide a method in the player class to return how many cards are still on the deck. We could provide a getter for the deck, like this with a property, and we say deck, and we return self.deck, like this. This way, we are providing a way to access the deck in another class or in another part of the program. And we will not modify it because we are not providing a setter for that attribute. Now, if we go to our class right here, we can just replace this with the name of the property, deck, right here. And we see that the warning is gone because we are no longer accessing the non-public attribute or the protected attribute directly. We are accessing it through the property, through the getter. And right here below, we are going to write 4 dashes. We have our print stats method, and we also want to define a method to print a welcome message. We will copy this format that we have right here, and then we will write this, war card game. You could also say, for example, welcome, it's great to have you here, or anything you like. Awesome! Can you believe that we already have our war card game class implemented? We have all the main functionality and logic of our game implemented and represented in this class. So we will just have to write very short code to implement it in our main file. Right here we have init, we can make the initial decks, we can start a battle, we can get who won the round, we can get all the cards that were won by the winner, and we can add cards to a particular character, start a war, check if the game is over, print statistics, and then print the welcome message for the game. In the next video, we will implement the game's main logic, and you will be able to play with your game. So, see you in the next video! Welcome back to this final phase of our project implementation. Now we will write the main logic of the game using the classes that we've defined. We have our card class, our deck class, our player class, our suit class, and our ward card game class. We will write the main logic of our code in a new file called main.py. First, to access our class, we will have to use import statements to access each one of the classes that we have defined. So we say from suit import suit. The first name is the name of the file, and this one is the name of the class that we want to import. Then we say from card import card. Then from deck import deck. From player import player. And from war card game import war card game. Okay? So these are all the import statements that we need to implement our code. Let's start by creating the player and the computer instances. We say player, player, and if we go to our player class, we can see that we need to specify a name, a deck, and whether the player is the computer player. Let's say that the name is Nora. You can customize this with your name. And then we have to specify a deck object. In this case, we can specify it directly. We can create it and write it directly as the argument. And the deck will be initially empty. When we create the deck right here, we can see that in init, we have to specify if the deck is empty or not. If the deck is empty, we have to pass a value. If it's not empty, then we can just leave it blank because false is the default value. And that's it. We have our player instance because its computer is by default false. This one is not the computer player, so we can just omit that argument. Now we're going to create our computer instance, which is also a player. The name will be just computer. And we will also create an initially empty deck. This time we have to specify that the player is the computer player. We can just write true right here, or we could also specify the name of the parameter. I really like to do this in these cases where we have more elaborate arguments because it helps you recognize visually that this is the computer player and to what parameter this argument belongs to. This is what we call keyword arguments. You specify or write the name of the parameter right here explicitly. After that, we need a deck because the game has to have an initial deck with 52 cards. We can create a deck with empty parentheses because we want the deck to be built. We want the deck to have 52 cards. So right here, by default, the value is false. The deck is not empty by default. So we can just write empty parentheses. After that, we have to create the actual game instance. We want to have a war card game associated to the player, to the computer player, and to the deck that we just created. We have our instances. Great work. We have our players, we have our deck, and we have our game. So how are we going to make this work? First, we want to take the game and we want to print a welcome message. We will be calling this method that we defined right here below. Print welcome message. And then, let's see this logic. We say while it's not the case that the game is over, remember that this returns false if the game is not over. So by adding the not, we are continuing the process. We are negating that value and we are continuing the loop. While the game is not over, then what are we going to do? We're going to start the battle and then we are going to print the statistics. Remember that we said that the statistics were how many cards were on the players and the computer stack. Well, that will be an added value to the game to make it more interactive. And we're also going to ask for user input, to ask the user if he or she would like to continue the game, to make this a little bit more interactive as well. And we say, are you ready for the next round? We add a new line character and we say, press enter to continue. Enter X to stop. Okay? The user has to press enter to continue the game or enter X to stop the process. After we have that input from the user, we can check if the user chose to stop the process. We're going to get the lowercase version of the input in case the user enters X as an uppercase letter or as a lowercase letter. That will be equivalent. So we say if the answer was X, then we just need to break out of the loop. We stop the loop and the game ends. We also end the game if the game is over, if one of the players wins all the cards. Excellent work so far. Now we've really implemented our card game. We have all the classes right here. And right here, I added something to show you that PyCharm can be a really helpful tool for this. If we go right here to the top of the file, we see that these two import statements appear in gray. That is because we are not using suit or card anywhere in this file. So we can just delete them and only keep the import statements that we are using. Those are the classes that we need for this file. Finally, let's save our file and run the main file right here. We right click on it and then we say run main. Right here we see the output. War card game. This is the welcome message that we are printing right here. Then we say let's start the battle. Your card was a jack of clubs. The computer's card was a queen of clubs. The computer won this round because the queen has a higher value than the jack. You can see right here that the symbols are really nice. And we see these are the stats. You have 25 cards on your deck. The computer has 27 cards on its deck because the computer won the 2 cards that we had right here. And we see, are you ready for the next round? Press enter to continue, enter X to stop. We press enter and we see another round right here. Let's start the battle. Your card was an ace of hearts and the computer's card was a queen of hearts. You won this round because the ace is the card with the highest value. Now we see the stats again. You have 26 cards and the computer has 26 cards. Are you ready for the next round? Let's see. We start another battle and we see ace of diamonds was your card and the computer was 10 of spades. So you won this round. Now you have 27 cards on your deck and the computer has 25 cards on its deck. If we enter X right here, we just stop the process and the game stops. We can continue as much as we need to. And if there is a tie, we will have the war. Let's run the file again and continue until we get a tie. But remember that this is random, so perhaps we will not get a tie until after a few tries. We will press enter, then enter again, then enter again, enter again. So far, we haven't had a tie. Remember that this is random, so we have to wait until the 2 cards have the same value. Right here we see a tie. This is an example of what happens when we have a tie. Let's start the battle. Your card was 8 of spades, and the computer's card was 8 of hearts. So we see it's a tie, this is war. We have 6 hidden cards that were drawn, 3 from the player's deck and 3 from the computer's deck. We start the battle again. Your card was 7 of hearts and 9 of diamonds, so the computer won this round. What happens? The computer won 1, 2, 3, 4, 5 cards. Previously, you had 33 cards on your deck in the previous step before the battle and the war started. And now, after the war has been completed, you have 28 cards on your deck. You lost 5 cards. And previously, before the war started, the computer had 19 cards on its deck. Plus 5, that would be 24. And that is exactly what the computer has on its deck right now. So this is an example of a tie. That is really awesome. And when one of the players runs out of cards on the deck, then the game will stop. But since this is random, it might take some time. We can test this by removing the input right here. Okay? We can test this by removing the input and just letting the loop run on its own. And the game will stop when the game is over, when one of the players runs out of cards. Let's test this. Right here you can see that it took the game several rounds of battles and wars to reach right here the game over. You have 0 cards on your deck, the computer has 52 cards on its deck, and we see it right here, game over. Try again, the computer won. So this is an example of what happens when we have a game over. But asking for user input makes the program more interactive and it enhances user experience. Awesome work so far. Try to remember what you knew about this when you started the course. And now you are implementing your very own card game using all the principles that you've learned with object-oriented programming. I really hope you liked this project and you found it helpful. I will see you in the next section to continue learning more about object-oriented programming. This is a fascinating topic and there is a lot to learn, so I'll see you there. Welcome to this section. Now you will learn object-oriented analysis and design. We will analyze a scenario and identify the classes, attributes, and methods that are required to build an actual tic-tac-toe game. By the end of this section, you will have a working tic-tac-toe game implemented with the principles of object-oriented programming. Are you ready? Let's begin. Before we start working on the actual game, let's see some guidelines that you can apply as you analyze problems with an object-oriented approach. First of all, classes are typically identified in a problem description from the nouns. Attributes are commonly or typically identified with the adjectives, or they could also be nouns in certain scenarios. And methods are typically extracted from the problem description as verbs. Whenever you see verbs that apply to a specific class, then that is a potential candidate for a method. Classes are usually nouns, for example, animal, person, truck, address, account, car, client, date, and task. As you can see, these are all nouns, and depending on the context of the problem, they could be potential classes. You just need to identify them in the description. Then, right here we have attributes. They are commonly extracted as adjectives. Some of them could also be nouns, so you don't have to adhere to the strict rules of adjectives. For example, color, diagnosis, the x-coordinate of a player in a game, speed, lives remaining, street, size, weight, and name. As you can see, these are all attributes of classes, or specific classes depending on the context. Remember that attributes are divided into 2 types. Class attributes, which are shared across instances of the class, and instance attributes, which are independent for each instance, so they can be updated and the other instances will not be affected. Finally, methods are commonly extracted from verbs. For example, move, display, register, sell, remove, calculate, find, concatenate, and reverse. These are examples of possible candidates for methods depending on the context. You will need to extract the verbs from the problem description. Always remember, classes are extracted from nouns, attributes from adjectives, and methods from verbs. You will have to analyze the problem description to identify these key elements for the design of the program. Great, so now that you know these guidelines, let's apply them to build the tic-tac-toe game. We will do this in the coming lectures. Before we start writing the actual code and planning the different classes that we're going to write, let's have a quick introduction to the tic-tac-toe game. This is the game that you're going to be building. This is a graphical representation. The tic-tac-toe game basically consists of a grid where each user can enter either a circle or an X depending on its designated marker. The grid has 3 rows and 3 columns, so we call it a 3x3 grid. The rows will be numbered from 1 to 3 in our game, 1, 2, and 3 from top to bottom, and the columns will be marked with a letter, A, B, and C, from left to right. So the final grid is going to look like this, where, for example, this element right here is at row 2 and column B. Or, for example, this element right here is at row 1 and column C. The player will have to enter a move, and that move is going to specify the row and the column where he or she would like to add the marker. The player wins when his or her marker fills an entire row, an entire column, or an entire diagonal, either the main diagonal or the anti-diagonal from right to left, from left to right, or from right to left. Those are the different ways that a player can win the game. So now let's see some of the formal requirements that we gathered from the game. You might have gotten these requirements from a client or from yourself as you analyze the problem and you identify what the game has to do. So let's read the first one. The game shall start by displaying a welcome message and an empty 3x3 board. This is specifying the dimensions of the board, and it's telling us that we have to display a welcome message, so that is something that we have to take care of when we implement the code. There will be 2 players in the game, the user and the computer player. Based on this description, we already know that the user has to be a class. We could also call it a player because we're going to have a human player and a computer player right here. So we could implement just one class called player and make it act as either the human player or the computer player based on a condition. That is exactly what we are going to do. We have our first class. Let's assign a different color right here. Then we have that the user will have the X marker automatically. The user will not be able to choose the marker. He or she will have to use the X marker automatically. The computer player will therefore have the O marker, the circle, automatically. The user will be prompted to enter his or her move with the format row column. For example, the number of the row, row 1, and followed by the column, which is a letter, where row can be either 1, 2, or 3, from top to bottom, as you saw in the diagram, and where the column can be either A, B, or C, from left to right. These values shall be displayed on the board as a reference for the user to know which row is which and which column is which. If the user or the computer player selects a position that is already taken, a descriptive message should be displayed. Now, the updated board shall be displayed after entering or generating the move. After the user enters his or her move, the board with the update will be displayed. And after the computer player generates his move, the board will be displayed as well with his update. For a player to win the game, that is very important. How does a player win the game? Well, there must be a full row, a full column, or a full diagonal with its corresponding marker. The game ends when there is a tie, when the board is full and no one has won the game, or when the user or the computer player wins, when this criteria is met. The program shall assume that the user input will be in a correct format. This is to make the implementation of the code in this project, in this section, a little bit simpler, because we're not going to handle mistaken or wrong user input. We're going to assume that the user enters a valid format, a number followed by a letter. And this is basically the set of requirements that the game should meet. We're going to implement them in our code, and we are going to identify the different classes. We already know that we have to create a player class. And what other important class do we need to create? See if you can identify it in this description. What other key element do we have in the description? What other object do we have to incorporate into the classes that we're going to design? Well, it's right here in the first requirement, the board. The board is one of the key actors, or one of the key objects in this description in the game. So we're going to create a board class and a player class. And the board and the player are going to have their own unique set of attributes and methods that we're going to extract from these requirements as we write the code. So now we know that we have to create two classes, the player class and the board class, because these are the two main actors in our game, the two main objects that we're going to represent. In the coming video, we're going to start implementing the player class. So I'll see you in the next video. This will be a quick preview of the project that we'll be building during this section. It's an interactive tic-tac-toe game. This is the main board of the game. A descriptive message welcoming the user is displayed, and the player is prompted to enter a move. For example, let's say that we want to add an X, a marker, to this cell, row 1, column A. We enter this move, and we see an X displayed in the updated board. Then the computer moves automatically with a randomly generated move, and the O is added to the board at that particular position in the grid. Then we can move again, for example, to A. And the computer move randomly selected the row 2 and column B, but that space was already taken. And finally, we can enter 3A, and we won the game because a column was full with the X marker. This is how the game will work, and you will have this working game by the end of this section. We will build it piece by piece, so let's start working on it. Great, now you know how the game works and the requirements that we have to meet, so let's start writing the player class. We're going to start writing this class based on the requirements that you saw in the previous video. The player has to have a marker, and the player has to be either human or a computer player. This marker will be either X or O, depending on the type of user. If the user is a human user, then the marker will be X. And if the player is the computer player, then the marker is going to be an O, a circle. The marker, by default, will be X. So we're going to assign a default value for this attribute that we have right here. Then we have the second attribute for the player class, is human. This attribute is a Boolean value, either true or false. It's true if the player is the human user, and it's false if the player is the computer player, the automated player that is going to select a random move. By default, the value of this attribute is going to be true, so by default we are going to have a human user, and we're going to have to pass the value explicitly false for the computer user. Okay, so let's start writing the player class in a Python file in our code. The first thing that we need to write is the keyword class, of course, and then we write the name of the class, which is player followed by a colon. We're going to define an init method, a constructor, to initialize these instance attributes. The attributes were marker and is human. The marker attribute, by default, had a value of X, the marker that we were going to assign to the human user by default. And the isHuman attribute is going to have a default value of true. Right here, the default value of isHuman is true. Within the body of the constructor of init, we define the instance attributes. Marker, which we're going to make non-public. To protect it from being accessed outside of the class, we're going to define a property for this attribute. And then we are going to define isHuman. And we assign this value right here. We save the file so we don't lose any work. You can save it with file, save. Great, now we have our constructor. We have this parameter marker and isHuman. We assign those values to the corresponding instance attributes, marker and isHuman. By default, this has a value of X and this has the value true. Now let's define properties so we can access these attributes just with their names without this underscore, and still the data is protected. This is a Pythonic way of defining getters and setters. We add the parameter self because we're writing a method. Remember that when we write methods, we have to add this parameter self as the first parameter, and we're going to return the value of the marker attribute. We write the name of the attribute that we defined right here, including the underscore. With this, we're going to be able to use the name of the property directly outside of the class. Then we're going to define another property, isHuman, for the other attribute. We're only going to allow access to these attributes, not changing the attributes, so we're not going to define setters for these properties. Right here, we return the value of the attribute is human, which is protected, and we create a new property. Now we can access the attribute's marker and is human. Let's start diving into the methods. Right here you can see that we have three methods that were extracted from the description: getPlayerMove, getHumanMove, and getComputerMove. The getPlayerMove is the method that we're going to call. And this method is going to call either one of these two methods, either getHumanMove or getComputerMove, based on whether the player is a human or a computer player. If the player is a human, this method will be called, and if it's a computer player, this method will be called. This method, the getHumanMove method, is going to take user input. It's going to prompt the user to enter the row and the column where he or she would like to add the marker. And this method right here, getComputerMove, is going to select a random space to make the move, a random row and a random column to add the marker. Let me add some space right here so we can add the methods in the class. We're still working on the player class, and now we are going to define three methods. We're going to start writing their definitions first, and then we're going to fill in their bodies. You will see in just a moment why. We have the getPlayerMove method, which is going to be the main method that we're going to call to get the move from a player, either the human player or the computer player. Right here in the body, we're going to temporarily add this statement right here, the pass statement. This is used when we want to fill in something that has to be completed later, but we have to fill in the body. For example, right here, we can leave the body of the method empty until we go back to it. So we just write the pass statement and then delete it. Then we're going to define the getHumanMove method. This is going to get the move from the human user. We write pass and then the computerMove method. Right here. We already know what these methods should do. This method asks for user input, for the user to enter the row and the column of the move, and this method generates a computer move automatically. It selects a row and a column randomly. These two methods are called by the main method, but this method, getPlayerMove. This is the method that we're going to call from outside of the class, and these two methods are going to be like internal to the class. So let's start writing the body of this method right here. What do we want to do? First, we want to check if the player is either a human player or a computer player. And how can we do that? Well, we can check the value of the isHuman attribute. In this case, we are going to add the underscore because we're using the internal property of the class. You could also use the name of the property, but this is commonly used outside of the class. So self is human. If the player is human, then we want to call the getHumanMove method. Else, if the player is not human, so it's the computer player, then we want to call the getComputerMove method. So this is basically the implementation of getPlayerMove. It helps us choose which method we have to call, if humanMove or computerMove. So let's implement these two methods. The getHumanMove asks for user input. Using the input function, it prompts the user to enter the move. You can customize this, but I will write this message right here. Player move, followed by a colon and a space after the colon because the prompt will be right here. So we give it some space or a separation from the colon right here. It's best for presentation purposes when we write these messages in the input function. Then we're going to store that input as a string in this variable move, and we are going to return it. That's it. That's the implementation of the getHumanMove method. And now we have to go to the getComputerMove method. This one is a little bit more elaborate because we have to generate the row and the column randomly. Let's start by generating the row. And how can we select something randomly from a sequence of valid values? Well, we use the import statement to import the random module. We go to the very top of the file, we click enter, and we add a few lines right here, and at the top of the file we write import random. This will import helpful functions that we can use to generate random numbers. In this case, we're just going to use one function, which is going to let us choose an element from a sequence randomly. We write random, which is the name of the module, dot choice, This is the name of the function that selects an element randomly from a sequence, and we write the sequence. But what sequence do we have to write right here? Well, the sequence of valid rows, 1, 2, and 3. Those are the valid identifiers for a row, as you saw in the previous diagram of the 3x3 grid. And the column will also be selected randomly. So we have choice, and now we have to choose between A, B, or C to select either the first column, the second column, or the third column. Now that we have the random choice of row and column, we can display the computer move because the human user has to know the latest move in the board. So we write computer move, which is O. We're going to remind the user the marker of the computer player, followed by a colon and a space, and we just print the row and the column. Okay? So we convert the row to a string to print it. Because this is an integer, we're going to convert it to a string, and we also write the column right here. But instead of adding a comma, which is going to add a space between the row and the column, we're going to concatenate them. So the column is immediately after the row without a space separating it. So we're going to have something like this, 1A, without a space in the middle. This is the format that we ask the user to enter the move, so we have to keep that format for the computer move. Then we simply return the string row plus column. Since we are using this expression in two different places in the function, we could perhaps store this string in a variable called move and display the move directly and return it. This is an alternative to avoid repeating this expression right here. We store it in the variable, and we use the variable directly in the print statement and in the return statement. Great, so now we've implemented the methods of the player class, and we completed the code for the player class. We have two attributes, marker and isHuman, that we have right here, and we define them as properties. Then we define the method getPlayerMove, which selects which method to call if the getHumanMove or the getComputerMove method, based on whether the player is human or not, if it's the computer player or the human player. The getHumanMove method takes the user input and it returns it in the appropriate format. Remember that right here we are assuming that the format of the user input is going to be correct, a numbered followed by a letter. And the getComputerMove method selects a random row, a random column, makes a move from that combination. It prints or displays a selected move, and it returns the move as a string. Now the player class is complete. So let's start writing the board class, which is another key class for the implementation of the tic-tac-toe game. We'll start implementing it in the next video. Great, now we've made the player class from the requirements that we gathered for this project. So now let's start analyzing and writing the board class. The board is another main element of the game. So we're going to represent it with a class, and all the main functionality of the board will be represented as methods. The key attribute of the board class is going to be the game board attribute. This attribute right here, which is going to keep or store a list that represents the board of the game, the 3x3 grid, with 3 rows and 3 columns. And how are we going to represent that exactly? Well, with a 2D list, a two-dimensional list in Python, which looks like this. It's basically a list that contains lists as elements. You can see them separated with a comma right here. So each list is an individual element of the outer list that surrounds all the different internal lists. It's a list of lists. These internal lists will make the rows of the tic-tac-toe game. And the individual elements at the same index in different lists are going to be the columns. As you can see, this would be index 0 of each one of the lists. This would be index 1, and this would be index 2. All the elements at the same index are going to be considered part of the same column. This is the basic structure of the board. And the class is going to have 3 more attributes, which are going to be constants. These constants will be empty, columns, and rows. And they will be written in capital letters, in uppercase letters, because this is a convention in Python. When something is a constant and its value should not change, we write the name in uppercase letters and underscores if we need to. The empty constant is going to store the symbol that we are going to use to denote an empty cell. For example, in this 2D list, when we find a 0 in a specific cell, in a specific location of a list, then that means that that cell is empty. We need to have some way to represent that. If neither the user or the computer player have chosen that specific location in the board. That is what the empty constant is for. The columns constant is going to map each one of the columns to its corresponding index, the grid. And the rows constant is going to be a list of the valid rows for the board, 1, 2, and 3. Let's take a closer look at this columns constant and what it's going to represent. Right here we have the 2D grid that is going to represent the board. The first column is A, the second column is B, and the third column is C. This is the notation that we use to represent the columns when we display the board to the user. But those columns have to be mapped to the corresponding indices that they represent. A is index 0 because all the elements at index 0 are part of the first column, of column A. Index 1 corresponds to all the elements of the column B. And index 2 corresponds to all the elements of the column C, of the third column in the board. So that is basically what we're going to have. We're going to have a dictionary that maps the letter A to the index 0, the letter B to the value 1, and the letter C to the value 2. The rows constant is going to be a list with the valid rows, 1, 2, and 3. Then we're going to convert them to the corresponding values as indices. Let's start implementing the board class in the code. In the same file where you've been working, where you wrote the player class, let's go right here below. And below the player class, we are going to start defining the board class with the class keyword, and we define this right here with a colon. The first thing that we're going to define in this case is going to be the constants. Empty is the first constant that we're going to add. We're going to write it in uppercase letters because this is a convention in Python. When we have a constant, we write the name in uppercase letters and underscores if necessary to separate different words. We're going to assign the value 0 to this constant. Why? Because we're going to use 0 as the symbol to denote an empty cell in the board. Then we are going to define this constant, columns. This is going to be a dictionary that is going to map the name of each one of the columns, A, B, and C, that we're using to display the board to the user, to its corresponding index in the list. 0, 1, and 2. And then we have the rows constant, which is going to be 1, 2, and 3. We can define this as a list, or we can define this as a tuple if we want to take advantage of the immutability of this data structure, that it cannot be changed or modified. So we are protecting the data much better right here. Now that we have our constants defined in the class, we can start writing the constructor, the init method. With the def keyword and double underscored, we write init. And of course, self is always the first parameter. And this was something that I decided to implement for this constructor. Well, we are going to add a parameter, GameBoard, with a default value of none. And why are we going to do this? Because perhaps the user or the developer in the future is going to want to start the game with a specific board, an initial board instead of the default board. So we're going to give that option from the start. We're going to think about the future and some future needs that the game or developers might have. In this case, we are going to give the option to customize the initial board. We're going to say, if the game board is not none, then we are going to assign that board as the game board. Else, if the game board, if this parameter was none, then we are going to use the default board that we are going to define right here. How do we define this? We start by defining a list, a regular list that you commonly use in Python. And then inside that list, we are going to add 3 lists as the elements. This is a list, this is a list, and this is a list. Right now they're empty. But we are going to structure them in such a way that we're going to have a 3x3 grid. For visibility purposes, you can write the list like this, and you will see how the grid starts to look like a grid. Right here. We are going to start with zeros because that is the value for the empty cell. We could start with zeros, or we could use this constant right here. We're starting with zeros because that is the symbol that we are defining as the symbol to denote an empty cell. We're going to use this constant in our code to check if an cell is empty in this board. This is the default board that we're going to use to start the game. Remember to separate the lists with commas. That is why it's very helpful to start defining it as we did. First the list and then populating the list with the elements. Great, we have the board class with the constants and with the constructor, the init method. So let's start analyzing what the board class needs to do, the methods that we have to implement. Let's save the file and start analyzing the methods. The first method that we're going to implement is called printBoard, and we're going to use it to display the board as we update it with the player's move. This is the first method that we're going to write, and you're going to start writing it in the next video because it is quite detailed and we have a specific format that we want to get to display the board to the user. Then in the coming videos, we're going to start implementing these two methods, submitMove and isMoveValid. The submitMove method is going to take the player's move and it's going to update the board so that it adds the marker either X or O to the board, to the two-dimensional list that represents the board. And this method, isMoveValid, is going to return true if the player's move was valid or false if it wasn't valid, if it was out of the range of valid rows or columns. Remember that we said that we're not going to check if the format of the user input is correct. We're not going to check that because we're assuming that the user entered a number followed by a letter. But that number and that letter may not be valid, so we're going to check that in this method, isMoveValid. And finally, we are going to implement this method, isWinner. This is perhaps the most detailed method of the entire game, because this is going to determine if the human player or the computer player has won the game after each move. And how is it going to do that? Well, it's going to check the current row of the move to check if the row has 3 equal symbols for the player that made the move. If the row is full with the same elements, then that means that the player won the game. Then it's going to check the row of the current move. For example, if the current move was adding this X right here to the board, then this current row is going to be checked and this column is going to be checked to see if the player has won the game. And we are also going to check the diagonal of the board, if it's full with the same marker, if the player has won with this diagonal or with the anti-diagonal, which is also a scenario where the player could win the game, if the anti-diagonal is full with the same marker as well. We're going to write these methods in a sequence of videos because they are more detailed. In the next video, we're going to print the board, so I'll see you there. Now we're in the board class and we're going to start implementing the printBoard method. So let's define it right here, printBoard. Let's move a little bit down right here so you can see it better. And we add self as the parameter for the method. The question right now is, how do we want to print the board? Well, the final output should look like this, when the game just starts and displays a descriptive message, and right here we have the board, the current state of the board when all the cells are empty. We immediately see, as part of the board, the first row. The first row has the letters as a visual reference for the user, A, B, and C. We're going to have to print this row with the corresponding spaces to make it look nice. So let's start doing that. The first line that we'd write is print A, B, and C. But we have to add the necessary spaces to make everything fit correctly. Before the A, we're going to add 1, 2, 3, and 4 spaces. And between A and B, we're going to have 3 spaces, and between B and C, we're going to have 3 spaces. 1, 2, and 3. Perfect. 1, 2, and 3. This is how we're going to align the letters to the different columns in the board that is displayed. After this first row, you can see that we have a pattern that repeats itself. We have 3 rows in which the number of the row is printed and the elements of the row are displayed, separated with a vertical bar. And after those rows, we have a line with a sequence of horizontal lines. We're going to focus on these rows right now. And how can we print them using a for loop? Well, let's see. After the print statement, we are going to write a for loop that is going to use a very nice tool that Python gives us. We're going to use enumerate. We say for I and row in enumerate. This is a function that is going to return a counter. The value of the variable I is going to be a counter that is going to be incremented by 1 for each iteration. It's going to start at 1, and then it will be incremented to 2, and then to 3. And this variable is going to have the value of the row of the board. We want to do that with the game board. And we want the count to start from 1. That is the second parameter that we pass to enumerate, because the sequence right here starts from 1, 1, 2, and 3. And then for each element of the game board, we want to assign right here the row. For each row, what do we want to do? First, we want to print the number. So that number is the value of the variable I. This number has to be followed by a vertical bar and by the value of the row in the current state of the board. We can do that with the end parameter of the print statement. Instead of making a new line after printing one, we are going to end this print statement with a vertical bar, a space, a vertical bar, and then another space. That will give us the separation that you can see right here between the number and the vertical bar, and then the center of this cell, where the value will appear if there is an X or an O. After this, we want to print each value of the row. We want to take the current state of the board, right here, and we want to print each cell in the board, whether it's an X, an O, or a 0. If it's an empty cell, we don't display anything. So we can do that with a for loop. For each column in the row, we have nested loops right here. For each column in the row, if the column is not equal to the symbol that we assigned as empty, as an empty cell, if the current value is not the marker for an empty cell, if the cell is not empty, then we print the value at the column, followed by a space, a vertical bar, and another space. That will occur if the cell is not empty, if the player or the computer have set the marker at that cell specifically. Else, if the cell is empty, then we just want to print an empty space. And we can do that right here, with a space, a vertical bar, and another space, followed by an empty string. So we don't want to print a new line, we want to continue printing on the same line, but we just want to print an empty space, a vertical bar, and another empty space. That will give us the presentation that you can see right here. If there is an X, it will be displayed right here. There will be a space before the X and a space after the X, and the X will be in the middle. The same will occur if there is a circle. And if the cell is empty, only an empty space will be displayed. What we just wrote will get us this pattern. 3 rows with the numbers 1, 2, and 3, followed by a space, and then this sequence of elements. If there is an element, it will be displayed if there is a value, and if the cell is empty, an empty cell will be displayed, followed by a vertical bar, and we get this structure in the board. Then we see this right here. We have to print a line with dashes to make the separation of the different rows. Let's do that. This is the inner nested loop that is going to print the elements of the row. After that loop has been completed, at the same level of indentation as the for keyword, we want to write this right here. A new line, because we want this series of dashes to appear in a new line. And we write the sequence of dashes. This will be approximately trial and error how many dashes you have to write. But in my case, I used approximately 15 dashes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 dashes. And that will result in this separation that you can see between the rows. Great, so now we have the print board method implemented. Let's check it out in the interactive shell to see how the board is currently printed. We can test this with the board that is generated by default that will be empty. And we should see the board as output, this part of the board. We will just see this board right here. Let's run the code and create an instance of a board. You can test your code like this as you write the methods. You just create an instance of board with an empty list of parameters to use the default value for the board, and then you call the print board method like this. And you can see the board right here, but you can see that they are not really aligned right now, and that is because there is a missing space in this definition right here. We need to add a second space before the vertical bar in the else clause. If we run the code again, you can see that now they are aligned correctly. You need to add 2 spaces before the vertical bar within the loop. Great work! We have the print board method implemented. In the next video, we're going to implement the method submitMove, and we're going to check if the move is valid. See you in the next video. Now that we have the print board method of the board class, let's start writing the submitMove and the isMoveValid methods. Below the print board method, we start by defining the submitMove method. This method is going to take 2 parameters. Of course, additional to self, which is always the first parameter in the list of a method. The second parameter is going to be move, which is going to be the string that defines the move of the player for the current iteration of the game. The move is going to be, for example, 1A. It's going to be a string with a number that represents the row and a letter that represents the column. We write this, and let's temporarily write pass right here to fill the body of the method. Let's also define the method isMoveValid. This method is going to take an additional parameter, which is the move. It's going to check if the move was valid or not, if the row and the column is in a valid range. So let's check this with this method. It's going to return true if the move is valid and false if the move is not valid. We say return, and since the condition is going to test 3 conditions, 3 aspects of the move, we are going to divide it, we're going to write it in several lines, and we can do that with parentheses in Python. We're going to check if the length of the string is 2, because there can only be 2 characters in the string. If the length is 2 and the first element, the row, is in the valid range of rows, this is the row, the first character in the string, converted to an integer. If that row is in the valid list of rows, the class attribute that we defined right here with the valid list of rows, and if the column is valid, this selects the letter from the move. Move of 0 is the first element in the string, the number, and move of 1 at index 1 is the letter. If the letter is in the valid list of columns, this is going to check if the letter is in the dictionary as a key. If all of these conditions are true, let's close the parentheses right here. We have a multi-line condition. If all of these conditions are true, then true will be returned and the move is valid, else false will be returned. Let's review the structure of this method quickly. We're checking if the move has a length of 2, if it has 2 characters. Then we're checking if the row is valid within the valid range of rows, and then we are checking if the column is valid, either A, B, or C. So we can start writing the submitMove method, which is going to use this method that we have right here. What do we need to check first to submit a move in the game? Well, first we have to check if that move is valid, right? So let's do that. Let's check this first. If the move is not valid, and how do we know if the move is valid? Well, by calling this method, isMoveValid. This is going to return true if the move is valid and false otherwise. So if the move is not valid, then we are just going to print a descriptive message. Invalid input. Please enter the row and column of your move. Example 1A. Right here, we have the print statement. Invalid input. Please enter the row and column of your move. And within parentheses, we write an example of the format that we are expecting, the number followed by a letter. After that, we are going to return. We're going to write a return statement because we want to end the function. We print this message and we end the function because the move could not be submitted. The board is not updated or modified in any way. Else, if the move was valid, then we do have to update the board. And how do we do that? First, we need to find the row and the column in the 2D list. And for that, we can get the row index again. We get the number, we convert it to an integer, and we subtract 1 to get the corresponding row index. And then, to get the index of the column, we need to find the matching number for the column. Right here, we get the value that corresponds to the letter of the move in the columns dictionary, which is a class attribute. This dictionary that we have right here that maps each column to its corresponding value or index in the list. After we have these two values, then we can check the value that is currently at that index. To check if the space was already taken, because the user could perhaps enter a move or a location that was already taken with an X or a circle. So we need to check that. To get the current value at this particular position in the board, we just retrieve that element from the two-dimensional list with the row index and then the column index. This accesses the row first, the list, and then the corresponding element in the list, the column. That value, we're going to store it in a variable called value to make the code more readable. Because we're going to use it in this conditional, we're going to check. If the value is the symbol that we assigned to an empty cell, then that means that the cell is empty. And we can update the value appropriately in the two-dimensional list that represents the board. So let's do that. Self.gameBoard, and we need to specify the row that we want to modify and the column that we want to modify. And what are we going to assign at that position of the list? Well, we are going to assign the marker of the player. That is why the method takes the player in addition to the move, because we need to know which marker we're going to assign at that particular location. Now, this handles the case when the position was empty, but if the position was already taken, then we have to print a descriptive message. This space is already taken. Let's review this method quickly. This is the submit move method. It takes the move that we want to submit to the board and the player that is submitting the move. If the move is not valid, then a descriptive message is displayed and the function is completed without affecting the board. Else, if the move was valid, then we get the corresponding row and column. We check if the position was available by checking the value that is currently at that position in the board. And if the value represents an empty cell, we assign the marker of the player at that particular position in the board. Else, if the position was already taken, we print a descriptive message. Now we have the submit move method and the isMoveValid method implemented. In the next video, we're going to implement the logic to determine if a player, either the human or the computer player, won the game by checking the rows, columns, and diagonals. So I'll see you in the next video. Now we have the submit move method and the isMoveValid methods implemented in our board class. Now we have to implement the logic that will determine if the player, the human or the computer player, wins the game. Let's do that with the isWinner method, which is going to return true if the player is the winner of the game and the game should stop. This method is going to take 3 additional parameters, besides self, of course. The player, that could be the potential winner, the row, and the column. For this method, we are going to assume the row and the column as a string, the number as a string, and the column as a string, okay? So let's implement this method. What do we need to do to check if a player is the winner of the game? Well, we have to check each row, each column, the diagonal, the main diagonal from left to right, and the anti-diagonal from right to left. Those are the possible scenarios for a player to win the game. We only need to check the row and column of the latest move, because that is the only possibility that the player will win, if the column or the row has been completed with the latest move. We're going to need smaller methods that are going to perform these tasks, checking the row, the column, and the diagonals. So the first method is going to be check row. The first argument is self, and then, of course, the method has to know which row is going to be checked, and the player that we're going to check if the player has enough markers in the row to fill the row. That is the first method. Then we are going to check the column. This method checks the column that could make the player the winner of the game, and it takes the player. And then we will have two additional methods. Check diagonal, which only takes the player, and check anti-diagonal, which takes the player as well. Okay, so we have these 5 methods that are going to help us check if the player that made the latest move is the winner of the game. Let's implement the is winner method before we implement these helper methods. If the current row is full with the player's markers, then that means that the player won, so we return true. Else if the column is full with the player's markers, then we return true. Else if the diagonal is full with the player's markers, then we also have to return true because the player won. And the same occurs with the anti-diagonal. Else, if neither one of these cases are true, if the row is not full with the markers, if the column is not full, if the diagonal is not full, and if the anti-diagonal is not full, then the player did not win the game in this particular round. So we have to return false. That is the main logic of the is winner method. We check the row, the column, the diagonal, and the anti-diagonal, and return true if either one of these cases makes the player win the game. Else, false is returned. We could make this more compact by writing a single condition with all of these conditions and using the OR operator. You can refactor this with a single condition in an if statement. So now let's implement the check row, check column, check diagonal, and check anti-diagonal methods. For the check row method, we need to check all the elements in the row. Let's visualize this. Here we have a board. Let's say that this is the current state of the board at a particular point of the game. We can identify X markers and circles, O markers. Let's say that the last move made by the user was this one right here. Row 1, column A. What the check row method is going to do is going to be checking this list right here, the first nested list at index 0. And it's going to check the individual elements of that list to verify if the number of X's, the number of markers of the player that made the last move, is equal to 3. To check if the row is full with the markers of the player. In this case, that is not true because right here we have an empty cell. If we had an X right here, then the check row method would return true because the row is full and the player won. Let's implement this in our code. The first thing that we need to do is to get the row index. Remember that we are assuming that the row and the column are passed as strings to the method. So we need to convert that into an integer like this. Then after we have the index that corresponds to the row, we need to get the actual value of the row. We need to have this list right here to check its individual elements. And that is what we are going to do. We get the row from the board. And since the game board is a list that contains lists, we are going to access the row index. This is going to return the current row, so we can check its individual values. Then we are going to use a special function, a particular function that we can use in Python, which is going to count how many elements match the element that we describe. Board row is a list, And we are going to count how many times a particular element occurs in that list. We are going to count how many times the marker of the player appears in the list. If the number of markers of the player in the row is equal to 3, then that row is full with the player's markers, and true is returned by the method. Else, false will be returned from the method right here. It always returns a Boolean value. Now we have the check row method implemented. We can check if a row determines the winner of this game. But that may not be the case. The player might still win if the column is full with its markers. So we are going to implement this method now. First, let's take a look at the logic right here. This entire column right here is made by the elements located at index 0 of each one of the lists. This is a list, this is another list, and this is another list. And these elements are located at index 0. Then, these elements are located at index 1, and these elements are at index 2. The elements of the same column have the same index in their corresponding list. That's what we're going to use to implement this method. First of all, we need to transform the column that we get as a string, right here, into an index that we can use to access the two-dimensional list. We use the columns dictionary from the board class, this dictionary that we have right here, that maps the names of the columns to the corresponding indices. And then we want to keep track of the total number of markers that we found for the player. We're going to use a for loop to get each one of the rows, and then we are going to select the element at a particular index, and that will give us all the elements of the same column. That is basically the logic that we're going to use. We're going to use a for loop to get each one of the rows, and then we're going to use an index to access all the elements of the same column. Let's implement this in the code. For I in range of 3, because we have 3 rows, if the element at that particular position, which is the row I, and the column that we had right here, the column that we're currently checking, if that element matches the marker of the player, then we are going to increment the number of total markers by 1. That is going to count how many markers of the current player are in the same column. After the loop has been completed and we know the total number of markers, then we are going to check if the total number of markers is 3. And if that is true, then that means that the column is full with the same markers that match the player markers. In that case, the user has won the game, the computer or human user. Else, the user has not won the game and we return false. That is basically the implementation of check column. We take the column as the argument, the player, and then we get the column index and we count the total number of markers in the column. We check if that total number is 3. In that case, the player has won, so we return true, else we return false. Okay, so we can check now rows and columns. What happens with the diagonals? Well, it's very similar with a little change in the indices. Let's see the logic. For the main diagonal, we have this right here. The main diagonal moves from left to right, and it is made from the element at this position, and this position right here. And what is so curious about these elements in particular in terms of their indices? Well, they have the same value for the indices. This element is at index 0, 0, the first list, and the first element in the list. Then this element is at index 1, 1. It is in the list 1, and it is the second element of the list, so it's 1, 1. And this one is at index 2, 2. Because this is the third list, index 2, and it is the third element in the list. So we can use a double index of 2, 2. As you can see, the values are equal, so we can use this in our code to check the diagonal. In this case, we don't need any specific rows or columns. We're only going to check the 3 elements in the diagonal. We're going to keep track of the total number of markers that we found so far, and we're going to use a loop to access the elements of the diagonal. For I in range of 3, because we have 3 rows, if the element at position I, so for the first row that would be 0, 0, for the second row 1, 1, and for the third row 2, 2, as you saw in the diagram, if that element is equal to the marker of the current player, then we increase the counter by 1. And finally, we check if the total number of markers is equal to 3. If that is the case, then we return true, because the player has 1. The diagonal is full with the markers of the player, else we return false. Great! Now we have the check diagonal method implemented in our code, and we only have one method left to implement, the check anti-diagonal. The anti-diagonal is this diagonal that you can see right here. This one right here, this one right here, and this one right here. That is exactly what we are going to do with a loop, but now we need a different condition, because notice the different combination of indices. We have 2 with 0, we have 1 with 1, and we have 0 with 2 right here. That would be 0, 2, 1, 1, and 2, 0. This method takes the player because we have to check the marker. We're going to keep track of the total number of markers. And then, using a for loop, we are going to iterate over all the rows. And we are going to check if the element at a particular position matches the marker of the player. Like this. But what do we need to write right here? This is not the case where the indices are equal. With the diagonal, this was quite easy, quite intuitive. The value of the column was equal to the value of the row, but now that is not the case. We need to find an expression that works for this situation. We need something that matches this pattern. Let me write this with a comment so we can illustrate this. When the row is 0, the column has to be 2. When the row is 1, the column has to be 1. And when the row is 2, the column has to be 0. Okay? And how do we do that? How do we get that pattern? Well, we can do that with this expression. If we use I for the row, because we're incrementing it using range, we get 0, 1, and 2, exactly what we need. That is the sequence returned by range. But for the column, we need to use the value of I to get this sequence, 2, 1, and 0. And how can we do that? With 2 minus I. Let's see how this works. Let me write this right here. When I is 0, when I is 1, and when I is 2. Those are the values that I is going to take, and I is representing the row. 2 minus I takes the value 2. 2 minus 1 is 1, and 2 minus 2 is 0. Exactly what we needed. I is taking the role of the row index, and 2 minus I is taking the role of the column index right here. And we get exactly what we need. So we can match and check the elements in the anti-diagonal. If we find the match, we increment the counter for the total number of markers and total markers. If that is equal to 3, then we return true. Great work! Now we have all the main methods of the board class. See you in the next video where we will implement the functionality of the game. Now we're in the final phase of the project. We implemented the 2 classes that we need for the game, the player and the board classes, and we are ready to start writing the main logic and functionality of the game. The first thing that we were asked to implement in the main game was a descriptive welcome message to welcome the user to the game, so let's do that. We are going to write a sequence of asterisks and the name tic-tac-toe in the middle. After testing the number of asterisks, I think that 16 asterisks look pretty well to cover the entire word. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Then, in the middle, we want to write a descriptive message. You can customize this, for example, tic-tac-toe with an exclamation mark. And then we can copy-paste this sequence of asterisks again. If we want to check how this looks in the interactive shell, we can run the code and see that the name is indeed covered by this sequence of asterisks. Let's remove, let's say, 2 asterisks and see if this looks even better. I think it does. We could add a space before the word tic-tac-toe. Great! So now we have a descriptive message for the user. After printing the descriptive message, we have to create the relevant instances for our game. We have the classes, but we don't have the instances that we can work with in the game. So that is our main priority right now. We're going to create an instance of board, so we can play the game with this board. And we're going to create an instance of player for the human player. And we're also going to create another instance of player for the computer player. In this case, we are going to pass 2 values, 2 arguments. The marker, which is O, and the value false, because remember that by default, this marker was X and this was true, to define a human player. In this case, we want to define a computer player, so we have to specify these 2 values. We can review this by going to the player class and going to the constructor. We can see that we have to pass the marker and false for human if we want to define a computer player. Okay. Now we have the relevant instances for the game, the board, the player, and the computer player. So the first thing that we have to do after printing the descriptive message is displaying the board, of course, to give the user an idea of the board that he or she will be playing with. Then this is where the logic of the game starts really, because the program only stops when a player wins and when there is a tie. So we are going to use a while true loop, which is going to keep looping until a condition is met and we break out of the loop. The repetitive process has to be getting the player's move. We have to ask the user to enter his or her move, so we are going to call the getPlayerMove method. On the player instance, we want to get the player's move. This is the human player. And then after we get that move, we want to submit the move to the board. We want to process that move and determine if it's valid or not and update the board accordingly. So that is what we are doing right here. Let me add descriptive comments to see what we are doing. Ask human user move. Then we are going to submit the move to the board. Then we are going to print the board because we want to see the updated version of the board. If the move wasn't valid, then the same board will be printed, but we have to show the user that the board was not updated. Then, after we have the move and we've updated the board, we want to check if the player has won. But before we do that, we need to check if the move was valid. We call the isMoveValid method and we pass the user's move. We check if the move was valid, and if it was valid, we check if the player is the winner. We pass the player, we pass the row, and we pass the column. Remember that move is represented as a string, with the row as the first character and the column as the second character. If that is the case, if the move was valid and the player was the winner, then we print, you win. You can make this message more descriptive and customize it to your liking. In that case, we break out of the loop. We stop this while true loop. We stop this infinite loop and the game ends. Else, if that doesn't happen, if the move was not valid or if the player was not the winner in this round of the game, then we want to get the computer move. We call getPlayerMove from the computer instance. Let me add this descriptive comment. Ask computer player move. And then we are going to submit that move again. Board.submit move. We pass the computer move and we pass the user, the player that is making the move. In this case, it is the computer making the move. Then we want to print the board. So we call print board on the board instance. After the computer has made the move, we want to repeat this logic and check if the computer has won the game. But this time, there is actually no need to check if the move was valid because we are generating a random move from the set of valid columns and rows. We only need to check if the computer was the winner. And pass the latest move of this player. Right here we pass the row, and right here we pass the column. If that is the case, then we print the computer won. We can write it with capitalized right here. And if that is the case, if the computer won, then we break out of the loop, we stop the process, and the game ends. This is the basic logic of the game. It is a repetitive process. We ask the user to enter the move, we submit the move and update the board accordingly, then we print the board, we check if the move was valid, and if the player was the winner in this round. If that is the case, a descriptive message is displayed and the process stops. Else, we ask for the computer player to make a move. Then we submit the move to the board and we print the board with the updates. We check if the computer player was the winner this time, and if that was the case, then we print a descriptive message and stop the game. Else, the process continues until one of the players is the winner or until there is a tie. This part right here is not repetitive, but it is key for the process. We are creating the three instances that we use in our game: the board instance, the human player instance, and the computer player instance. And we print the board initially after printing a descriptive message. Great work! So now we can run the game and see how it works. And voila! Here we have our game. We see a descriptive message welcoming the user to the game, tic-tac-toe. We see an initial empty board with the rows and the columns, and we see a prompt to enter the player move. Let's say that we want to add an X to the cell 1A. We write 1A, and we immediately see the updated board with the X on row 1 and column A, and we see the computer move which was generated automatically. The computer added an O to the cell 2A. Now we are prompted to enter another move, for example 1B. The computer added an O to the cell 3A, so in this case we're going to win because we are going to enter 1C. Like this. So a row has been filled with the player's marker, and the game ends because the player has won the match. Awesome, right? Now we have a working tic-tac-toe game implemented with the principles of object-oriented programming. I really hope you liked this project and that you found it helpful to understand how object-oriented analysis and design works behind the scenes, how we take a problem description and build a working product from it based on the classes that we identify and the methods and attributes of the classes.